Yes. So I think I'm just passing it off to you after I introduce everyone. So, yes. Okay. All right. Hello, everyone, and welcome to day 2 of the UIFCW. Thank you so much for being here in person and virtually. So my name is Alikia Srinivasan, and I'll be your MC for today. I'm a William M. LaPenta intern with the EPIC program. And I'll be your MC for today. A crucial part of my role as your MC is I must ensure time management. This is to respect the tight schedule and provide equitable speaking opportunities for all presenters. I apologize if I may need to gently alert or interrupt anyone purely in the interest of fairness and timekeeping. This is only to ensure we are all able to benefit from what all the participants have to offer. So here are some of our sessions for today. The purpose of the UIFCW is to foster collaboration among academia, industry, and operations with the aim of enhancing and accelerating contributions to the unified forecast system and improving our weather forecasting capabilities. The schedule can be found on EPIC Community Portal through the provided QR codes. And we are live streaming this event, so please be aware of any hot mics as we are video recording. Please connect with us on social media. Here is our Wi-Fi UCAR visitor, so please connect with that for Wi-Fi. Our Twitter is NOAA-EPIC and at UFS_community, and our Instagram is at NOAA-EPIC. And now I will pass it off to Dr. Jim Kinter to continue the sessions for today. Thank you so much.
Okay, we have a packed agenda for this morning. So I'm going to try to be brutal, keep you all on time as closely as possible. Our first speaker is Jessica Meisner, who's going to give us an overview of the next global forecast system. And I'll try to give you a high sign at about the 10-minute mark. So.
Okay, perfect. All right, hi everybody and good morning. My name is Jessica Meisner, and myself and Kathy Thomas are the co-project leads for GFS V17. Fenglen and Daryl are our project managers, and my co-authors are points of contact for various parts or components of the GFS system. And I would like to start by thanking them and thanking the many people, both internal to EMC, at other NOAA labs, and in the community who are contributing and actively developing the UFS and contributing towards GFS. So thank you to many of you who are in the room today. So today I want to give you an idea of where we're going with version 17. So I'm going to give you an overview of our goals and scope, where we expect to see some benefits, and then talk about in detail some of the potential component upgrades. So to get started for time, I'm just going to put this up here. I hope all of you know what the overview of the GFS system is, and I will jump to what are the goals and scope of the GFS version 17 system. So for version 16, we have a one-way coupled atmosphere wave model, and for version 17, we are going to have a coupled forecast model, including the atmosphere, land, ocean, ice, and wave models. And with these new components, we will have additional DA systems, and those will be using the JEDI for DA for our non-atmospheric components. And then we're also going to be working towards consolidation of the inset production suite. So we talked a lot about the goals for that yesterday, and so we're going to be working towards that in V17. And then lastly, we know about issues in version 16, and we're going to look to improve upon those in version 17. While these seem like 4 very simple bullets, this is a monumental effort and is a very big project, and so hopefully we'll kind of show you how big this project really is as we go through some more of the details. So here is our system overview. On the right is a schematic diagram of our UFS coupled model. So we have our atmospheric component, which uses the FE3 die core, the CCPP physics driver, and the NOAA MP land model. Currently, we are looking at having the current resolution, which is C768 with 127 levels, and potentially increasing that to that 9 kilometers for the atmosphere. For the ocean model, we are using the MOM6 ocean model at 1/4 tripolar, with a 1/4 tripolar grid. We're going to use that same 1/4 tripolar grid for the Los Alamos sea ice model, or SICE6. And then we have the wave model, WaveWatch 3. We are looking to move towards unstructured grids for the wave model, and it's undecided exactly what that resolution in that grid will look like. All of those components will be coupled through the CMIPS community mediator. And then lastly, you do see the aerosol go-kart component over here. This will be included in the GDAS deterministic forecast only, and we don't expect we are not going to have aerosol radiation interaction in that forecast model. So lastly, while GFS and GEFS will be separate systems for version 13 and version 17, we are looking to move towards unification. So our infrastructure is going to be unified, and while we will have separate code deliveries, their implementation will be on the same day. So what are our expected benefits of version 17? These are really looking towards improving on the known issues in version 16. So we're going to look to improve the forecast of low-level inversions and CAPE. We are hoping to improve hurricane forecasts, reduction of biases for temperature and wind speeds at lower levels, and we'll possibly be moving to that 9 kilometers, which will provide better boundary conditions for downstream models. On the wave side, we had low-level biases in high-amplitude wave events, and we also had some low bias in the swell forecasts in the Pacific, and so we're hoping to improve on both of those things for the wave model as well. So we're going to have a couple model. What's the benefit of that? We have inherent benefits in having a consistent atmosphere, ocean, ice, land, wave forecast. But beyond that, sometimes it's hard to articulate exactly what those other benefits will be. So we've looked to what other centers who have implemented couple models. And so based on their experience, we're hoping to see improved skill in the middle and upper troposphere and impacts based on tropical cyclones. That being said, none of these are guaranteed for our system, but this is where we expect to maybe see some improvements. So moving on to data assimilation. So we're gonna have weakly coupled data assimilation. That means that each of the components have their own data assimilation systems, but then we have a coupled forecast model. So for the atmosphere, we are still going to be GSI based. So we'll have the hybrid 4D ENVAR for the deterministic analysis and the GSI-based 4D LETKF for the ensemble analysis. We will also be looking to add a early cycle ensemble analysis that will be used for GEFS initialization. Then moving on to the marine components, we'll be using SOCA, the sea ice, ocean, and coupled analysis. And that is actually strongly coupled between the ocean and the ice model. And we will be using JEDI-based 3D versions of the schemes that we're using the GSI 4D versions for the atmospheric model for the ocean and ice. For land, we're looking at JEDI-based 2D OI for snow and a possible LETKF for soil moisture and soil temperature. We mentioned aerosols for that GDAS deterministic forecast, and for that, we'll be looking at a JEDI-based 3D VAR. So moving on to the atmospheric model, while we will still be using GSI, there will be improvements. So we talked about the early cycle ENKF for those GEFS initial conditions. And then we'll also have updates for the accommodation of the Thomson microphysics. So we're moving from GFDL to Thomson microphysics, and there will be adjustments in the DA schemes to adapt to that. We will also have updates for radiance and all sky assimilations, for example, upgrading to CRTM 3.0. We will also be leveraging work from RFS in terms of scale-dependent localization improvements and work towards that, and then also incorporating new observations. So for the atmospheric physics, we are looking at updates to cumulus convection and PBL to improve hurricane forecasts and CAPE. We already talked about upgrading the microphysics schemes from GFDL to Thomson microphysics. We will also be looking at updates to gravity wave drag, radiation, and updates to move towards fractional grids, which is what's used for the coupled model. Moving on to the land component. So we are replacing NOAA LSM with the NOAA MP model. That model was created to improve on the known issues from the NOAA LSM. So some updates for the NOAA MP, we're gonna have canopy heat storage, increased number of soil levels, increase in the depth, and we're gonna have updated vegetation type and land sea masks by using the VIIRS data set. So continuing on, for our marine components, for the MOM6 ocean model, we're gonna use the OM4 setup. For size 6, we're using 5 thickness categories and mushy thermodynamics. And for the wave model, instead of getting currents from RTOFs, we'll have currents coming in from the MOM6 ocean model. We'll have time-varying ice input. And then also we'll be looking to have feedback from the wave model to the ocean and atmospheric components. Lastly, we of course want to make sure we're improving on those known issues in version 16 for the wave model. So in summary, our goals and scope for V17, we're gonna move towards that coupled model forecast. We've got atmosphere, land, ocean, ice, and waves. We're gonna have JEDI included for our data assimilation for our non-atmospheric components. We're gonna continue to move towards our consolidation of the INSEP production suites, and we're gonna improve on those known issues for version 16. So I have talked really fast to get through a lot of information, and I have left off even more information. So hopefully these slides are available to you so you can go back and read more details about what's going on. And then some of my colleagues will be talking about more details. So Lydia is up next, who's gonna be talking about our high resolution prototypes, which are version 17. Raul is going to talk about global workflow, which is a very important component towards this. And again, you've seen how much of a complex system this is, and we're really excited about version 17. And so with that, I think I actually talked fast enough to have time for questions. So.
We have time for a question? Shout it out.
I am going to actually.
If you can read the question back for those joining us virtually. That would be
Sure.
great.
So the question was about the positive mass flux and if there would be clipping to get to go to zero. Is that a correct assumption? And I'm going to ask our physics chief to ask.
Please use a mic. There's a mic coming your way.
The dicot itself is already positive definite. We had some of the component physics that produce negative tracers. The convection PPL, now we have all this so-called positive definite scheme. So there's no clipping in any of the components anymore.
I think that's all the time we have for questions, so thanks very much, Jessica. Next up is Lydia Stefanova, who will tell us about evaluation of high-resolution prototypes for the next global forecast system, GFS V17. And Lydia's online, I understand? Is that correct?
Correct, yes.
Hi, this is Lydia. Can you hear me and see my screen?
We can hear you.
We don't see your screen, though. If you can try resharing it.
Any better?
There seems to be an issue. We can move on to the next speaker, Lydia, and I can work with you and try to resolve
Okay.
the problem.
Okay.
Okay, we're going to be agile, as they say. So our next speaker is Lisa Bengtson, who is going to tell us about improving the representation of tropical variability and its large-scale teleconnections in the unified forecast system. I'll give you a 2-minute warning.
Can you? Yes. So I would like to start off by acknowledging my collaborators, Juliana Diaz, Maria Gene, who's here, and Kyle Hall at PSL. Let's see, can I?
It's this button right here.
I had to, oh,
And go back.
okay, thank you, sorry. Okay, so in global numerical weather prediction, it's really important to have a good representation of the tropics, not only for the people who live there, but also because of teleconnections impacting the weather at mid-latitudes through, I guess, tropical waves, wave modes acting as Rossby wave source, impacting low pressure systems coming our way. Juliana Diaz and her colleagues at PSL, they did this really nice study where they tried to answer the question how much skill can be gained in mid-latitudes if you have a perfect tropics. So what they did was to nudge the tropics to a perfect state, so a reanalysis, and then they assessed the skill at mid-latitudes in terms of various variables like precipitation and I guess also the state. So they found that there's a 20 to 50% reduction a week 2 to 4 mean average error over the United States precipitation. And in particular, as you can see, that's over the US West Coast. And there's also a week 3 to 4 improvement in California anomaly pattern correlation, which is 2 to 4 times larger. They also try to study in which phase the MJO has to be in order to really see a strong connection to the tropics. So they found that with tropical nudging, the skill of week 3 UFS precipitation predictions over the western US are improved, in particularly when the MJO is active at an initialization time in phases 1 and 5. Challenge with the MJO is, of course, that it depends on a lot of processes that are subgrid in our models, so they're very sensitive to physics parameterizations and coupling and so on. In the last few years, I've been working on 2 developments to enhance a representation of convective organization in the UFS. The first one is to use a stochastic self-organizing cellular automaton to enhance spatial and cross-grid and temporal organization, and I published a series of papers on this work. And the second is to use evolution of convective area fraction for the closure to enhance temporal memory and organization feedbacks. So the GFS version 16, you heard a lot about the work going on and trying to improve upon GFS version 16 for I would like to add to Jessica's list that also in GFS version 16, tropical variability was not very good, and the Mad and Julian oscillation is also not very good, and there's another incentive to have a coupled system and improve upon physics to enhance these processes. So with the prognostic closure, we can see that we enhance the coupling between low-level moisture convergence and precipitation that's shown in this space-time spectra. And there's also some indication that we can improve the propagation and amplitude of the MJO. In this talk, I'm going to focus on the cellular automata work, and I will explain a little bit more about that. So the idea of using cellular automata is really the idea that it exhibits self-organizing properties and birth-death processes that are suitable for modeling organized physical systems. It introduces 3D physics of convection, which is generally modeled using 1D plume models, by allowing the CA to inform on convective initiation in a nearby environment. It allows for stochastic representation of deep convection at the source of uncertainty by addressing statistical fluctuations in cloud number and intensity, and also triggering on the subgrid. And for seasonal and climate predictions, stochastic cumulus convection can be viewed as a noise-induced forcing to modulate larger scale predictors. The cellular automata cumulus convection scheme and the prognostic closure scheme that I mentioned earlier, they have both been included in prototypes of the GFS version 17, GEFS version 13 prototype. The cellular automata went into the prototype 8. And to the left here, you see a snapshot of what the cellular automata looks like in GFS version 17 prototype simulations. It's active on the subgrid. So the CA itself runs on a higher resolution than the NWP model. Here the snapshot is showing when it's coarse-grained back to the NWP grid. And as you can see, its evolution is strongly coupled to where convection occurs. It's a two-way coupled system with the CA conditioned on convective rain evaporation. You could also see that it's limited to the tropics. I set it to 0 away from the tropic with the idea that the time scales of organization are much different in the tropics and the mid-latitudes. We looked at the difference in a couple metrics, and here I show the OLR bias with and without the cellular automata when we have 24 MGO cases from the prototypes. And this figure is from Lydia Stefanova, and we see that there's a reduction in OLR bias over the maritime continent, but we also see a reduction in OLR bias over the western United States, even though the cellular automata scheme is only active over the tropics. So this led us to this study where we would like to understand about improvements in the tropics and its connection to the western United States. And we could do this with a kind of nice, clean study since the CA is only active in this region. So the impact of the CA convective organization scheme is very small, of course, compared to nudging the entire state of the tropics. So we approach this challenge in terms of forecast of opportunity, in that when we have a case that has an active MGO moving across the Indian Ocean and the maritime continent, we see an atmospheric river event off the coast of the western US about 2 to 5 weeks later. So we posed the question, can the CA organization scheme active only over the tropics improve on such a case? So the experiment design, I used the UFS couple prototype version 8, both model tag and workflow tag, and I simply test with and without the CA. So we use all the model components, these are fully coupled runs. And thanks to Bing Fu for initial conditions, so we can run an ensemble. We use 10 ensemble members, and these runs are 35 days long at 25-kilometer resolution. So in the upper left corner, you can see the impact with and without the CA. So without is in yellow and with is in green, and the observations are in black. And this is the Romy plots, so essentially showing amplitude and propagation based on OLR. And when you can see in the ensemble mean precipitation without the CA, this is 5 weeks out now when we initialized, can you see that? Yeah. sorry, we initialized the run when the MGO is in phase 7. And 5 weeks later, we can see some impact in moisture being transported up to the west coast. And when we have the cellular automata, we see some more moisture transport towards the west coast of the United States that also leads to some enhanced precip along the coast, but still kind of weak out over the sea. When we initialize the model, when the MGO is in phase 2, we really noticed that the model struggled propagating and moving the MGO forward. And I think it's really it's really difficult for the system to have a good MGO when you initialize where the MGO has a weak phase, weak amplitude. So in this example, we don't see much impact. So this is now looking at initiated in phase 2 and an ensemble mean over week 3. Okay, I'm gonna move ahead because I got a little warning there from Jim. So when we initialized the model here in phase 3, the impact on ensemble mean week 2 integrated vapor transport and precip is quite neutral. And I think at this point now we're looking only 2 weeks out, and initial condition plays a much larger role. And ensemble mean forecast is pretty good in both these cases, actually. Maybe one thing that distinguishes the two runs is that the run with the stochastic physics tends to have some more variability in the precipitation fields. So I was interested in the case where we have a really good atmospheric river. So I grabbed one ensemble member. This happened to be member 7. And we saw that in comparison to without the CA, the moisture transport up to the west coast is much stronger. And we looked at the precipitation over the tropics and the propagation, and it seems like the cellular automata convective organization scheme, it can organize disturbances and generate eastward propagation far away from its initial state. And then if we plot sort of the phase speed of precipitation as a function of the variance along the phase lines, we can see that precipitation variance is enhanced along the phase speed associated with MGO and Kelvin waves, and the shaded lines here represent ensemble members. Also, just to point out that the precipitation mean state is really quite unchanged, so I think this is encouraging that the enhancement of eastward propagation and organization seen with the CA scheme is not due to a change in the mean state in which the disturbances are embedded in. So just quickly about future plans. One of the main things I want to mention is that we're working on trying to add advection to CA plumes so that we can move whole clusters and maybe have some tighter coupling between the model and the CA itself by allowing to account for advection. So maybe I will just stop there then. Thank you.
Thanks, Lisa. I think if you have questions for Lisa, well, thanks.
Thank you.
Do we have Lydia queued up at this point?
Yes, we do.
Okay, great. So Lydia, again, Lydia Stefanova is going to speak about evaluation of high-resolution prototypes for the next GFS. Take it away, Lydia. Great.
Thanks.
Nice
So I am going to start with first apologizing for the technical difficulties, and second, acknowledge this talk. And let's move to the next slide, please. And all the people that are involved in the GFS development that are on this slide. And next, please. So for today, I'm going to talk about the high resolution prototypes that we've been working on, and specifically the evaluation of them. The one that we've completed so far is the first one, HR1. I'm going to briefly compare it to the version that we're replacing, the GFS version 16, and then to the version that we're headed to, GFS version 17, although I'll do that very briefly because Jessica already talked about that. So I'll spend most of the time talking about the evaluation of this prototype, the targets, and the results. And next slide, please. So just briefly to give you a context for the HR1, our starting point was prototype 8 of the low resolution prototypes that we ran for the last couple of years, going from P1 to P8. We're starting with P8, we branched into targeted development for GFS and for GEFS. And what I'm talking about here is the first high resolution prototype HR1. There are going to be more prototypes until we reach the target point of GFS version 17. The details of the model again are, Jessica talked about them, so I'm just going to describe the runs. They're a set of summer runs starting 3 days apart for the summer of 2020. They run out to 16 days, and similarly for the winter of 2019 to 2020, we have forecast starting every 3 days going out to 16 days. So that's a total of 30 summer, 30 winter forecast. And we also have a hurricane set, which covers the active part of the 2020 season of the North Atlantic. Those are, again, cold start forecasts every day and going out to 7 days. The model is initialized with GFS version 16 atmosphere. It has its own spin up of the land using the land surface model that's in this version. Waves are either spun up with GFS version 16 forcing when they were not available directly from GFS version 16, or interpolated from GFS version 16 when they were available. Ocean and ice are both initialized from replay. Next, please. So a very, very brief comparison between GFS version 16, which is the previous or the current operational, and GFS version 17, which is the future operational. A big difference between version 16 and HR1 is the additional ice and ocean modeling components, which were not part of version 16 at all. It had prescribed ocean and ice. And increased resolution and changes of physics, most notably the Thomson microphysics, although there are a whole lot of other changes as well, and the land surface scheme of NOAA-MP replacing the plain NOAA. What is lacking yet to be version 17 is further necessary upgrades to the physics and changes in the addition of the DA for initialization. Next, please. For evaluation, I'm going to touch on several aspects that we're keeping track of. Those are global distribution of biases, MJO, some AC scores, some parameters for CONA, specifically the 10-meter temperature, 10-meter winds and 2-meter temperatures, and CAPE magnitudes, and then TC track and intensity. As far as evaluation tools, for part of this evaluation, we use non-METPLUS based scripts as we used in the prototype evaluations. And for part, we're moving towards the METPLUS based evaluation using the EMC Verif global package that has been developed previously to translate largely the VSDB evaluation into METPLUS compatible or METPLUS using version. The link to that package is in the GitHub link listed here. Next, please. So here's some look at the global biases for clouds on the top row. Shortwave radiation at the surface coming down, and shortwave upward radiation at the surface at the bottom. The left strip is the bias in version 16, the middle strip is the bias in HR1, and the right strip is HR1 minus version 16. The main features that we see here is generally reduced cloud cover in HR1 compared to version 16. In many places, particularly in high latitudes and around the equator, that's a good thing. In other places, it's a little bit of a deterioration. The biggest problem that HR1 has is the increased cloudiness south of the equator in the Eastern Pacific and Atlantic, which represents a positive bias in the cloudiness, B, a negative bias in the shortwave downward radiation, which, as I'll show in the next slide, has consequences for sea surface temperature. And another shortcoming is the shortwave upward radiation, which is showing a negative bias over deserts and sea ice. Both of these issues are things that are that are being addressed in change through physics changes and parameter changes in HR2. Next slide, please. So this shows the net shortwave radiation bias at the surface, ocean surface, and the SST bias, and it illustrates that the deficit of incoming shortwave radiation in the Southeast Pacific and Atlantic is leading to negative SST bias, which again is something that tuning of Thomson microphysics is going to take care of in high resolution prototype 2. Next slide, please. This is one of the very nice improvements that we see in HR1 compared to version 60 to GFS version 16. This is the MJO, one of the key modes of variability. The top set is the anomaly correlation as a function of lead date, and the bottom two are amplitude error and phase error respectively, for winter on the left and summer on the right. Blue is GFS version 16, red is HR1. The main point is that we are improving MJO quite notably in both seasons, reducing amplitude error and reducing phase error. Next slide, please. This is an anomaly correlation scorecard for winter and summer for select variables showing an improvement. So the green colors show improvement. And we see that in tropics and the winter hemisphere for heights, wind speed, and upper tropospheric temperatures. And we do see some issues. Those are the red triangles pointing down for low level temperatures. Next slide, please. I'll look at 10-meter wind speeds in winter over west and east CONUS. The gray line is the observations, black is version 16, red is HR1. Mean and error. What we see here is that the wind speeds in HR1 are generally lower than GFS version 16, and this is an exacerbation of the underestimation for Western CONUS, but it's a reduction of the overestimation in Eastern CONUS. Next slide, please. 2-meter temperature shown here for West CONUS in summer and winter. For summer, we see reduced daytime warm bias and generally improved diurnal cycle range. The diurnal cycle shape, but reduced diurnal range. And for winter, we see an exacerbation of nighttime cold biases, although still an improved diurnal cycle shape. Next, please.
Yeah, I'm going to give you the 2-minute warning.
Thanks. This is another positive development in HR1. So GFS version 16 has had the concern of overly low CAPE values in summer over CONUS. In HR1, we see an increase of the CAPE value, so increased instability, although these are still not at the magnitude that we want them to be. They're moving in the right direction. And again, HR2 is implementing changes that are further increasing these values. Next, please. This is the last result slide. It's about the track and intensity errors in tropical storm forecasts, tropical cyclone forecasts. Here, the blue line is HR1, black is observations. And it's the main concern here is an underestimation of further deepening of the underestimation of intensity in HR1. This is not surprising given that this is a coupled model, so feedbacks with the sea surface temperature, with the ocean atmosphere interactions do lead to reduced sea surface temperatures, and that lead to decreased intensity. And again, changes are implemented in HR2 to take care of that. Next, please. And finally, this is just a summary that we see a number of benefits of HR1. Most notably, those are the MGO scores and the improved anomaly correlations in the upper troposphere. Some improvement in CONUS biases and increased CAPE, and there are some deficiencies that we are aware of, and most of them are being addressed by HR2. So that's it. Thank you.
Thank you, Lydia. I think we have to move on in the interest of time. Our next speaker is Maria Gaina, who's going to speak about convectively coupled equatorial wave skill in the unified forecast system. I'll give you a 2-minute warning.
Yes, so this is work together with Juliana Diaz and George Calades. And in general, when we're looking at precipitation skill and numerical weather prediction, the mid-latitudes tend to outperform the tropics for the first about 4 days. There's a few reasons for that. One of the main ones is that the underlying dynamics are very different in the tropics and mid-latitudes. And in the tropics, convection is the main driver of precipitation. So we can expect that the convective parameterization has a much larger impact on the precipitation in the tropics. And then, of course, precipitation skill in and of itself is worthy of improvement, but then there's also evidence that better forecast skill in the tropics can lead to improved forecasts in the mid-latitudes at later lead times. So essentially this talk is an advertisement for looking at precipitation and convective variability in the tropics, and not just looking at skill scores and statistical skill scores, but looking at diagnostics and metrics that are based on something more physical. So we know that there are well-known sources of predictability that go beyond a few days in the tropics, such as the MGO and convectively coupled equatorial waves. So what I'm going to show here is we'll look at metrics and diagnostics to better understand convective variability in the tropics and hopefully identify forecast error sources in the tropics that are related to moisture convection coupling, convectively coupled equatorial waves. And then I'm also going to look at several versions of the UFS to show the utility of these diagnostics. So I'm going to show 2 versions of the uncoupled GFS. It's the version 15 that was operational at the time, and parallel runs of the GFS version 16. And the nice thing about these is that they were initialized every 6 hours. And I'm going to look at April through October 2020. And because they're initialized every 6 hours, I can look at these metrics as a function of lead time, which is very, very nice. And these are uncoupled forecasts. And then I'm also going to look at several of the coupled prototypes for the UFS. And to compare to that, I'm going to look at the 2021 EC model version from the S2S database. Looking first is large-scale precipitation. We average precipitation from 5 south to 5 north, and then we can look at these Hofmahler diagrams. And what we see is that early on in the forecast, the models actually match the observations very well. To quantify the agreement, we then compute the pattern correlation as a function of lead time. And what we see is that initially, the model at forecast hour 6 is about, the correlation is about 0.67, and it's higher than the correlation between iMerge and ER5. So what that tells us is that, one, the assimilation and initialization of all these fields that go into producing precipitation in the tropics is actually doing very well and is comparable or even better than in the reanalysis. But it also tells us that at forecast hour 6, we're already down to a correlation of 0.67, which is fairly low. So we're losing a lot of potential skill in the first 6 hours of the forecast. Looking at this in the UFS along a forecast now, and this is for a dynamo period, 30 days in 2011 that has an MJO event, we can see that there's a lot of variability between ensemble members and between models, where some of the models and ensemble members actually show some enhanced convection during this observed MJO event, and others don't show anything like that. And again, we can quantify this with a pattern correlation, and I'm not going to show that right here, but it's very similar to the uncoupled models. Now I want to look at the actual scales where convection couples to the dynamics, and the scales where observed precipitation and model precipitation vary coherently. So higher values mean at those scales, there's a zonal wave number by frequency. At those scales, the model precip and the observed precip vary coherently, or on the right-hand side, the model precip and the model low-level divergence vary coherently. So this can tell us something about how well do the models initialize and propagate convectively coupled equatorial waves. And it can also show us these scales without having to remove the background spectrum. And it makes it possible to evaluate the strength of this coupling relationship between precipitation and dynamics and how it changes with lead time. So first, looking at the coherence between observed precip and model precip, we see that higher values are at low frequencies and larger spatial scales and along the dispersion curves of the theoretical dispersion curves of convectively coupled equatorial waves. And then we see that this level of coherence actually decreases very quickly with lead time. So, and what this means is that either the model is not able to initialize convectively coupled equatorial waves at later lead times, or it might be propagating those at the wrong speed. So, and I'm going to show in the next slide that it's probably the first that's the case here. So this is looking at precipitation and convergence or divergence at 850, so low-level convergence. And again, these peak at along dispersion curves, and also it's the coupling, first of all, at 6-hour lead time is weaker than observations, and it decreases with lead time. So what we can see here is that while the model is able to capture this coupling at initial time, it loses the strength of the coupling very quickly with lead time. And then I wanted to show an example of how you could use this during a model development. And this is for the UFS prototypes now. We can see, first of all, that the UC model has a band of coherence for the convectively coupled Kelvin wave that's too narrow and probably propagating a little fast compared to observations. In the prototype 5, the coupling was too weak, which then as you go to prototype 7 in the center, you get a little bit of stronger coupling, and moving on to prototype 8, you get even more coupling, and you get some more dispersion, which is compares well with the observations. The last metric I want to look at is based on spatial EOF patterns of observed precipitation for these different convectively coupled equatorial waves. And essentially what you do is you take your model precip, you project it onto those spatial patterns, and you get an activity index for that particular wave, which you can then correlate with the verification precip that was also projected onto these spatial EOFs. And what you see is that this is, again, for the uncoupled models. GFS version 16 was slightly better than GFS version 15. And in this particular metric that's based just on precipitation, the GFS was able to propagate or forecast the MJO for about 5 days on average in this particular precipitation-based metric. Looking at this in the coupled UFS prototypes, results are similar. It's a lot more noisy because there's a much smaller sample size here. The one notable difference here is that the equatorial Rossby wave scale is retained for longer in these coupled runs, but that's not the case for the Kelvin, MRG, or the MJO. Comparing the UFS coupled prototypes to the EC model, in general, they have comparable skill, which is, I guess, good for the UFS. For the Kelvin wave, the skill still drops below the 0.5 correlation level within the first day. So there's not It's comparable to the EC, but it's not a lot of usable skill very long into the forecast. Looking at equatorial Rossby waves and the MJO, again, it's comparable to the EC. Do I have the, yes, on the right is the EC. The MJO in the coupled UFS in this particular metric actually looks a lot better than in the EC. And we need to do a little bit more work and look into why this is the case. If this just happens to be sampling, or if this actually is something usable in the UFS. So to summarize, I'm encouraging everybody to look at skill metrics that are more than just statistical skill scores for tropical variability. Thanks. Much of the precipitation skill in the tropics is already lost in the first 6 hours following initialization. The coupling between convection and the circulation is improved in the UFS coupled prototypes, but it also still decreases rapidly with lead time. And what I didn't show is that I only showed the lower levels. It's worse at the upper levels. So somehow that connection from the surface through the convection to the outflow at about 200 hectopascal is also still missing in the UFS. In a precipitation-based metric, the UFS coupled prototypes actually show skill at longer lead times for equatorial Rossby waves and the MJO. And then we're looking further into why the UFS seems to show better MJO skill in this metric than the EC. There is a Python GitHub repository for these diagnostics and many more that is available for anybody to use. And then several of these diagnostics were also included in last year's release of MetPlotPy and MetCalcPy of MetPlus. And that's it. Thank you.
Thank you. We have time for a quick question. Yes, Lisa?
Nice talk. It's fascinating about the MGO. Curious, is that the exact same cases and exact same lead times, and is it an apples to apples comparison?
Make it as close as possible, but the EC is only initialized every Monday and Thursday of the week, so twice a week, and then the UFS prototypes were initialized on the 1st and 15th of every month.
Okay.
So I took the cases from the EC that were within 1 to 2 days of the UFS initialization, so there is a little bit of a, variability there. Like, is it actually picking up the same phase or amplitude of the MJO at initialization?
Operational.
No, this is from the S2S database. This is the 2021 model version, and the current one is the 2022.
All right,
Yeah.
thank you.
Thanks, Maria. Next speaker is Ben Cash, who's going to tell us about wintertime diabetic heating biases in prototype 8. And I'll give you a 2-minute warning.
That seems to be straightforward. Thanks, everybody. I made a little bit of a change to the title. Is there a... Nope. All right. We're looking at... This is definitely a preliminary analysis. This is in progress. I'd like to acknowledge my collaborators on this, David Strauss, Eric Swenson, Julsu, and myself, and also certainly grateful acknowledgement of the support we've gotten from NOAA. So why diabetic heating? Why are we looking at this at all? Particularly in the context of subseasonal to seasonal, predictability is largely due to the influence of slowly varying boundary conditions. We've heard some of that today. And so also features like MJO, soil moisture anomalies, et cetera. And the direct influence of these anomalies that we're hoping to harvest predictability from is pretty limited in terms of the atmosphere and pretty local. So their remote influence, say from ENSO to somewhere where people live, where we might be more interested, is communicated via the atmosphere through things like teleconnections, which we heard about earlier today. And those are driven largely by diabetic heating anomalies. One of the problems is that diabetic heating is very difficult to observe directly, particularly if we're looking at the three-dimensional structure. There are satellite measurements, things like condensation, but in general, there are very large observational uncertainties in looking at what's a pretty critical piece of the puzzle. However, you can try to estimate the three-dimensional field using thermodynamics and with modern reanalysis products. So this is something that David Strauss has been working on for quite a while. You can use the potential temperature equation to evaluate these terms over here and get an estimate of Q. And you can do this every 6 hours, three-dimensional, to get a pretty high resolution, temporal resolution estimate of diabatic heating.
Ben, sorry, I'm back here. Could you just keep speaking into the mic and not turn around? And if you can use the laser pointer on the screen in front of you, and it'll display up on the big screen as well.
I don't see it there. All right, I'll look this way.
Thanks.
So what we're going to do is we're going to estimate monthly mean diabatic heating from the January starts of the prototype 8 data. This is data that we obtained, downloaded from Amazon. I have to take a moment to talk about what an incredibly valuable resource that is and how fabulous it is that the data is out where it can be easily accessed and you can do an analysis on it. There's always more data than you have eyeballs. So putting it out there where we could get it down and play with it, it really enables a lot of science without having to have the resources to do your own runs. And we're going to compare the diabatic heating we diagnosed from the prototype 8 data to ERA-5 using exactly the same procedure. The heating's integrated over a number of vertical layers as shown here. All results I'm going to show are in units of watts per meter squared. So what do we get? So on the top, I'm going to turn away again, but the top on your left is the lowest level, so 1,000 to 925 for ERA-5, and then on the bottom is what we got from prototype 8. And just sort of by an eyeball test, you can see they look pretty similar. And the comparison is on the right, and there certainly are places where they're different, but by and large, it's, I would say, almost surprisingly good comparison between the two. So that was encouraging, that the model in this critical feature is not doing a really bad job. And then I'm just going to step through the layers. I'm not going to dwell on the details of each one of these, particularly in the interest of time, but ERA-5 is on the top, so you have the 925 to 850 and 850 to 750. ERA-5, UFS on the bottom, and again, without doing a difference each time, just as an eyeball test, you can see that they're actually pretty similar, and you see the sort of features that you would expect if you were looking at a heating field. Continuing onward, you can see the patterns are changing as we go up in levels, but again, they're still matching up pretty well. Going up again, and we're seeing more concentration over the maritime continent, but again, the model is really holding up surprisingly well as we go through this. All right. But it wouldn't be an interesting talk if I got all the way to the top and told you that it did a great job all the way. We didn't find out anything interesting other than, hey, good job on diabatic heating. As we get to higher levels, now we can start to see, particularly over the Pacific storm track in the 350 to 200 range, we're starting to see differences emerge. And then for 200 to 50, now we have a pretty clean miss where ERA-5 is showing heating, mostly concentrated in the tropics, and the UFS is not picking that up at all really and still has very strong cooling over, particularly over the Pacific storm tracks. So what's going on here? Well, we can try to answer this question a little bit because we're diagnosing this from an equation, which we can then break down into its individual components. So what I'm showing here is just the contribution to diabatic heating from the horizontal advection. And again, we can see the differences are not very large. So it's not coming from here. It's not because the model is incorrectly advecting potential temperature. That should give us a clue as to what's coming up on the next slide, which is if we look at the vertical component, and this is pretty much where it's all coming from. Again, the patterns are not grossly different, but when you take that difference, you can see the error in the Pacific Storm Tract region in particular really jumps out. So this is where that difference is coming from primarily. So what does that tell us and what did we do? I managed to get all the way through this without Jim flashing a number at me, so I could take a little bit of time on the conclusions. So we've diagnosed the diabatic heating, and we found that for the most part, prototype 8 very closely matches error 5. It's really doing a pretty good job until you get to these upper levels where we find it's significantly too negative in the northern hemisphere over the storm track regions. Oh, there we go. I'm going to take the somewhat unusual step of disputing my own conclusion slide on this next bullet, where we say that the time vertical advection term is responsible for this difference. I have not actually shown that. What I've shown is that there is a big difference in the vertical term, but it could just as easily be that there's an error coming out of the diabatic heating coming from the parameterizations, and what we're seeing in this very large difference in the vertical advection term is the response to that. And by looking at the analysis in this way, we can't actually disentangle that. We're going to have to dig more into the details in the model to determine which of those it might be. And that is some of the ongoing work. So we're doing some further decomposition of the vertical term, particularly looking at contributions from eddies. That requires longer runs than the prototype runs because you need to be able to do some temporal filtering. Fortunately, as part of the project, we are making seasonal scale runs, so that analysis is underway. We've also saved off the individual tendency terms from the model so that we can directly assess what is the tendency from the individual physics components. And that will hopefully also give us some information on where this term is coming from and a little bit of help us with the chicken and egg problem. And we're also, we're going to look and see how much it matters by doing some work to correct some of these biases that we did identify and see if that improves the forecast scale. So that's all I have. Thank you for your time.
Thanks, Ben. We do have time for one question.
Thanks for an interesting talk. Oh, sorry.
Yeah, he was first. You got to be quick.
I'm interested in the connection with Maria's talk here and in terms of the tropics and the lack of connection or coupling between convection in the tropics and the upper level dynamical fields. And in this case, the lack of diabatic heating at upper levels. Is it like one physical interpretation of this is deep convective heating just not reaching deep enough in the UFS? And I mean, I guess to tie this back to Maria's talk again, as far as tropical sources of predictability, that doesn't really bode very well if we're not getting sufficient divergence at upper levels.
So that is something that I think will be easier to answer in some of the going forward work that I just mentioned, where because we do have these longer runs where we have the specific temperature tendency terms from the physics parameterizations saved off. And so then we can really dig into the model. First, we can compare and make sure that the residual method actually lines up pretty well with what the model thinks the diabatic heating is. But then we can also look and see which individual components are contributing most and see maybe which ones are out of whack. So I think that's easy. It will be easier to answer the next time I give this talk.
Like a great resource. Thank you.
Great. Thank you. Our next speaker is Guo Yuan Lien, who's going to speak about the operational use and local development of UFS MRW GSI at the Central Weather Bureau in Taiwan. I assume this is an online presentation?
Yes.
So I'll give you a 2-minute warning when there's 2 minutes left.
Okay, thank you. So this work was done by many of my colleagues at Central Weather Bureau of Taiwan, and also with help and including Darrell funding and the VJ. So CWB has a long history of developing and maintaining an operational NWP systems. So on the top, this timeline shows the several major changes of the CWB's global NWP system over the past 20 years. And in recent years, in collaboration with NCEP EMC, CWB has decided to adapt the result of the NOAA NGGPS or the NCEP JFS starting from version 15 as our new operational global NWP systems. So here, this short list the progress in recent years. Note that starting from 2021, we were able to start running semi-operational near real-time run of this system. And in the last year, we ported this system to our new HPC, which is in ARM architecture by Fujitsu company. And finally, in this year, we will make this system in operation officially. And we would like to call it Taiwan Global Forecast System, TGFS. So this is the grid configuration of the TGFS version 1. So for the deterministic system, we run it at C384 resolution. And for the YANCAP system, we run it at the 192 resolution, both of which are just half of the operational resolution of NCEP GFS. And also you can see that we rotate the tile configuration to let one of the tile be centered at Taiwan. And also we enable this regional tile in the area near Taiwan at a resolution of about 5 kilometers. And this regional tile is run simultaneously with the global model using the unnested capability originated from the GFDL FVGFS. So our TGFS version 1 is largely based on the NCEP GFS version 15.1, but we also do some local development trying to further improve the system. So this table shows the main differences between the TGFS version 1 and the NCEP GFS version 15.1. So we changed the grid setting and also resolution, as I mentioned. And in the model part, we modified the cumulus parameterization scheme and also the land model. And also in the data assimilation part, we interfaced the GSI with our real-time operational real-time observation data stream CWB for the conventional data. And for the satellite data, we mainly relied on the buffer data openly available on NOAA NOMADS, but we also added some self-processed satellite data sources, including the Cosmic 2R data and the Himari 8 and 9 data. So based on these differences, we listed 3 main inferiorities of the TGFS compared to NCEP GFS, which include lower resolution and few ensemble members and few observation simulated. So with these differences in mind, then we show this forecast verification in our semi-operational near real-time run. So this is the first year of this semi-operational run. So in the first year, 2021, we see that in the traditional mid-level height ACC score, it's considerably worse than the NCEP operational GFS. And the score is just comparable to our old operational CWB GFS system. And also on the right, it shows the scorecard comparing the TGFS versus our current operational CWB GFS. this is kind of a neutral impact, neutral differences. And in the next year, we improve our forecast skill significantly. So we see that the forecast skill become more close to the NCEP operational GFS and become significantly better than our current operational CWGFS. So we become confident that this system can be used as our next version operational system, replacing the CWGFS. And yeah, on red, it also shows it's overall it's better than the CWGFS. And in the first half of this year, we further improve our skill a little bit. And we are very happy to see that in this ACC score in the Northern Hemisphere, it's quite close to the NCEP operational GFS, even with health resolution. Although we know that this ACC score, it's just large scale patterns, it doesn't mean everything, but I think we're still happy with this. And this slide shows the precipitation forecast verification of our Taiwan nested tile. And we compare this score with our CWB's WRF-based operational regional NWP system, which has been developed at CWB for about 15 years. And in short, for the precipitation forecast on the day 1 and the day 2, this score is worse than the WRF-based operational system, but they are comparable after day 3. And from here, I'm going to show some improvement of this CGFS on top of the NCEP GFS version 15, but just very briefly. So this slide shows the improvement of the new SAS cumulus scheme. We did this work mainly based on the study by Kwong and Hong in 2019 in their Korean system. And this improvement successfully improved not only the synaptic forecast skill, but also the structure of the frontal systems. And this shows the improvement of the land processes. Here, the main thing is simply we update the surface static data, including the land use and soil type and the vegetation fraction data with much newer and higher resolution one compared to the GFS default fixed data. And we also modified the land model process slightly. And this change also led to a very good improvement. And this slide shows the improvement of the GNSSR observation error specification in the GSI data assimilation, which also improved some skill score, especially in the tropic. But I think I will skip the detail here. So this slide shows, so as I said, our TGFS version 1 is developed based on the GFS version 15. But after that, we know that there have been huge amount of the developer work in GFS version 16 and also in wide UFS communities. It's actually quite difficult for us to follow this big amount of new changes frequently. But we hope that we will try our best to incorporate the new changes and to let the best version of the CWBT GFS just behind the NCEP GFS by about one big version in principle in the future. So here are summaries. CWB has adapted the NCEP GFS version 15 as our new operational global NWP systems. And since this model component of the system has later become part of the UFS MRW applications, the CWB may be regarded as one of the UFS and NRW's early adapter. And we thank the UFS project to make many UFS-related tools to be very transparent and portable and well documented. But I would say that despite of this, to build the entire operational workflow of a system in the environment outside no one computer is still not a trivial task due to the complicated nature of the operational systems. However, we worked based on mainly the EMC's original operational code, and we admitted that we did not watch closely to the UFS community releases. So maybe that's our problem. And we also try to, based on this system, we try to collaborate with some Taiwanese universities and research institutes. So this may help to expand the community as well. And finally, I would like to say that we greatly thank the UFS project and the efforts spent by many people to provide these great tools that allow us to build and use a state-of-the-art NW system at STWB. Thank you.
Thank you. Is there a quick question for Guo Yuan? Okay, thank you very much. We'll go on to our last speaker for this session is Yuejian Zhu, who is going to tell us about introducing the next global ensemble forecast system for weather, subseasonal, and monthly. I'll give you a 2-minute warning.
Okay. Good morning, everyone. Yeah. I'm not sure I'm gonna get the right, the audience over here because my talk originally arranged the Friday morning and I already booked the return flights on Friday, so change it to today. Hopefully, people understand what I'm talking about. Okay. So anyway, I'm talking about the global ensembles. Yeah. The expansion from GFS. You heard of the lots of the GFS setting. Just additional the ensemble system, and also the future. I hope everyone heard of that. June 27, European Center is already no deterministic. The first time, another achieved milestone, okay? They are running 51 members, 9 kilometers. That's the second milestone European Center already achieved it last month, okay? They are, from that day, they don't have any deterministic. If you want to deterministic, just ensemble control. That's 9 kilometers. Be careful, we are much behind than, So ensemble next one is the 25 kilometers still seminar solution. Okay, anyway, talking about ensemble, I only have 12 minutes, okay? I have Korea, the Binfu here, Hongguan here, and Near here, Fair here, Aperture, and the funding, the many courses are over here. I'm talking two parts. One is quick review the GAPS version 12. It's kind of operational. Why I do that one? Because that is one for the GAPS 13 to compare to. We have stakeholders, 7 NSAP centers and all the regions. They are evaluate our system to qualify, upgrade, make that happy. They want to compare the current operational, okay? Last implementation, I will give you the little bit of background. This table compare current operational is the version, let me see the high. Yeah, this is the version 12, it's kind of operational. Compared to the version 11, a lot of changes, okay? I just give you highlights. The first one is the FO3 dynamics, okay? The first one. Second one, model resolution from 32 kilometers to 25 kilometers. And the third one, we extend to the subseasonal, 35 days from 16 days, okay? And we introduce the field over here, the SPPT and the SCAP. Is for model stochastic. And also we have the 30 years, the reanalysis and the reforecast to support this system. So this is a very good system. You will see this is the pattern, SPPT pattern. I'll just give you one, I not posted the SCAP. The SCAP is a more dynamic, stochastic, and this is a physical tendency stochastics, okay? So you give you highlight here, the version 11, we have a stochastic called STTP, the stochastic total tendency perturbation. We still is over-dissipating, under-dissipating most of the globally. And after we introduce the SPPT and the SCAP, see, it's very good. I mean, right now, I don't hear 2 or 3 years, I don't hear too much complaint from our users for the new system. And accomplishment, of course, a lot of accomplishment from weather and week 2, week 3, week 4. Also, we have wave. It's one way, the force in the waves, okay, no feedback. And also only run one members is separately 32 members running out to 5 days. It's no the interactions. And the ensemble running 31 members, 30 perturber and 31 unperturbed, and 31 reforecast, okay? So, I'll give you a couple of highlights. That time we evaluate. This is a CIPS score. It's a major ensemble predictability, the probability forecast, okay? So the 5 days on the top and the 10 days on the bottom. So red is the new one, and the black one is the older one. We are all the way significantly better. We test that, it's significantly better. User like that one. All the score from south, northern hemisphere, southern hemisphere, both of them. This is the one. Moreover, you look at the precipitation. This is from different categories, different lead times, and this reliability is much improved, red and black compared to. And the WPC and the Service Center like that one improvement, okay? So that's give us a pressure for next one, okay? They will compare. This one still on deck, all the results on deck, okay? So MGO, we are usually the 16 days, MGO is for uncoupling system is very poor, okay? Usually 14, 15 days, the MGO scale, if we say the 50%, but the new one is already reached the 23 days, more consistently. So I'll give you an example over here. People familiar with this one is MGO publication. Use a longer record, okay? To see that one, the left is a observation analysis, OAR and zone F50, okay? And the right one is the forecast for leading 30 days. You see the publication, eastward. It's pretty good, okay? Let's just give you a quick examples. And we have a set of reference. People can look at that one. Why I talk about that one? Because we still have a 30-year reforecast publicly. I know many of you in the community and a student, you can to study that one. It gives you a lot of the interesting the stuff. You can see that one. And I'll move to the next one. I think people are more interested in the next one, right? Because I saw many people talking about the next gaps of version 13. We also list the tables. A lot of changes. I think you heard that one. Jessica already listed the bunch of them. I don't want, that is GFS, okay? For ensembles, I will give you some highlights. This is the kind of operation, okay, version 12. This is the next one. We're not following our system, just to give you expectation, okay? I give you some highlights. A lot of change in physics. You know that one. Physical changes, the turn off the physical changes. I may highlight some, for example, is the microphysics from GFD microphysics to Thomson microphysics. That is a big change also. And others, say I'm highlighting unified wave dragon and the DKE boundary PBL scheme and also the SAS also upgrade, okay? So I give you some vertical resolution. We are not changing horizontal relation, but we are increasing vertical resolution from 64 level to double them to match with the GFS. The vertical resolution increased, and ocean and CIS model is new. This is new coupling. We don't have that one. Last model, we use a 2-tier SST. Use the CFS predict ST as the bias correction as the boundary forcing. So that's why good 23 days of MGOs, that's benefit from that one. And we are the random model is highlighted over here. No IMP, replace the original one. And the new ocean CIS wave is a 2-way coupling, and the aerosol still on the way to test that. Okay, I don't know what is the result look like. We are not start testing yet. Okay, and the second one is supported. I don't think that you are more interested in that one. I'll give you a couple of highlights. We plan to extend the 35-day forecast to 48-day. Why do that one? Because that solves the CPC, support the CPC for the monthly forecast, not only the week 3, week 4. Monthly forecast need more lead time to support the 1 month forecast. So 48 days, probably we can handle that one. And model-weighted resolution, so data is more because we increase the model-weighted resolution. And the ocean CIs, we have a new product, of course. We plan to produce the 30-year reforecast based on the replay analysis, not our own analysis. Use the EI5 and the European, a couple of the ocean analysis to replay, to generate the analysis, allow us to run the reforecast. Still the 11 members in January, but we run in the extent for reforecast twice per week. Before we run it once per week, okay? Expectations. I'm listed over here. The benefit from a company, because we are computing cost is the 5 to 6 factors, of course. We introduce the coupling, and also for the improvement of property with the forecast include PKOPM, to-mean temperature, and the tropic cyclone, and also improve the MJO predictions. Include the propagation intensity and the scale. So we try to understand the benefit or improvement from a two-way coupling, the waves also. That's always the one-way coupling before, but the two-way coupling now. And the new products is another expectations and a 30-year reforecast, okay? And give you a couple of the results. This is the one already published January, the JGR atmosphere, okay? And also this paper, selected okay, yeah, called the highlights. That is how many, 5% or whatever, is a highlight of US. You may saw that one. We already published it for the new, the UFS, the ensemble system. Okay, I'll give you a couple of the highlights over here. One is this is an experiment based on the prototype 5, yeah, P5. We're running the called EP1, ensemble prototype 1, first one. So you see all the way is the normal correlation. The black way is operational, and the red is low resolution, and the green is the high resolution. Northern hemisphere, southern hemisphere, PNA, and the tropical, and the lead time is week 1, week 2, week 3, 4, and a monthly. You will see all the way we get better, and also we highlight some is significant better. We have a star over here. Maybe you cannot see this very small star. Okay. Second one, ensemble we more care about the uncertainty. We are tuning uncertainty. We saw the operation over here for some summer months and the winter months. We saw the tropical over dispersion a little bit, but we are out tuning. We get much better from high resolution, low resolution. Okay. And particularly the interest in the users point us is outline for the kind of operation over here for this domain is a atmosphere river region. It's very important for corners. Okay, our latest experience showed very better result to solve that one. MGO we consistently to get about 26, 27 days. Latest one, please to attend the Bean Food talk on the Friday. We showed that one more details. The latest one showed the 26, 27 days. That's very exciting, okay? And summary, I have a summary, okay? The GAPS version 12 implementation is 2020. It's 3 years ago, okay? It's already 3 years. And 13 configuration, I don't want to read that one. You know that is a 25 kilometers all the way to the 35, the 48 days, and the 4 coupling, the ocean, sea ice, wave, and aerosol. Land already included, okay? And expectation from GAPS version 13, the benefit from the 4 coupling, the GFS, improve the property with the forecast MGOs, new ocean and sea ice products. Definitely people so exciting of that, and the 30-year replay, reforecast. And timeline, I'm just over here. This maybe not the final. I'm just based on my information is the flowing out system around the end of this year, start from January of next year. We start run the reforecast. This time we must flow in our system to run reforecast in order to implement by the Q1 26. And a couple of references. We already published a couple of them, in the review papers for the new GAPS version 30. Let's start over here. Thank you again. Great.
Thank you very much. Do I turn it back to you, Alekia? Yeah, so.
All right, thank you so much for all those wonderful presentations. We'll now be taking a break for the next 30 minutes until 11, and we'll be returning here in the next 30 minutes to continue the session. So thank you so much, and we'll see you all in 30 minutes. This is just a reminder that the sessions will be continuing in a couple of minutes. It is now 11 a.m. We'll just wait a couple more minutes for people to trickle back into the room to begin our sessions.
Here, so that means
I'm monitoring another session from 12 to 1, so it's in a different room.
All right, hi everyone, welcome back. We will continue the parallel sessions with updates on and challenges of the UFS applications, and I will now pass it back to Jim Kinter to continue introducing the sessions. Thank you so much.
thanks, Alekia. Our next speaker, we have two speakers in this session before we switch over to Q&A. So our first speaker is Rahul Mahajan, who's going to tell us about demystifying NCEP's global workflow. Rahul.
My name is Rahul Mahajan, and I'm going to talk about NCEP's global workflow that has been used to power the global applications that we heard about this morning from Jessica Meichner, Lisa Bengston, and Lydia, who have used the data to generate, who have used the global workflow to generate the data for P8, and some follow-on talks that followed that used the P8 data set. The list of contributors for the global workflow is long. It's not just the workflow team. It's also scientists from across EMC and PSL and other parts that contribute to developing the capabilities of the global workflow. So just to lay the layout of the land, the global workflow here is built to support the applications of the global applications ranging from the GFS, the global forecast system that Jessica mentioned, the GEFS that Eugene mentioned, the GDAS, the data assimilation system, as well as the GODAS, which is kind of loosely tied to the global workflow. It doesn't really exercise the GODAS application. And where we're headed in the next few years is towards a fully integrated global application for V18 GFS, V14 of the GEFS, and a seasonal forecast system of the V1. So all the green bars will converge and be exercised through the capabilities of the global workflow. So what is the global workflow? The global workflow is essentially a series of sequences of boxes that tie from pre-processing, data assimilation, numerical weather forecast, the model, post-processing, validation, data and archival and dissemination. All of these are driven by an application configuration in the purple box, and they are driven or automated through a workflow engine. In operations, the workflow engine is used as EasyFlow, whereas for research purposes, we use something called as Rocodo that was developed out of GSL. The global workflow is fully automated with minimal user intervention for execution, meaning once you set up the experiment and let it go, it will continue till the end date has been reached, or there has been failures in the experimentation, in the execution of the steps. The workflow also ensures each step is run at the correct time in operations, or when the data is passed between the different steps of the workflow. So just to lay out what the global workflow superstructure with all the components and its details, you get a directory structure with model components, with the built-in model in the source code, in the source directory with the model code in here. We have the GDAS app, which is where all the JEDI data assimilation executables and configurations are stored. The GSI ENKF, which is where the data assimilation music for the atmosphere using the GSI and the ENKF is stored, and all the auxiliary utilities and codes that go in support of this end-to-end system. The system consists of jobs that drive the system. There are driver scripts or OOSH utility scripts that are used to perform the actions. There's a workflow directory that configures and sets up the different applications that the application requires, as well as configurations which are stored in this PORM directory and module files that are machine-specific execution. All in all, the workflow the global workflow is a collection of 10 plus repositories, builds with it some 53 executables plus unknown number of JEDI ones, which are coming in as the JEDI development is being added to the workflow. It has about 369 scripts that drive the system with 67 jobs. So it's fairly involved infrastructure that orchestrates the development and the execution of applications within for global applications. In a nutshell, to set up an experiment, you basically clone your global workflow and run a sequence of steps. Where you check out is basically will collect all the ingredients, if you will, of the global application from the model, the data assimilation, et cetera, et cetera. It will do a build of all of those, so based on what you want to build. And link is essentially going to place all the required artifacts in the right spaces so that when the workflow starts executing, it's going to be able to find the executables, the fixed directories, the PARM files, the configurations, and so on and so forth. So that is a one-step process. The second step is the workflow, where we create the experiment. And this can be repeated for any number of times based on what the user wants to configure an experiment X for. So setup expd.py is a user interface for the user that will query the user for what kind of experiment you want to set up. You can set up a GFS or a GEFS experiment. You can set up a cycled or a forecast-only experiment. You can set up one with ensembles or one without ensembles. So it will set up an experiment directory with configuration files that the user can then customize to their heart's content and generate the XML. The XML is basically the recipe of orchestrating the jobs in the sequence of the workflow. And once the experiment directory has been configured, you launch the experiment using Rokoto run, which is what submits the jobs to the queue, and you let go. It will keep cycling until it reaches the end of the experiment, or there has been an error in it. So the yellow boxes signify the global workflow repository or the source code are components of the global workflow, and the green is a user experiment. So this workflow is portable on a handful of machines. First of all, it's portable on the NOAA's operational supercomputer, the WCOS2. It's also runnable out of the box on Hera and Orion, which are NOAA's RDHPCS. It's also runnable, last we checked, on JET, which is a NOAA RDHPCS machine, as well as the University of Wisconsin SSEC S4. These were efforts contributed to the global workflow by Dave Huber, who is now at EPIC. The system also runs on NOAA's ParallelWorks AWS for a forecast only. I'll explain what forecast only means. Essentially means that you can set up an experiment to run forecasts from set up initial conditions to a forecast length, whatever the user desires. Port to Hercules is coming soon. The global workflow's operability supports applications such as the GFS and GEFS, as Jessica mentioned for the GFS and Eugen mentioned for the GEFS. SFS capabilities are being developed as we start to ramp up that project. The modes for operability, we are supporting forecast only, which what that means is if you have set of initial conditions, you can run a set of forecast length forecasts and post-process those to produce GRIP files or output that can be then evaluated by scientists. Or you can have a cycle system where you have a set of initial conditions and you do cycling data assimilation as you go by from cycle to cycle. The reanalysis and reforecast capabilities will also be developed as part of the SFS development. Currently, the following model configurations are supported in the global workflow. Atmosphere only, atmosphere plus aerosols, that's what the ATM and ATM-A are. ATM-W is a desire. It currently doesn't work, but it will be enabled soon enough. S2S, the fully coupled system with and without waves and aerosols, is also functional within the global workflow. This system is also used by DA development for both component data assimilation as well as weakly coupled data assimilation. The data assimilation systems that the global workflow currently supports is for the atmosphere is the GSI-based, ranges from 3D VAR all the way to hybrid 4D ENVAR. From the JEDI-based, which supports currently 3D VAR and the ENKF, but not the hybrid, work is underway to do that. It supports JEDI-based 3D VAR for aerosols, JEDI-based ocean and ice using SOCA, which is also a JEDI system, as well as land assimilation using for snow DA using the LTKF-OI capability that was developed in conjunction with PSL in the JEDI system. As far as modularity of the workflow is concerned, it is able to run any component of the workflow as a standalone job. It's not a turnkey in the way that people would like to have it, but a super user could pull out the global workflow and run any component of the job any component of the workflow as a standalone job. For example, observation pre-processing or post-processing and product generation. The machine-specific components of the workflow are abstracted to a single directory. So if you want to port this to a new machine, you could collect all the requirements into the single directory and begin your portability experiment, portability exercise. What this affords is flexibility to combine to create combinations of DA and components for weakly coupled DA applications. So we have a range of applications currently being run with cycle DA with and without different components. For example, we have atmosphere cycling experiment with a coupled model. We also have weakly coupled DA with other components. And the most important thing is there's refactoring of older tasks that are going on and addition of new tasks to follow following a hierarchical design based on object-oriented programming and breaking down of tasks for efficient use of resources. As far as testing goes, we have unit testing using PyTest for Python. We also have end-to-end testing that is enabled through GitHub Actions. You can see as soon as a PR is opened, you can see an experiment is triggered on Hera and Orion for a various set of configurations, and we can evaluate. The users are able to see the results of their pull requests online as soon as the PR is opened. We have code coverage. Make sure that we are putting in testing and code and covering parts of the code that are new and being added every day. We also have documentation for the global workflow. It's a work in progress, but we have we host documentation to the global workflow on RTD, as well as any utilities and common tool sets like WXFlow that we are building as a library of common tools for workflows is also available online. And here are a few slides that I want to add just to highlight the contributions from our partners or users and developers in the global workflow for enabling different applications. So this is a slide from OceanDA, which the next few slides have been shown in other talks, so I'm just going to speak what their capabilities are. This is OceanDA by Guillaume Vernier at EMC, shows a weakly coupled cycle data simulation system in the global workflow, showing the improvements of having a coupled model and a coupled DA in this for ocean observations. Similarly, for CIs, shows a better CIs extend in the weakly coupled DA prototype. Corey Martin at EMC has done enabled capability for aerosol DA using JEDI in the global workflow. Similarly, Jairi Dong from EMC and Clara Draper from PSL have enabled snow DA capability in the global workflow that allows expansion and running of the land simulation that has been released as part of EPIC's program. What I haven't highlighted here is the atmosphere DA JEDI system, but that also has been developed in the global workflow, which enables or allows the science teams to accurately compare the GSI-based assimilation system with the JEDI-based assimilation system in the same workflow and same infrastructure as can be evaluated for operations. So just to summarize, the global workflow serves as multiple needs for applications and has been developed as part of the operational upgrades. There's a lot of progress being made towards modernization of the code base, as well as making sure the system keeps running towards reaching operational milestones. Automate testing, I will not say more than that. We have engagement from the science development teams in developing these capabilities, as these slides showed, towards planning core capabilities in the workflow. And the last bullet is the one that I want to make more emphasis on, is there's a lot more work needed to make the system more agile, extensible, configurable, portable, all the while maintaining reproducibility and operational readiness. And I'll take questions now or later.
I don't think we have time.
Sounds good. Thank you.
Great. We do have time for questions coming up after our next speaker, who is Austin Coleman, who's going to tell us about better use of ensembles and operations through clustering and ensemble sensitivity analysis. Come on in. I'll give you a 2-minute warning.
Oh, yeah, thanks. Thank you. Relatively new at Series at WPC, working as a contractor through Series. And today I'll be talking about a better use of ensembles and operations through a couple of very quick and easy post-processing tools. This is very much a group effort, so I'd like to thank my collaborators, Brian Colley, Jim Nelson, and Travis Wilson, along with my predecessor in this role, Bill Lamberson, for laying a lot of the groundwork here. Let's see. There we go. Okay, so to briefly motivate this, as I'm sure a lot of you are aware, the National Blend of Models, or the NBM, is often used as a first guess for National Weather Service forecasts. This is great because it blends a large amount of forecast data, but forecasters often see it as a black box and desire more information about what goes into the NBM, since it kind of outputs this pseudo-deterministic product at the end. One way to give them this is through the ensemble mean of the NBM subsystems, which are the Canadian, the GEFS, and the Euro, to quickly summarize those solutions. But the big problem with that is that often washes out really critical nuance amongst the ensemble membership. Alternatively, we don't want to go and give all the forecasters 100-member postage stamps to work through every day either. That sounds awful. So kind of a nice in-between compromise with this is to develop an ensemble clustering approach that distills the ensemble down to its most prevalent forecast scenarios and retains that really critical nuance amongst the ensemble membership. And I also just want to say really quickly that this was inspired by and in collaboration with fuzzy clustering work being done at Stony Brook. So I think it's a really cool example of a nice academic partnership too. So how does it work? This methodology relies heavily on what's called empirical orthogonal function analysis. This is something that climatologists often use to diagnose leading modes of temporal variability within data sets, but we're kind of taking a slightly different approach to this, where we apply the EOF analysis to the ensemble membership itself. So we're trying to identify the leading modes of variability in the ensemble. So here's an example for a day 7 forecast of 500 millibar heights, where the ensemble mean 500 heights are in the gray contours. And basically we see that our leading mode of variability here is this monopole in the EOF pattern that's placed on top of the ensemble mean trough axis. And this is what's known as an amplitude signal. So it's saying that the leading source of uncertainty here is the amplitude of this trough relative to the mean. Our secondary uncertainty, you can see this dipole along the ensemble mean trough axis, and that's a positional signal. So the secondary uncertainty here is the northwest-southeast positioning of the trough. So now that we know what the leading modes of uncertainty look like spatially, we can go ahead and diagnose the ensemble members within that context by looking at the members in principal component phase space. So basically, we have all the ensemble members in that PC1, PC2 phase space on the right, and the colors just denote which subsystem the ensemble member came from. And so basically how this works is that ensemble members with a positive PC1 will look a lot more like EOF1. So in this case, members with a positive PC1 will have a shallower trough than average because the EOF1 pattern is positive. And then same goes for the opposite. Members with a negative PC1 will look opposite EOF1. And the same goes for PC2 and EOF2. And really quickly, I just think this is really cool that we can even do this. Like, look at how much information we're able to get just in a two-dimensional plot. You know, we can kind of see where the ensemble's members play out within these scenarios just by looking at a 2D scatter plot. But we can take that a step further and actually group together ensemble members that have similar scenarios through k-means clustering. And so all the numbers there depict which cluster that ensemble member falls into. And so basically, cluster 1 members here all have a positive PC1, and then for the most part, a positive PC2. So that means shallower trough than average, likely shifted to the southeast. Cluster 2 members have a negative PC1, so those have a deeper trough than average. Cluster 3 members tend to have a negative PC2, so the trough is shifted to the northwest. And then cluster 4 finally has a negative PC1 but positive PC2, so deeper trough shifted to the southeast. So I think it's really cool that we can even just diagnose this two-dimensionally like that. But the other cool thing about clustering is that we don't even need to look at the EOFs or the PCs to use. And this is what forecasters often tell me that they do. They just skip straight to the cluster forecast. And so this is the spatial manifestation of all those clusters that we were just looking at in the previous slide, where you have the cluster mean in the gray contours and then the difference from the multi-model ensemble mean in the color-filled contours. And just by looking at this, you can see how much nuance the multi-model mean is washing out of this forecast that you kind of get back when you look at it from a clustering perspective. If we verify this particular day, we find that the multi-model mean has a mean absolute error of 30 meters, and we actually have a cluster that improves upon that. You can see cluster 1 has an MAE of 21 meters. And this is what we often find with this clustering product, that in generally speaking, the best cluster tends to verify better than the best ensemble or best deterministic forecast. And this is looking at a 6-month data set worth of cases at different lead times. And you can see that the best cluster in blue is able to outperform the best ensemble or best deterministic at any lead time, but that difference gets starker with increasing lead time. So at day 7, you're really getting a lot more value by looking at this from a clustering perspective than you would be with an ensemble mean. We can also use those 500 millibar height cluster members to predict sensible weather fields. So this is looking, at the same set of clusters we've been looking at, but for 24-hour QPF and the difference from the multi-model mean. We also have a page that clusters on QPF uncertainty specifically. So this is the leading modes of uncertainty for a 48-hour QPF forecast, and you can see that the precipitation amounts is the leading uncertainty with that monopole over the mean precip max in kind of Montana and southern Canada. And then the secondary mode is the positioning of the precip max. If we look at the clusters that are generated from this particular day, looking at the 50th percentile 48-hour QPF, you can see how much nuance there is in this precip forecast, not only with the precip max locations, but also like the footprint of how the precip forecast looks. That the multi-model mean just isn't capturing. And some preliminary studies from Brian Colley and his students at Stony Brook have shown that using the QPF clusters directly produces forecasts with better skill than using QPF derived from the 500 millibar height clusters. So this is something we're actively developing. Another really great thing is that this tool kind of gained popularity organically. In 2019, it was being referenced about 38 times in National Weather Service area forecast discussions, but by 2021, it was being referenced over 3,600 times. And this is largely due to Western and Central regions really championing the tool. So it's been kind of cool to see how this was sort of a grassroots thing and the forecasters really use this very regularly. The clustering has also been adopted as kind of a centerpiece of the experimental ensemble visualization platform known as the DESI. And as part of the DESI, the clustering has been used extensively as a scientific tool as well as a way to communicate the uncertainties in the forecast to stakeholders. But forecasters still want more information on how the different clusters come to be, and so this is where another post-processing tool called ensemble sensitivity analysis comes in. So essentially, the clusters tell you the different prevalent forecast scenarios, but they don't really tell you what leads to those different outcomes. And as a forecaster, you could go back and look early on and kind of see which early forecast differences are leading to those different bifurcations, but that takes a ton of time and energy. And so ESA is able to relate those possible forecast outcomes back to the early forecast state and kind of relate what's leading to those different scenarios. So in other words, clustering describes the what and ESA describes the why. So this is something we're actively working on. And so how this works, basically ESA tells you how the atmosphere needs to evolve in order to look like a given EOF. So in this example, our leading EOF shows the main uncertainty is the positioning of this cutoff low along the west coast. And so members with a positive PC1 have that cutoff low shifted to the west, and then members with a negative PC1 have it shifted to the east. And so what we can do is we can turn those PC values for those members into what's known as a response function, and then regress those PC values onto the early forecast state. So that's what this looks like in this example, and it's kind of a complicated plot, so I'll walk you through a couple signals here. And basically, we're looking at how the PC values relate back to the forecast 500 millibar heights at forecast hour 114, so a couple days prior. And the sensitivities is shown in the color-filled contours, and basically we see, for example, with this ensemble mean shortwave ridge, members that have that ridge more amplified early on will tend to have a cutoff low shifted to the west later. With this broad cutoff low, this is a positional sensitivity signal, meaning that ensemble members that have this cutoff low shifted to the west will also see the cutoff low a couple days later shifted to the west, which makes a lot of sense. And then finally, with this shortwave trough here, again, members that have that trough shifted to the southwest will tend to see the cutoff low a couple days later shifted to the west. So forecasters can kind of use this to bring situational awareness and also hedge their bets onto a particular cluster verifying based on how the atmosphere evolves. So all in all, I think ensemble clustering has a lot of potential to really break down the forecast into its prevalent scenarios. I think it'll have its most utility if we use it in conjunction with other post-processing techniques like probability matched means, for instance, or spatially aligned means. And ESA is able to provide additional the ESA is able to provide additional context on how the atmosphere must evolve early on in order to lead to the different scenarios. All in all, though, I think this is a real testament to the potential of data mining these ensemble systems. And as we continue to build techniques around these, I think it's really important that we keep forecaster needs at the forefront. So I think there's a lot of really cool opportunity for O2R and R2O in these spaces. With that, thanks so much, and I will take any questions or thoughts.
We have time for questions.
Oh, wow, wasn't expecting that.
You did great. Yes.
Well, that's a great presentation. Just have one question. Is there a quantitative mechanism to synthesize these different modes into something that could be, viewed more probabilistically? For example, that, where for us users, we're mostly interested in the probabilistic QPF. So if you talk about these different modes, I mean, is there a sort of established process to transform these into, probability of precipitation over a specific area exceeding, a given amount?
Yeah, that's a great question, and actually that's a big part of the DESI. One of the, I think I have a slide that shows it. So yeah, this is clusters, but the really cool thing about the DESI is that once you have the cluster membership, you can kind of like view it and interrogate it in any way you like. So I don't think there's probabilistic. I'm not sure if there's probability of QPF from the clusters in there yet, but that's something that I'm sure will be available in the future. So did that answer your question? I don't know if. Okay, we can talk afterwards too if you like.
My question is, a lot of these techniques can be, particularly using EOFs, can be very sensitive to how many EOFs you retain, or exactly how big the region is. Particularly, you can get domain-dependent patterns. Have you looked at the sensitivity to like including EOF3 or increasing or decreasing the size of your box?
Yeah, so at least personally, I haven't looked at including EOF3, although I think that's a good idea because I do retain some of those plots sometimes, and yeah, occasionally there is some significant looking signal in there. But I would say there's definitely a lot of domain dependence, and so anecdotally speaking, we've been playing around with the best ways to optimize that, and I think I think there's definitely I think. Anecdotally speaking, I think like kind of sectorizing the CONUS seems to be the best way to do it, because if you have the entire CONUS as your region, we find that the signals get really muddy very quickly. And then alternatively, if you have like say a box that just isolates Hawaii, you get like these sensitivities to a single isopleth and its placement. So I guess that's kind of a wishy-washy answer because we haven't specifically looked at it. But yeah, it would be a good thing to explore more formally.
Okay, thank you very much.
Thanks.
I think it goes back to you now. Maybe not. No? This is a Q&A session now, right? Okay, so first of all, I wanted to thank all the speakers from our earlier session and our session just now, so give a little round of applause. So now we have about 25 minutes or so for Q&A. All of the questions, all of the presentations we had this morning, as well as just recently, are fair game for questions at this point. The floor is open. If you have a question, I don't know if anybody's monitoring online. I don't know how to do that from up here. Okay, Jan is monitoring online. Excellent, thank you. So if you have a question, just raise your hand. We'll recognize you. And if there's an online question, Jan will give me a high sign. Well, we'll answer it. We all collected all the wisdom from the speakers.
This is a question that Jin, you probably could answer, since I feel like I'm channeling you. This is to Yujan's talk about GEFS version 13 and thinking about evidence-based decisions. And one of the slides he was showing was comparing the low resolution, which is the half-degree version, to the quarter-degree version. Both of those are substantially better than GEFS 12, but those two looked about the same in their skill. And there may be other metrics that show that the higher resolution is better, but is there evidence that shows he could answer that?
So this is a question for Guo Yuan, right?
Probably, because that was his paper.
Yeah.
But, so.
Is Guo Yuan still online? I'm guessing not, because it's... Oh, there he is. Did you hear the question?
Excuse me. I thought that's question for GEFS.
Yeah, that's
I think that's
Yeah,
for
Oh, for
probably
oh,
for
it's- oh,
you know,
I'm sorry.
the
I'm sorry.
Yeah,
I
the
thought-
region.
ensemble system.
For the ensemble system. For for Yujuan. Yeah. So
yeah,
I don't- he's not here, is he?
I guess he's in a different session or
Yeah,
whatever. So
okay.
on. All right.
Yeah. Sorry.
Well, I'll have to
Sorry. I
defer
thought you were
that to
talking
another
about
time.
the Taiwan results. Okay. So is anybody here who can answer that question? And the answer is no. Other questions for any of our speakers?
I have a question for Ben. Very interesting talk. I may have missed this in your talk. Did you examine the role of radiation in the upper level heating biases?
So, so not yet. We haven't broken down the possible contributors to those upper level biases. So that's definitely something we want to look at. I mean, we want to look at the role of radiation. Like I said, I really want to look at the output of the individual physics tendencies. Since that data is not in the P8 runs we pulled down from Amazon, but it is in the runs that we're doing, so we can sort of make that direct comparison. But it's sort of a long way of saying no, we haven't looked at that, but we definitely want to.
Yeah, I think the two-way interaction you kind of mentioned in your last slide is interesting. Like on one hand, I think upper level heating would affect the stratification, which can affect like convection depths and upper level clouds. Then clouds can affect like radiative cooling or heating. I think that's very interesting. My second question is, how about in the summer season? I think your study was mainly focused on the winter season. Right, yeah. In the summer, I think Lee's research group at Penn State, they mentioned like diabatic heating along teleconnection pathway can help to amplify teleconnection. So that may be something interesting. Yeah, thank you.
All right, I have a question. This is a question for Maria and Lisa. I don't know, is Maria not here? I don't think. I think she left. So just for you, Lisa. So when Maria was showing her results looking at the convectively coupled equatorial waves, she showed a big improvement in P8. And I actually asked her at the coffee if she thought that was because of the introduction of the cellular automata. She said, you can't tell because there's so many changes from P7 to P8, and CA is only one of them. So I don't know if you remember what she was showing, but I'm wondering if you have any comments about what might be going on in her results.
Yeah, it's a good question. So I guess you're specifically referring to the coherence spectra.
Right.
We have discussed that quite a bit, and I think essentially she's showing that it's for the early leads. You see it in early lead times. There's an improvement, but it kind of washes away rather quickly. So there's, from prototype 7 to prototype 8, there were, I think, 3 or 4 main updates in the physics. One was the cellular automata, one was the introduction of the Thomson microphysics, and then another important one was update to the land spin-up. I really suspect that the spun-up land, it had a huge impact on precipitation over land, and it has a huge impact on all our bias over South America and Africa. So I think we should not rule those changes out, but I think we would need more of a clean experiment to be able to say exactly what's what. But this is my suspicion of the changes we made along the prototypes.
Great. So that kind of begs the question, doing one change at a time type experiments. Okay, I got a big excited response to that.
If I may just, and I'll pass it. So while we're doing the physics development for the prototype, we did a lot of isolated experiments. The challenge is a full prototype. You can't just take one change at a time. With the cellular automata, we have done some isolated runs with and without, but we also see it's a difficult one because we see some improvements in early leads, and in all the sensitivity to physics, it washes away, in particular, this coherent spectra. So I think in terms of isolated experiments, we should also maybe consider the initial conditions. That's my comment, and maybe I'll pass it along.
Yeah.
Hi, my name is Ben Green. I'm at GSL. I just wanted to first give a plug that Shan Sun and I actually, in Prototype 8, we did a isolated test to isolate microphysics. We reverted back to GFDL microphysics, and I've realized in this morning that we really should have put more effort to put that data onto AWS, and I've already sent out an email to the appropriate people to do that. So hopefully, if you want to, excuse me, if you want to isolate the microphysics impact, hopefully that data will be soon, because you compare P7 with GFDL to P8 with GFDL to P8 with Thomson. And then to follow up on the expense, yes, these runs were extremely expensive, so it is not for these longer lead times into the subseasonal feasible to do so. But one thing that you may be potentially able to leverage, which I think Lisa was alluding to, is that for certain phenomena, you can look at shorter range forecasts and not have to look all the way out to 35 days to get your answer. But that's definitely dependent on what you're looking at. And then I'll just plug my poster tomorrow evening. You can stop by and I can talk about this at length.
Excellent. And back to Lisa.
Yeah, I just wanted to mention also that even though we say the big change is in Thomson microphysics, it is also because once you introduce a new scheme, you have to ensure you do a lot of integration between different physics components. So there's also changes in how radiation and microphysics interact, and in particular with the changes in convective clouds, how they interact with radiation. So even if we say it's this scheme turn on and this scheme turn off, you have to be very careful to interpret the results because they go together with the rest of the physics has to be tuned. So we tend to list sort of the large updates, but they're not just to be switched on and off. You have to really be careful with that.
So if I could step out of my moderator role for just a second and step into, I would love to be asking questions too. It sounds to me like there's two opportunities here. One is what you were mentioning about some of these intermediate experiments that may have gotten done or that maybe people want to do post facto, so a P8. So a given prototype gets implemented and the full test is run, and then somebody goes back and says, well, wait a minute, there's 20 changes there. Let's see if one of them makes a difference, and do a subset of the prototype evaluation runs, either shorter runs to see the evolution of the short-term error, or a smaller ensemble, or fewer cases, whatever, and then putting those data out on AWS so that lots more eyeballs can look at them. So it sounds like there's really two opportunities there. One is doing those runs, and sometimes that happens by accident because you forget to change. Yeah, I wasn't accusing you of that, but that does happen. And the other is to have the data made available. So, okay. Thank you. That was a good discussion. More discussion. More. And I'll warn you, don't have questions, I will ask more. So, yes, Jan.
I want to add to what Jim is suggesting. I see many nice presentation try to evaluate the science evaluation, so those can be communicate to a broader community, so they know where this UFS stands. Like we seen the MGO seems have been improved, maybe on the level similar to ECMWF system. This is, I heard, is very encouraging. And also Lisa showed this impact, the stochastic CA scheme impacts. And also the diabetic heating bank cache has shown. those are all going to contribute the confidence we have on this system in terms of the science evaluation. I highly encourage the folks continue to design the experiments to understand. We need more eyes to look at the system to improve. Or whatever phenomenon you want to look at, like hurricane or the teleconnection, certain events. I think individual cases may be durable as this kind of sensitivity test. I work at the OSTI modeling program. We like to help the teams. They are working on improvement, but a lot of time it's nice to see the more science evaluation, broad communicate our achievement. I think the team did a great job. Thank you.
We have a question here from Phil. A comment. Okay, we have a comment here from Phil.
Yeah, so there's a lot of talk about putting the data on the cloud so people could evaluate it, and I just want to implore that we need to change what we're putting on the cloud and drop GRIB data. We need to go to cloud-friendly formats like XAR or even NetCDF, because otherwise it's just a big FTP server, and that's not very useful.
For that, other questions? Well, so I have a question, and I want to commend Guo Yuan, your time. So thank you for staying up with us. My question is, so you showed some results from the Taiwan GFS where you have a regional tile that you're running at 4 kilometers, and you showed that the results were worse than your operational high resolution, which I think was WRF, if I remember correctly. Anyway,
yes,
but
yes,
you
exactly.
said for just for the short range, and then the errors become comparable after day 2. Is that because the errors have gotten so big that there's basically no skill left in either of them, or is there some physical reason why you think the regional tile that you're using in your current system gets better over time relative to the old system?
Okay, thank you for the question. So, actually, honestly, we didn't spend too much time to our regional nested tile in TGFS, just because of the limited human resource here, and because we already had a very, I think, a mature WRF-based operational regional system, but we try to study the differences, and I think I don't have a good answer now, but I would say that one thing we found is the skills are quite different for different weather systems, and for the FS3 based system, it performed extremely well in the winter season, but it's more problematic for the summer season with some convection. So I think that's overall average skill cannot tell too much. We need to study more carefully.
Thank you. Other questions for our speakers? I'll keep going if you guys don't have questions. Here's a question in front.
I have a question for Lydia, and I guess really everyone in the room. And I'll preface this by saying it's unfortunate that we're sort of literally parallel to halves, tropical cyclone. So Lydia, you showed results, which I've seen before, but you showed results on the tropical cyclone performance in HR1, and you were talking about how coupling, made the tropical cyclones even weaker. And I guess my question is, how much importance should we be putting on having a global model get tropical cyclone intensity correct because of, number one, the resolution of the model, and number two, the fact that we have things like halves, and I would even say number 3, the fact that if we try to drive the model more towards tropical cyclones, we might be doing at the expense of other things in the larger scale circulation. So it's really open to anyone, but Lydia, you're the one who brought up that slide, so.
Well, I will probably leave most of it for somebody else, but I would say that while it's not the primary focus, it probably having the intensity at least decent is good for forecasts away from not for just the tropical forecast, the tropical cyclone forecast itself, but also for the surrounding environment. So I would think if it can be fixed without great cost, it's not bad to do so. And then I'll leave the whether it's Half's job or well, I'll leave it open to others who are probably who may have other opinions on that.
Does anyone else have an opinion on that? Okay, well, yeah, Lisa, is it same thing or different? Okay, Lisa has a comment.
Just maybe an opinion is that we should always develop physics for physical reasoning and not tune things for a specific phenomena, and particularly in a global forecast system. So I think that's the challenge sometimes that I see with the HAFS model. The main metrics is essentially hurricane forecast, but it could be when we try those changes in a global system, we do see a degradation across the globe, and to me that's a little bit concerning. But I would like to understand a little bit more about why we see this in HR1, because it's not trivial to understand why the changes in coupling cause such a degradation in the track. At least not to me, but maybe to others.
If I may, I don't think. Sorry, I didn't know if you're done. So I don't. The degradations that we see in the track are not necessarily something that we can be very certain of, because there's very few cases towards that end of the curve, towards the point where they start diverging. What we definitely see is the degradation in the intensity. So the track, I think, is not very clearly super statistically significant.
Oh, okay, thanks for clarifying that.
So that actually stimulates the question I wanted to ask, and this is a question for Lydia, but it's also a question, and also including Austin. What should be the driver for the way we understand the changes that we make in the models? And I'll give you an example. So what we just heard was there's a potential trade-off between what the stakeholders require, which is more skill and longer lead time and et cetera, versus a physically realistic model. So sometimes a game is more like the Earth we live on, is bad for the forecasters because the model gets worse. So what should be the driver? And maybe the answer is both, or maybe the answer is neither, but I'm just curious if people have thoughts about that. And I would place a side bet that people who are in operations will have one answer and people who are in universities will have a different answer. But any reactions to that? Maybe I'll put Lydia on the spot. How do you feel about that?
All right. Well, I think from a practical point of view, if the forecast is not better, the model might not get accepted. So that would be a problem. On the other hand, I think forgetting about one in favor of the other is not a good idea, because then things go into never land at some point. So I think it's best to try your best to make the model be as physically correct as possible. But then unavoidably you do have to add tunings that take you away from that. But I think pushing both, trying to catch each other is the optimal strategy, and that's not very objective way of talking about it, but I think it somehow works out in the end.
Okay. Lisa has a comment?
Yeah, I think when almost every single time when we have a better parameter, I would say better in terms of better process description or better inclusion of another tracer or something, an advancement in physics experimentation, we almost always see a degradation in skill because of compensating errors. So the challenge I see is that we should always strive for having improved physics. But the challenge, I think, is what do you do then when you see that this degraded your results? And I think this is where we shouldn't work on physics development and compartmentalizing it to individual schemes. And that's been a huge lift when we have the working groups, because then convection people can talk to microphysics people, and we can address it as a physics as a whole. And I think that's a really key thing that we see that recently with the gravity wave drag scheme, we can really isolate. We could see we had a massive drag near the surface in the previous scheme, and we correct it, but now the anomaly correlation goes down, and something else is compensating for that, and we really need to dig into correcting that. So that's sort of my point of view on this question.
Good. Other reactions? Phil has a reaction.
So the response to that, and also to Lydia, to your talk about basically the expected benefits of the coupled model, I think it's helps, basically move towards getting the right answer for the right reasons, because there's more room for things to go wrong. So you don't have an infinite heat sink in the ocean anymore. So if your fluxes are messed up or you're too many clouds, you're going to pay the penalty. So it's just, it makes for better physical, it forces you to have a better physical representation.
Okay, so we have 4 minutes left, and I wanted to tee up a really provocative question that builds on what we're just talking about. It's from applying a machine learning algorithm that was originally developed in China, and the Chinese showed that they were able to equal or beat the skill of the IFS, their global atmosphere. So the European Center took that to heart, and they did a rigorous test of the machine learning algorithm versus the full up physics, dynamics, everything, yada, yada. And without, without making any kind of a value judgment, they simply said they are able to reproduce the skill level that they get with IFS using the machine learning algorithm. And they have invested considerable funding into developing an operational capability using a machine learning algorithm in place of, well, either in place of or in addition to, for ensemble generation or what have you. So that kind of flies right in the face of what everybody is saying in this room, which is more physical intuition, a model which is a better and better representation of the actual physics and the actual dynamics is a better way to go, because that model knows nothing about dynamics and physics except what it has learned from the data that it's been fed. So we have 2 minutes left. Comments? Phil's got his hand up.
I'll jump right on that. And the first thing, all of these algorithms, these machine learning algorithms, produce a good reanalysis.
So far, that's true, yes.
We're never going to improve if we basically just base our knowledge off of statistics, and that's what machine learning is.
That's right, but you could imagine, machine learning version 2 that starts from the observations and goes straight to the forecast. No DA, nothing, no reanalysis. You could imagine that. Nobody's demonstrated that yet, as far as I know. Yes?
Very quickly, machine learning, I think, has the biggest weakness of machine learning is in the extremes. And that's when the, tried and true physical models will outperform and always outperform.
That's true. But if you look at the European Center report, there's one really provocative graphic where they're showing the error at 6-hour intervals for IFS and the machine learning algorithm over a 3-month period of forecasts, and they track each other perfectly, almost perfectly, including all the times when the dynamical model has a big dropout. So RMS error goes up by a factor of 3. Same thing happens in the machine learning algorithm. So the implication is that the algorithm is actually reproducing the dynamics and physics quite faithfully at 5-day lead time. So, so in principle, that's either because the initialization is bad for both of them, or it's because there's an extreme event that neither of them got right. So there's more analysis is needed there. Was there another hand? There's a hand up right way in the back. I'm trying to tee up a nice conversation for lunch, so yeah, please go ahead.
I actually had a really great conversation about this last night. I think it would be impossible to solely rely on machine learning algorithms because you have to rely on how they're trained. And if you have no improvement in the physical representation of the model, you have no improvement in the machine learning model because you're training. So it's almost impossible to say the machine learning algorithm is better when it's based off of what we already have. And so, yes, I think we should absolutely pursue machine learning. We should absolutely pursue every avenue to improve. But if we rely solely on a method, one particular method, I think we lose something.
Yes, here's a hands up here.
I think machine learning can complement some of the difficulties we have right now. For example, some of the physical processes, we are not sure what exactly the equation is. So this is where the machine learning can contribute. So for example, using my own study as an example, we are looking at the snow cover simulations in the UFS land component, but then we don't know exactly how to represent that formulations. So this is where the machine learning can contribute based on all those available observations we have. So in such case, I think machine learning is very valuable and has its own benefit to improve our current physics-based model. We can have the hybrid model for sure, because a lot of parameterizations, even in the current version of UFS, it's still based on empirical parameterization. So, yeah.
Yep. Yeah, that's a very good point, the complementary modeling capability. There's also complementary post-processing. So this gets to Austin's presentation, where rather than using principal component analysis or some other a priori evaluation of what you think is going to be the pattern of error, you simply turn a machine learning algorithm loose on all of the forecasts that you've got and end up with a way of characterizing the probabilities for given synoptic situation, whether we're going to have a good forecast or a bad forecast. We're out of time. The intent was to be provocative at the very end so you'd have something to talk about over lunch. I hope that worked out for you all. I'm going to turn it back to our MC. And thank you all very much.
All right, so it's now time for lunch. This is also a reminder that there is an AWS Q&A session at 1 p.m. today in room 3131. Again, that's room 3131 at 1 p.m. for the AWS Q&A session. Also a shameless plug, I'm also hosting a student session today, actually right now. I'll just be grabbing lunch really quickly and then heading up to room 2126 for my student session. We'll just be discussing the UFS and academia and how we can bridge the gap between the two sectors. So if you are interested in attending, that's room 2121, and I'll be hosting that in a few minutes. So thank you so much and have a nice lunch. All right, welcome back from lunch. We'll just be starting in a couple of minutes. Okay. I think I'm introducing someone else. So, okay. Don't worry about saying any other names. You look to handle that because they're the ones So you just let them, you hand it over. Just know the times you have on there, that's when I'm lifting up my cards, and now you know why I'm lifting up my cards, because they're around each time, and then if you need to kind of cut them off or push the next person, you can do it. I thought I was just introducing people at the beginning, and then introducing Fred Carr, so he could introduce everyone? Okay, that's totally you. Okay, okay. All right, hello everyone. We're back from lunch, and I hope you all had a great lunch. Just another reminder that there is a Q&A session in room 3131 right now at 1 p.m. So this is from the AWS Q&A from yesterday, so if you had any follow-up questions, please make your way to room 3131 for this session. Also, just a note that the two sessions have fused into one, so we'll be starting with our presenters, and then we'll be following up with our panelists. So if you have any questions, please save them for the panelists, and they will answer them for you. But for right now, I'll pass it off to Dr. Fred Carr to introduce the presenters for the afternoon session.
Hi, good afternoon. I saw on the program that my name was listed in the bio sketches, even though I'm not speaking at the meeting, so I thought I'd make myself useful. So as long as we keep the slide up there. So yeah, so they've just recently reorganized the session, and we'll just get started on insights from industry and academia. And the first speaker will be Luke Peffers, who's currently the Chief Scientific Officer for Tomorrow.io. So he's representing a growing, innovative private sector company. Luke is actually from my alma mater, PhD from Florida State, in a variety of positions since then. And we'll just let him get started. So come on up, Luke.
All right. Can everybody hear me okay? All right, I'm going to set a timer for myself to make sure I stay on track. All right, as Fred said, I'm from Tomorrow.io, so we're representing the private sector. Wanted to share with you guys in the next 12-ish minutes kind of some of the work we've been doing over the past, I've been with the company for just about 5 years. Company's been alive for about 7. Let's see if this will work. Okay, so really quickly, what is Tomorrow.io? We're a SaaS company, so it's software as a service. We have a web platform, mobile app, API that customers basically get weather data from us. We do a little bit of work on the back end of data. We're not just providing raw weather data. We're providing insights and what we call weather intelligence to help customers understand the weather and what it means for their businesses. So this is kind of the user dashboard and why we're building models under the hood. So what I want to talk about is what's under the hood of this dashboard and how we're using things like UFS and WRF and what some of our future plans are. So really quickly, as I mentioned, we are a SaaS company, but we don't stop there. A lot of companies just regurgitate government data, which is a really useful service to make use of government data in web apps. But we go a step further. We want to control accuracy, and we want to basically be able to optimize some of the weather forecasting for our customers. We do have the luxury that we don't have to optimize every parameter for every altitude, for every use case. We optimize for our customers' use cases, mostly surface level weather, precipitation, temperature, humidity, things like that. The way we do that is we do have our user interface built in Tel Aviv, so we have a few offices, Tel Aviv, Boston, here in Colorado as well, and then some other scattering around the country. So what I focus on is the weather modeling, so I run the weather modeling team within Tomorrow, and we build our own, we call them proprietary weather models, but as we all know in this community, we're basically using UFS, WRF, MPAS, and things like that, and the proprietariness is how we tweak the knobs, how we do the data assimilation, what observations we're using in the system. So we do a lot of that work. We've been running WRF-based regional systems for about 4.5 years. That's what I joined the company to start. And we do that because there's a lot of gaps, especially outside of developed nations, outside of areas where we have HER, the JMA in Japan and things like that. So we like to run high resolution models, integrate customers' observations when we have that opportunity, and basically optimize the models for those use cases. So we have a lot of WRF regions running all around the world, in Africa, India, Central, South America, things like that. We don't stop at the models. We're a very innovative company, a very ambitious company. So we're also launching a constellation of satellites. So we have active radars and microwave sounders, tropics-like sounders. We've launched our first two Pathfinder radars, so they're active radars. They're nadir pointing only. And we have 2 of those in orbit right now, just launched just over the past few months, we've launched them. So we were starting to gather data. Things are really exciting, got a lot of that data in-house. So the next step for us now is how do we take that data, not just from the Pathfinders, but from the cross-track scanning radars that we're going to launch into next year and the microwave sounders next year. How do we make use of that data and bring that value to the customers through that web interface that I showed you? Because we're not going to be just providing raw data, satellite data, or model data to the customers. We're giving them this user interface to make sense and translate that information into actionable intelligence for their businesses. So really quickly, I wanted to set the stage for how we're using UFS. Basically, it's going to be replacing our WRF regional grids in the future, but right now we're going to continue with the WRF. But we are launching a global constellation of satellites, radars, and sounders. What we imagine, what we expect, and our hypothesis is that we're going to be seeing a lot of benefit from the microwave sounders in the NWP models. We're going to be seeing most impact from the active radars in our nowcasting, our real-time and nowcasting precipitation. So this is a little cartoon that kind of shows accuracy on the vertical axis and then time horizon, so your lead time, forecast lead time, and how the various models perform. You all probably know this very well. With the nowcasting, I don't know if color, we do have color. Earlier today and yesterday we didn't have color. So this large dashed blue line represents kind of the nowcast type of accuracy that we expect. In real time, we have the best accuracy, especially where we have active radars and X-rad radars, or things like in Japan or the Bureau of Meteorology, and in Europe, we have active radars. We're directly sensing the precipitation, so we obviously expect the skill to be very high. And then we have a nowcasting system that's currently based on optical flow that projects those systems into the very near future, hour or so, and then the assumptions of that optical flow drop off pretty drastically. So you can see that blue line, skill drops off pretty quickly. NWP starts to pick up after the cold start scenario, so then we see a pickup in skill for the larger lead times, multiple hours, multiple days. We go out to 2 weeks, but most of our customers are interested in the kind of high impact 1 to 5 day region, so that's where we're really optimized. So right now that green kind of dashed line shows the cold start spin up where accuracy increases after the cold start, and then we have a pretty good set of a couple of days of forecast accuracy until the boundary conditions wipe it out and just the forecast degrades. We also have a machine learning post-processing system that we call 1F. So we basically post-process all of our NWP models to reduce systematic biases. And we also generate a synthetic ensemble from that as well. So with this neural network, we're able to take a deterministic forecast and derive a probabilistic forecast from it. That just allows us to save cost and computational power. Ingesting ensemble data from the various national governments, we just generate it synthetically with about 4 years of training data. So we're seeing a lot of skill with that. So setting the stage, this green line is kind of what we're going to be talking about today, how we're using UFS and things like that. Holistically, what our customers get, though, we don't give them a spaghetti plot, we give them an optimal forecast. So we blend all those models together, we take the best performing models for each time segment, each variable, and we deliver that to the customer. So most of our customers are not experts. They don't want to see a spaghetti plot. They don't want to see ensembles. They just want to say, they want to receive our best estimate of what the atmospheric state is at any given time. And these probabilities, this kind of dashed line represents the uncertainty. So in the early hours, we're using that from our nowcast system. We're deriving uncertainties from the nowcast system. And then in the out hours, we're deriving that from the machine learning post-processing of the NWP models. So NWP models are the core for a lot of what we're doing. As I mentioned, we're running CBAM regionally around the world. And then we're in the process of building a UFS global system. So we were about 1.5 years into that project. Got Stelios here, my colleague's VP of Science and Technology, who's leading this team. But basically where we're at right now is we have a few external collaborations. We have a NOAA CRADA that we're working under to basically help NOAA assess the impact of our radar and sounder data for possible use in NOAA systems down the road. Also with JCSDA, got Tom here in the crowd as well, so we're working closely with Tom because we're going to be using JEDI for the data assimilation component of our UFS forecasting system. So right now we need to operationalize UFS. We're starting with UFS-EPIC DICOR. We would like to go to MPAS. We have MPAS in-house. We've done some experiments with MPAS, but unfortunately we need to move quickly. We need to move, and we also need to reduce computational power because it costs us a lot of money. We don't want to pass that cost on to our customers. We need to keep computational costs as low as we can. So we're starting with UFS-EPIC based on its performance, its computational performance. But we do have a lot of interest in moving to MPAS in the future. So we're definitely following a lot of the GPUification of MPAS to see if we can get the performance up to speed where we can implement that. But the workflows and things that we're building will be able to allow us to implement FE3 or the MPAS DICOR down the road. So right now we're working on the operational, kind of both, two things in one. I think a couple weeks ago we had the workshop on workflows, and we had a lot of really dynamic discussions on how to build workflows. We're actually building our own workflow right now. We're using components of the JEDI, JCSDA Skylab for 3D VAR cycling, but for us, we need to be able to do research as well as operationalize the system. So we're kind of doing both of those right now. We're focusing on OSSIs, observation system simulation experiments with the system right now so we can quantify the impact of our simulated radar and sounder data. So we have simulators that are giving us what we expect to see in space, and we're able to do these OSSIs with that now to help configure the constellation. How many satellites, how many of what type of each satellites, the radars versus sounders, what orbital configurations and things like that, and what resolution and air specifications we can tolerate. So we're doing those OSSIs right now with the idea that we're going to be able to operationalize this model toward the mid or end of next year when our full constellation is flying, or the majority of our constellation is flying. So that is where, so we're doing these OSSIs, we're simulating all the Earth observing systems, and we're going to be using 3D VAR, hybrid 3D VAR, and possibly other variants down the road, but just focusing on the simple solution to get something out the door, focus on the impact studies, and then operationalization will come next. And we're doing a lot of work on trying to figure out what resolution do we need, what refresh rate do we need, and it really comes down to what impact we expect from our satellite constellation, because there's really no need for us to be running this model if we're not going to be adding additional data into it. We're not just going to rerun UFS, the same configuration, so we want to extract as much value as we can, and based on how much value we extract and the configurations that go into that, resolution, update frequency, and things like that, that will determine what our operational configuration looks like and how much we're going to spend on that. We do run this on multiple clouds, so we've run natively on AWS, Google. We're now migrating, I don't know if Tim is in the crowd, but we're migrating to Microsoft Azure. We have a big deal with them right now, so we're going to be migrating a lot of these operational systems to Azure. We also have a data center that we lease in Iceland. So we're going to be running some of these research components on a data center in Iceland as well. So skipping forward really quickly, we've done a lot of experimentation. We're doing the single ops tests and things like that with all of our simulated data. The idea is we're going to build an operational workflow. I'm speeding up a bit because they're giving me the minute marker here, a couple minutes left. This is the ultimate goal right here. We already have an operational system like this that runs WRF regional. Wharf and GSI, so we're replacing that with UFS and JEDI. Same operational workflow. We're going to completely rebuild the workflow, though, with a little more modern technology. So 3 really quick slides. So helpful things that are coming from the government. We love the tutorials, the academies, the workshops. They're a great way to introduce users, especially when we're onboarding new employees to the company. NOAA's transition to GitHub is outstanding. We love that the code is open source. We can grab that open source code, and it's really useful. The documentation is mostly useful for us. Shared computing resources like Orion, although we don't use them, it is beneficial to have that. HPC considerations, so the JCSDA, NOAA, NASA efforts to unify the kind of software stack, the SPAC stack has been immensely valuable for us, so thank you very much for that. We very much value that. It's helped us accelerate our research and operations tremendously. There are a lot of missed opportunities with performance. We are a private company, so the price tag that we pass on to our customers dictates how much we can sell and how much profit margin we have and how we can maintain ourselves in the future. So cost really, really matters. So performance for us is cost performance. So anything we can do to improve the efficiency, like I mentioned with MPass, we can't use it right now until we can really GPUize it to a point that we can afford it and not pass that cost too much on to our customers. Barriers to development. So this, as we all know, this is a lot of this whole EPIC program and getting open source code is new. So there's a lot of work to be done on just a lot of these systems are built to run on NOAA systems. They're built to be operational. They're not built for commercial private use and research. So we're running into a lot of those hurdles that you all are very familiar with. And at present, there's really no good on the JCSDA side. Sorry, Tom. We're having some difficulty with getting access to the firewalled code. So right now we're just using the public version of the code. We've made some strides to try to get access to the firewall codes. Tom's been really supportive in that, but we've hit some roadblocks. So it makes it pretty challenging for us to implement the operational, not operational, but the firewall JCSDA JEDI code. So we're using the public version only. There's some challenges when they release updates. We don't really have awareness of that until it's already updated, and then we have to go rebuild some of our systems. So we're doing a lot of back and forth on that. It's a challenge, but we're making progress. We do have the 3D VAR, the Skylab thing running in pseudo operation mode, which is really valuable to us. But we're making progress nonetheless. And how we would like to contribute. Oh, that's my Mandalorian telling me it's time. Yeah, so we'd like to work, I'll just stop there. We're really enjoying the collaboration we have with the government sector. So we're just going to continue to work with Tom, continue to work with EMC through our NOAA CRADA. And as these satellite constellation flies, we're going to be doing a lot of joint work with the University of Oklahoma on the Cal-Val of our radars, as well as with the NOAA community. So that's what I've got. Yeah, exactly.
Yeah. All right, great. So so be given online. So someone come up and make sure that happens. I don't see anything here to bring her up. Yeah.
We are getting her online.
Okay. So hopefully she'll show up. Anyway, Dr. Shugang Wang received her PhD from Penn State University, and she joined the School of Meteorology faculty about 14 or 15 years ago, University of Oklahoma, and is now the Robert E. Lowry Endowed Chair of Meteorology, and runs a big research team under the name of MAP. And hopefully she will she is going to talk to us about the experience of her research team with the UFS. So.
Yeah, I'm online. I'm waiting for the share screen.
You should be able to share now.
It's actually not allowing me to share. I mean, the button.
Okay, I can hear.
It says one participant can share at a time. It seems somebody else is sharing.
No one else is sharing.
Oh.
We can move on to another presenter, and I can work with you offline just to test it out further.
Okay, let's do my talk after this then.
Okay, let's see. Well, if I'm doing this by memory, I think Christiane, sort of moving into we're sort of combining the speakers from the 2 sessions we had this afternoon right up front. And she is a professor at the University of Michigan. So just let her get started here.
So I'm talking about the UFS as a teaching tool, also as a model development tool, but academic research perspective. So basically, I'm asking a kind of provocative question: Is the model ready? The answer is no. And now I'll give you some reasons why I think that's the case, and give you some potential solutions that we can discuss further. Also, we'll augment this with a live demo in about a couple of minutes. So I hope that works, and the IT team can switch over to my own laptop. Not yet, but I give you a heads up. Okay. When we talk about the academic community, we have two groups. This is probably true also within NOAA or other communities. We have, I guess, let's see whether this works. We have a model development community that's smallish. These are the people like me who look at the real code, the Fortran code, the dynamical core, the physics parameterizations. That's not the majority. So we are really digging in. We are often in close contact with NOAA or the development agency, depending on the model. And we often utilize and benefit from idealized simulations, and I will hit home that theme. We also, and this is my other part, we also have like an academic community, a user community, and that's maybe 90% plus. These are the people that do not necessarily contribute no code or really modify the modeling systems in substantial ways, but they use the models with kind of the primary interest in analyzing and understanding phenomena in weather and climate models. So this is really generic for both communities. Often minor code changes, they might run some sensitivity analysis, some parameter changes, and they might not have really an interactive relationship with any of the centers. All right, so that's kind of where we are. And I'm now kind of in the middle as a professor at a university, and I teach modeling. And so what I think, let me just go. Oh, I don't think I can advance. Oh, let me see. Oh, okay. All right, what I want to hit home that we in the academic community are really at the heart of the, I guess, career development track. Yeah, we are educating the people that might join NOAA or other agencies. And what I mean by that, we are teaching, not at all universities, but hopefully more and more, we are teaching, model development, model, use and development. Here are a couple of examples how we had been doing this in the past. So these are now photos from the so-called Dynamical Core Model Intercomparison Project, or DCMIP as an acronym. And we have, and this was here at NCAR, we had been inviting the international community, and mostly I would say the dynamics community, the dynamical core community to NCAR over, a span of many, many years. It was kind of 2000, oops, where's my pointer? 2008, when we first initiated that. These are like 2-week events where we bring in the international lead developers from the model agencies and a group of students and postdocs to educate them what the newest dynamical cores are about. So we did this in 2008, 2012, 2016. We do it again, maybe in a year or two. And here you kind of see just pictures of this community. And again, these are members of the international community of learners. Here are a couple of maybe, more in-depth photos. So these are now, the inner actions. These are hands-on exercises, hands-on modeling, intercomparisons, I should say. So what the concept of this is that we run and even invent idealized test cases, idealized model configurations. We communicate that to the international modeling communities or modeling groups, and we let them implement that before we meet here at NCAR. And here you see now the inner action that happens every day here in this room, even for a 2-week time period, where we team up the students and the modelers, and they learn here about the dynamical core options and pros and cons. So this is, again, used for academic resources or purposes, but also for us as a research tool. Okay, so let me give you a little bit of a deeper dive what I'm talking about when I say idealized test cases or idealized model configurations. And here I kind of walk you through in a minute a kind of a live demo of a website that I put together when I teach a modeling class at the University of Michigan. But let me give you a little bit of a spiel before I do that. So here you actually see a snapshot of that class webpage, where you see kind of hands-on driven projects, and I will dive into a few here in a minute, but you see already maybe familiar patterns like baroclinic waves or gravity waves. This is an affection example. Here we see some aquaplanet, like more climatology of things. And what this is really, and this is at the heart of the problem, let me also get you to the kind of my bullet points here. Yeah, these idealized test cases really serve, as I mentioned, a development community. If you had maybe a chance to see Lou Wicker's talk this morning in the short-range weather application, he made a really convincing case that idealized test cases are mimicking the real-world problems we, for example, see in Rufus. But also in the educational example that I'm now presenting, I'm using these more idealized test cases for project-driven hands-on exercises. The tool is a CSM tool, and this is why I say, can I use the UFS? No, because the UFS is missing all the components I will be talking about next in my demo. The class covers really a broad spectrum of both dynamical core options and also physics, and I let the students experiment with idealized configurations. Could UFS be used? It would be super, but let's work on that. So it's very desirable, and this could maybe lead the way to another, DC MIP with a UFS participation. So the need that I want to claim we have is an easy-to-use UFS model hierarchy. All right. So I want to now switch over to a demo, and you can all do this at home if you have that presentation. So I actually put the link to that webpage here, and I will click on it here in a minute and share my own screen. And let me dive into a couple of these examples to really hit home what I'm talking about, to make it a little bit more concrete. So let me share my screen. And then the IT people should stop that screen share. Can you stop the screen share? Yep.
We just did. Please go ahead and share.
Okay. And do that. And hide that. All right. Okay, so here is now an example of, let me also use my mouse here to guide you, an example of a class web page. We are basically using a Google site, a wiki, and this is really the communication tool. So I'm teaching via that, I'm posting my lecture slides, but also the students work or present their hands-on projects via that slide. And I just want to give you a few examples how this feels for the students and also what the opportunities are. Let me guide you to a couple of these class projects that you see here, and I just want to click on a few to really give you a better example. So what I'm, as a lecturer, I'm posting actually a lot of instructions. So even that's, of course, a to-do list here for the UFS. We do need to educate more people at the universities, at the professor or lecturer level, to do what we can do here with CSM. So once we introduce the theme, and here, for example, I'm picking the impact of topography as a theme of that particular hands-on project, I post some ideas, what students can do. I also post some teaser images, for example, what topography can do to the numerical scheme, how the errors are assessed via topography, or here it's like a wave that's triggered by topography. But let me click on a couple of examples. So my students then go ahead and they post their own wikis, and this is how we are discussing the results. So let me kind of go to maybe Gopal. So here, Gopal was a student in my class who looked at mountains, the inclusion of mountains in a baroclinic unstable flow scenario. So these are kind of idealized initial conditions, and I know it's a little bit smallish, but basically what Gopal did, he moved the mountain. You see this mountain here a little bit in the black marks. He moved the mountains to different locations. For example, he is in the southern hemisphere, and he looks at the evolution, in this case here, of precipitation, or actually there's precipitable water. Down here, let me go here, we have precipitation. So depending where you move the mountain, he can make judgment calls by himself what impact that condition has. Another student also used this mountain example, very similar, but he asked a different question. He used the same initial condition, but he asked what happens if I go to a different mountain height? Just increase the topography height. So this was Gabriel. So if I click on his presentation, we are now looking at basically a baroclinic wave, but here in a cross section, you see a small mountain, kind of a medium mountain. This was a Mount Everest mountain with a 9-kilometer top. And so you're seeing here kind of the evolution. In this case, it's actually the water vapor and the evolution of the water vapor behind that mountain flow. And again, I let the students experiment. I give them suggestions and leads, but they are the ones that drive that research. Okay, let me maybe go to a different example. And I have only a few minutes left, I believe. So let me go maybe to an advection example. So here we are testing 3 minutes, all right. Here we're testing how good models are at transporting advection or the transport process. Again, I give them a couple of ideas. Here you see my extensive notes, yeah. So this is a contribution that the instructor makes, but once you kind of scroll down, I give them a little bit of lead, you know, what they could be looking at. Oops, couple of the teaser images. And let's kind of click on one person here. So this person, Alex, compared potential vorticity and potential temperature, which are a dynamic tracer, basically, in adiabatic models. And if you now compare potential vorticity up here to a tracer potential vorticity, and down here, potential temperature to a tracer potential temperature, they should look alike. And again, this is something that gives us information about the quality of dynamical cores. All right, let me maybe wrap up with one more example, and then I go to last project here. Towards the end of the class, we are going not just after the dynamical core, but we are going after also physics interactions and more complex configurations. Here, I talk about still somewhat idealized configurations, like an aquaplanet, for example, where you remove the topography and the lower boundary. And when you kind of do that, and let me just go to one example, maybe Joe, as a student here. He intercompared a couple of things. Actually, he compared runtimes. That's another aspect, like the scientific computing aspects. But also, he compared the complexity of aquaplanet versus AMIP. AMIP would be now fully forced lower boundary conditions. So, and he, I guess here we see examples of like Wheeler-Kelladis diagrams. We're also, not certain we have it here, we have some Hofmüller diagrams at times. We also can skip, so he used different configurations. So this is actually the AMIP, this is the aquaplanet. So so this really gives a tool, and I want to wrap up now. It really gives a tool into the hands of students to not just learn from me, but also learn from themselves, from each other, and really diving deep into a project. All right. Okay, let me stop that presentation, and then we just wrap up with, can you please go back to my slide deck? Yeah, so I'm just wrapping up, and oops, see whether, okay, one more, it's too far. Okay, let me wrap up. So my plea is, yes, UFS would be great to use, but it's not ready yet. And what we need in the UFS to make it ready for such exercises in the academic community is a hierarchy of model configurations. What you saw was the pyramid. Also, please note that Mike Eck will be talking about that on Thursday. We have pockets, and this is my closing comment, we have pockets of that model hierarchy available to us with FV3, but we have it in GFDL Solo, we have it at NOAA and SSL, we do it with an NCAR, LCSM, a little bit at DTC, so it's not really in the UFS. So the UFS has many gaps to fill. We need a portable model, we need a flexible workflow, we need the capabilities of a hierarchy in there, and this would be good to have as a wish list from the academic community in the future. Thank you.
Okay, thank you. So do we have Dr. Wang ready to go? I guess I already introduced her, so. All right.
So can you see my screen and hear me?
Yes.
Okay, fantastic. I'm sorry about the technical issue. I'm glad it's resolved. Thank you, Sean. Okay, our experience of using UFS for academic research, I thought, why not just do a survey for the students and the scientists working in our group? So I actually have two questions to them. The first one is, what are the existing aspects UFS that are useful or helpful to enable your research? And the second question is, what is your wish list for UFS that you think will further enable your research? So I'll be sharing a summary about all these responses to these two questions in the last part of my presentation. But first, I'd like to talk briefly about the research that our group is doing so that you have a context in terms of how we are using UFS for our research and what component UFS are being used in our data submission research. So this slide is just a brief screenshot from our website. So basically, we're interested in developing new data submission methodology, new ensemble forecast generation methods, and also applying all these novel methods for a variety of NWP problems and systems, covering a very large range of scales. For example, we're on forecasts like a supercell, a continental, United States convective system, hurricanes, and also medium range global forecast as well. We are also very excited about doing O2R, R2O type of work. Actually, in the past 14 years, we have been working with NOAA, many research labs and operation centers to transition our data submission research into NOAA operations. So in the next few slides, I'm just going to show examples how UFS is used for our data submission research. I'm not going to talk a lot about science here. The purpose of showing this briefly is just give you an idea of how UFS is being used for our research, what components we're using for our research. So the first few slides about developing multi-scale data simulation for F3 GFS. Multi-scale data simulation not only applies for coupled Earth system component data simulation, it also applies for like a single component like atmosphere, which is housing many, many scales. How do we initialize all the scales? So for this slide, we developed multi-scale data simulation with scale-dependent localization for F3 GFS 4D in VAR. And we found the multi-scale data simulation is able to improve global forecasts for almost all levels over the operational approach. So we will also further develop the multi-resolution background ensemble 4D in VAR for F3 GFS. And this is work done by master student Erin Jones in our group. And she found from her master thesis, the multi-resolution ensemble 4D in VAR is able to improve global forecast compared to the same cost, single high-resolution ensemble 4D in VAR for F3 GFS. And recently, Erin, through her PhD dissertation work, is working on developing the vertical flow-dependent localization for F3 GFS 4D in VAR. And her initial results show promises of this approach to improve GFS hurricane track forecasts. Okay. So the next few slides about examples of data submission for HAPS for hurricane prediction. And hurricane prediction is really a generic multi-scale problem as well, because you need to initialize hurricane self properly. You also need to initialize the large-scale steering flow for hurricanes as well. So we further developed the multi-scale data submission approach for HAPS 4D in VAR. And we found the multi-scale approach is able to improve the intensity forecasts, and it's also able to improve the track forecast, especially compared to the single-scale approach using a smaller localization radius. Okay, we know that over the open water, satellite radiance will be very important for hurricane sampling because we don't have many in situ observations. So in this work, we're doing research development to assimilate the ghost all sky radiances for HAPS, dual resolution in VAR. And we found that if we are able to use bias correction and depth observation error, the forecast for hurricane assimilating ghost 68 all sky radiance is much improved. Okay, so we're also working toward fully coupled data submission for HAPS. And the first topic will be how do we improve the background ensemble covariance at LC interface, the coupled covariances. We're taking advantage of the field campaign observations, which provide paired sampling of the atmosphere and ocean to first verify the HAPS model And then we'll use the same data sets to validate the covariances and to improve the covariances at LC boundary. The next few slides is about our research development for data summary for RFS. RFS forecast is also a generic multi-scale problem. So we further developed multi-scale data simulation for RFS prediction as well. So for this work, we found using the multi-scale approach, you can outperform the baseline in the reflectivity forecasts. And the baseline is mimicking the RFS operational configuration. So Yue Yang is working on developing convex scale static background currents for RFS hybrid EMR. So with this new convective scale static covariance, we can the 3D VAR actually shows improvement for the pure ensemble approach for certain aspects. For example, it can catch the midstorms that the pure ensemble approach cannot capture. When we hybridize static covariance with a pure ensemble approach, you can see these hybrids are performing both. Since 2017, we have been using the hazard weather testbed run here at the National Weather Center to test our data simulation research development. In 2022, we test the multi-scale implementation of the valid time shifting approach for the FE3 LAM-based EMR, mimicking the RFS. So we found that if we apply the valid time shifting to increase the ensemble size for both the simulating radar and other mesosynoptic scale observations, it can actually improve the forecasts. We also found that we really need to take care of model bias errors in order to best utilize the advanced data simulation methods. And Sam DiGilia, our postdoc, is working on developing the capability to assimilate GO16 all-sky ABI radiances into RFS. And we actually developed an approach to assimilate the brightness temperature, the radiance efficiently following our direct radar reflective simulation approach. We found this approach is able to make the minimization of variational system very fast, improving the computational aspect of the DA system. And he found that assimilating ABI all sky radiances on top of the radar reflectivity observation can help spin up the supercell better. It can also analyze the cloud top in the strata stack as well. Okay, I mentioned we're super excited to transition our research into operations. In this slide, I'm just share briefly our most recent ongoing efforts for transitioning the research development of data summary into the NOAA operation system. This is under the UFS era. So collaborating with EMC, we help transition the 4D environment into the HAS version 1, which went to operation last month. There's ongoing efforts, collaboration with EMC Derek Klast and his team to transition the multi-scale DA into the GFS version 17. There's also ongoing efforts in collaboration with EMC GSL, basically the short-range weather team led by Jacob and Curtis to transition multi-scale data simulation into RFS version 1. And we're collaborating with the same team to transition direct radar reflectivity assimilation in EMR and ENCAP into RFS version 1 as well. So the last few years, the US and WP is going a transition of infrastructure for both the model and data simulation. It's very challenging for us as academics to transition both at the same time and still maintain the research productivity. So the strategy we used in the past couple of years is to transition the model first. So, and then recently we have begun to migrate our data system into the JEDI system and to perform our research. I'm just showing a slide briefly. We developed the data simulation prototype using JEDI for both the GFS, RFS, and this is just some increments plot showing the system is working. So the next few slides, I'm going to show a summary about the responses I received from the students and scientists in our group. This flow chart is to show again, the DA system. We are using data simulation to initialize the model, and the model we used to initialize the data as a background for data simulation. So you get an idea, okay, what part UFS will be used for our research. So the helpful aspects of the UFS model. So we found the end-to-end workflow provides a very good way to get to know the mechanism of running every model, including from pre-processing to post-processing. This is very useful for beginners. We found that GitHub is it's great for downloading the code, streamlining the updates, and extracting specific versions to coordinate with other groups. And the documentation online are also very helpful to compile or run the model, and especially for NOAA machines. And the nameless options are configurable. This allows us to tweak the list, name list that we want to use and select the physics dynamic options. We also perform gratitude tests for medium range weather application, and still found this is very useful for first time user and for a reference for further research and development. So we just began to work on JIDA for our research. So this slide summarizes some of the helpful aspects we think JIDA will provide for us. The first of all, the tutorial is very helpful. For example, it gives examples on how to use different capabilities, how to modify the code to add new observations, etc. It can also run in a variety of range of computing platforms like containers and up to HPCs. JEDI is model agnostic by design, so that means the same algorithm can be ported for different models and across different applications. What we're doing for global, for multi-skill approach, for example, can be used for regional, for example. This doesn't mean they have the same research question, but at least we can share the code. And GitHub is also found to be very useful for obtaining codes, updates, and for exchanging issues and solutions when we have runtime problems. Documentation is very helpful to get users started. Now is the wish list for the UFS. This is for the entire UFS, including both data simulation and the model. From research perspective, we're hoping we are going to have the workflow could be more customizable, so we can turn on and off a particular one as needed. We're hoping we could have a simplified research mode type of system, so we can test our ideas with a relatively simplified system. And overall, we'd like to see more flexibility, so we're able to test various research ideas. Support. So we like to see increased support for porting the system to newer HPC machines outside of NOAA, like from Taro, Anvil, etc. And we'd also like to.
About 2 minutes left.
Yeah, this is I think the last slides, or second to last. Establish mechanism to support various levels of questions. So there will be like level 1 type questions from beginners, new users. There will also be level 2 questions from developers. So how do we support all sorts of questions? For JIDA in particular, given we're all going to extensive migration from GSI to JIDA in the near future, we expect more extensive support when using JIDA will be needed. JIDA is actually different from GSI in various aspects. This may require a relatively steep learning curve, especially at the beginning. So support will be essential. Documentation communication. One of the group members mentioned that UFS can be constantly evolving. So it'll be difficult to track, the changes and why they're made. So they're hoping the information on new aspect can be documented, including why they're implemented. I think Sarah Lu also mentioned documentation, science documentation. So really for to do research, we want thorough documentation on all this aspect, including their meanings and purpose. This will allow us to understand, modify, and select more easily when we actually perform our research. I think this is my last slide. Thank you. Okay.
Thank you, Siobhan. So the next talk is by a pair of authors. Are they you both going to be up here in tag team mode? Or? Oh, okay. So Anyway, the two, I'll just say, Xue Wei is a postdoc, I guess, with the Joint Center for Satellite Data Assimilation, but also affiliated with University of Albany, State University of New York. And Dr. Ligier Bernadet, I pronounce it in the French way. Is it Bernadet or Bernadette? Okay. Anyway, we all know Bernadette Ligier. She's deputy chief at GSL of the Earth Prediction Advancement Division, and very involved with the UFS and applications and CCPP and all these other things. So we'll let them come up and talk about their experiences.
Okay, thank you. I'm just going to share my experience as a graduate student, and then also, I think basically it should be a graduate student, yeah. Because I just started my postdoc this June, so it's pretty much fresh, and then I attended the graduate student test before, and I also attended the COFES for this June, so I would like to share some experience about the COFES, and then give some feedback to EPIC, and to see if you can have a better, not really better, some room can improve, yeah. So basically, this June we joined the EPIC COFES, and then something I think pretty well is we can get better understanding about what kind of support be provided by EPIC. So especially in this COFES, we joined the report provided by Kevin. Is really helpful to prepare the payroll cast on AWS, and it always be good to learning new stuff, because like cloud computing stuff and then container stuff, because I didn't have any experience with this tool before, so it's kind of totally new things for me. But as attend EPIC, the COFES event, we actually feel something can be improved. The first thing is about we don't actually know what main goal for the EPIC for the COFES event. So, and actually, the COFES event was booked for a whole week, and then before the event starting, we didn't get any instruction or agenda to see to learn what should we prepare for the COFES. So it's somehow confusing. So it will be better if we can get some idea of what kind of thing we need to prepare for the COFES, this kind of event. And another thing is, I don't know how many people you have been brought the EPIC website. The website provides some tutorial videos to help you set up the AWS server, but there are multiple, probably like 4 videos, but for different people, you may need to, you may need to go through different videos to get an idea of which one is the best for your needs. But at the end, for the COFES event, I just learned, okay, the most useful video is the video provided by Kevin, actually, yeah. So that's, among the 4 videos, we only need 1 video to set up our AWS payroll cluster to use the UFS and use the AWS. And then another thing is, because I think not many people are not everyone familiar with the AWS components. So for me, that's the first time I joined I learned the AWS. So like, what is the image means, what is instance mean, and what is a handle means, makes no sense for me. I don't know I have no idea about this. So it's very difficult for me to pick up the AWS to learn how to work with the AWS. So that would be good if we can get some better instruction about how each component within the AWS working together. Yeah. So that's also some my feedback. I just mentioned some feedback. So, but basically, for my first point of feedback is if we would like, for any users who would like to learn how to run UFS, the best way probably the graduate student test will be more effective, which will be the usability test later on. Yeah. And then another thing I'm thinking of is the documentation. Is mentioned many times this week already. Yeah, mentioned by Sarah yesterday, and also by the previous by Shiguang and previous presentations. So we don't. The documentation is very informative, but for any new user coming to the UFS community, we don't know. Beyond the quick start user guide, when we want to change anything or we want to have some flexibility, we don't know where to find the flexibility or where is the option for us to choose. So it's somehow difficult to find a keyword or something to go through the whole probably 30 pages, 30 sections or more than 30 sections in the UFS the documentation website. So I do think probably the better way to document probably is like for entry level, for any like a rookie user, you can just provide the basic information, and then for more developers, like Shiguang just mentioned, for the senior people or for more experienced developer, you can have a more documentation or more detailed documentation for them. And then the last point I put over here is for our university cluster to configure it as a UFS environment is quite difficult. So because we don't have a library ready for the UFS, so we need IT people to support us to install the library. So for that kind of university cluster, we may need to have a more collaboration with the EPIC Center to get more support from that. And then here is just, I just want to share some idea from my personal viewpoint. So basically, I feel for any users within the UFS community, you can consider there are in the 4 levels. So for the beginner, probably everyone can check out the code and then run in the UFS application. But later on, for the first level, the first 2 levels, the bottom 2 levels, the new user can easily to check out the code and run the UFS application. And then if they would like to have any new features into the UFS, they can easily to find the code and to know where to modify the code to make a change. So it's, for these 2 levels, I feel it's relatively easy and more straightforward. However, if you go to the next 2 levels, like you would like to add some features in the workflow, like I just mentioned, we don't know where is the flexibility. So for that kind of purpose, we don't, you need, for this kind of level, that users need to know get better understanding for the workflow. So workflow right now, I have experience with global workflow, so it's it's very, very complicated and a lot of components inside and very many layers. So you cannot just change one simple variable within the lower level scripts and to expect to have changes on your result. You need to, from the top level, to go through all the scripts you have in the global workflow. So the flexibility, like Shiguang mentioned before, the flexibility for the workflow will be needed. And then I think most of the people will now go to the level 1 to contribute the UFS their new features into UFS community repository, because I think it's not required. We can add any kind of feature we want, but it's not necessary to contribute to the UFS community. So unless you have, you would like to see the difference or make some changes to the UFS code, but how to encourage those people or stimulate these changes into a US repository should be the one question we need to consider for the UFS community. So I leave it over here, so Lidra will continue.
Yeah.
To the discussion, I just wanted to add a few more words here. One is to let you all, okay. Let you all know that a group of us from the DTC in collaboration with EPIC have been working on a white paper about hierarchical system development. And what we mean by that is those aspects of simplified testing and simplified workflow that Christiane and the other panelists talked about. So this well, or you can ask me later or get the slides. Anyway, in this paper we summarize what the needs are, the existing tools to our ability of knowing what they are. We had a community survey in which we prioritized them and we assessed level of effort to bring them into the UFS fold and support them. So the stage this is at is that DTC and EPIC folks are now discussing this paper, make sure everybody understands what's there, and EPIC will be determining the next steps in terms of funding the development of some of these efforts. And then another topic here, just wanted to add some additional thoughts about lowering the barrier of entry for those that are new to the UFS community. And I think there's two things that are important. One is the ability for everyone everywhere to run simple cases out of the box. So I think several of the previous panelists talked about we need to have easy documentation, including all the requirements, steps, and expected data sets, outputs of the tests, and that should be part of the public releases. So it needs to be, easy for someone to pick up and run. But another aspect is that there has to be a mechanism to collect feedback. So much like Shu Guang just issued this survey to her own students, we need to be issuing surveys to the larger community here to see if when they try to run the UFS, try to run this out-of-the-box test, do they find it feasible? Are there big hurdles? Can they run in a timely manner, or it takes them days to get it set up? So in the previous UFS releases, like short-range weather app on the left and medium-range on the right, we had something called the GST, or Graduate Student Test. So as part of this GST, we distributed some cases. So here on the left, for the short-range weather, the test involved instructions to install, run, and compare both the app run with different horizontal resolutions and different physics suites. And on the right, we have an example of what was distributed with the medium range weather, which was out-of-the-box capability to install, run, and then compare runs, forecasts of cloud cover using different CCN concentrations. So those were some very simple instructions. And out of those instructions, we were able to collect this kind of feedback that's displayed here. So this is just a sample of the type of feedback we got. So the different lines are questions that were asked. There were other questions. This is just a sample. For example, did you feel you need additional documentation? Did you find it easy to understand the configuration? Did you find the code was easy to get? Were you able to run without trouble? And did you find the code easy to modify? And then the folks would say what they agree with, what they do not agree with. The numbers inside the circles are the number of people that answered in each category. So we actually did good in those first graduate student tests in the sense of, most of the participants found that the code was easy to get and not so hard to set up. So this is the kind of feedback we need to continue gathering. So the post-mortem of this GST, in my opinion, is that, we were able to create this out-of-the-box capability and reach everybody. Even Neil was able to run in his laptop, he says. And it provided a very valuable way to collect feedback from the community. The main limitations was that, at that time, it was a very manual process, so required someone like a subject matter expert to sit down with the student and, help administer the test, and it wasn't maintained. So it kind of, over time, did not continue. So going forward, I think there's a strong need to put a strong focus on having this out-of-the-box capability for the various applications. And then there was a lot of, people didn't like this name GST, Graduate Student Test, because the tests were applicable to graduate students, but also undergraduate and other students, as well as other types of professionals. And we want to use this capability both to get the out-of-the-box capability out there and gather feedback. Now, EPIC now has, at least as part of the short-range weather workflow, this workflow end-to-end tests. And this is a capability that can potentially build on in terms of using this not just to, as it's used today, to test new innovations and see if they're not breaking existing capabilities, but also to gather feedback to see if new users can use the workflow and if they're having any problems and hurdles. So part of the question here, for the discussion is like, is this enough, or what do we need to ensure success to lower the barrier of entry for the UFS? So with that, I guess we're gonna move to the next part of this event here today. I'll be moderating the panel, so I'm going to invite the panel participants to come up to here. So Luke and, well, Shugwang will have to join remotely.
Yeah, I just want to thank you and everyone else, and I'm going to get out. So
okay.
Thank all the speakers.
Yeah.
And it's great to get all the feedback from the actual users. So
yeah, thank you.
Appreciate the first 4 talks and looking forward to this.
Okay, thank you. So Shuguang is there. So Luke and Christiane and Shiwei, I welcome you to come up, as well as Sarah Lu, who joined us as a panelist. And I also like to invite our chair, Enrique Alves, from the EPIC Program Office, to join us. So this is your opportunity to ask questions. We have 2 microphones in the room. One is here, the other is there. Online participants can also ask questions. And I think Aaron back there is going to read us if we have any questions for the panel. So, does anybody have any questions to begin? Danae, are you running away or going to the microphone? Okay.
All right, so Danae Carlos in SSL. So one of the things that I feel that we were missing in the start of this meeting is kind of almost setting the scene for EPIC and some of the accomplishments or the work that's been done since the last meeting of last year. I see a lot of it in some of the presentations, but I feel like we haven't really talked about the progress that we've made over the last year, and I'm trying to see if I can get a little bit of that out of this particular panel.
Okay, yeah, thank you, Danae. I think, yeah, it's hard to have all the presentations in the first day. So tomorrow there is a presentation by David Huber of EPIC talking about some of the user support capabilities that have been spun up. But until tomorrow, Enrique, maybe since you are part of EPIC, would you like to take that on? There is a button there you need to press when you want to speak. So then the light should come on.
Can you hear me? Okay. I think that in this situation, perhaps the question it's a multifaceted question, right? So you have different parts of EPIC. So you have the contractor, you have the program. So I'd like actually to invite, this is an open discussion. It's informal. Anybody can stand up, anybody can make questions, anybody can participate. And since we have Maui Huang, our program manager here, I think that she would be in a better position to provide that answer. So I'd like to invite Maui, if you'd like to get one of the microphones and provide that. And then again, maybe it could be an opportunity for somebody from the EPIC contract as well. I see Kevin is here to provide an overview and answer that question. Do you think that would be satisfactory for you, Danae? Okay, so if Maui, if you feel comfortable with that, I would like to invite you to provide some feedback to Danae.
So, thanks, Danae, for putting me on the spot. I wasn't prepared to speak to it, but I want to just reiterate some points that Dorothy provided in her opening remarks on Monday. Those are at a very high level. I will just summarize them in three high-level items. One is building the community. If you look at the EPIC strategic implementation plan, which we haven't released, sorry, we're actually gonna focus on three high-level activities. One is to build the community. This workshop itself is a community building exercise. We also try to reach out to working with UFS steering committee as well as NOAA modeling team to make sure we understand all the stakeholder requirements and inputs and making sure that we find out a way to implement them. It's not that easy to consolidate all the inputs, but we are making progress. Right? So that's one of the aspects we have been focusing on in the past year. The second thing is that in the past year, we are trying to focus more on the short-range weather application, working very closely with DTC and GSL. And we actually released two SRW versions. One is SRW 2.0, another one is SRW 2.1. And as well as focusing on working with the land modeling working group to release a land DA system, which some of you might have participated in our earlier training sessions. So this, but I agree with some of the panelists because EPIC is largely engineering program from my perspective, in addition to some of the community building activities. We actually have some difficulties in clearly articulate exactly what those capability work we need to do from our end, working closely with you to clarify the engineering purpose, the scientific purpose of the engineering development. Right, so that's the second thing. And actually, when we started supporting both land DA and short-range weather applications, the intention is actually to make sure we have an end-to-end system that can be released to the community, not only including the infrastructure, including how to run it, providing the tutorials, as well as to release it with data set and use cases so that people know how to replicate it. I would welcome you to the hierarchical system development presentation that Mike Hack will give later this week to better understand that approach. And as Nija mentioned, we worked closely with DTC to develop that concept, but that needs some additional thinking and support in the future. And the third activity is actually to, let me think. To have a way to make sure we have a way to demonstrate how we bring in innovation into UFS. And that should be built on infrastructure, right? So if we don't have the sound infrastructure, it will be hard for us to demonstrate that point. So again, we worked closely with the short-range weather application team and DTC to building some of the matrix, the forecast scale matrix, into the SRW application as well as the land DA system. That one was recently delivered to the program office just 1 week ago. So a lot of you have never seen that, but the purpose there is that in the end, we want to provide a dashboard. So if you grab a EPIC configuration, you should be able to grab a use case and then look at how much improvement you could have by changing a physics parameterization or changing some of the DA configurations in the future. Well, the DA component is yet to be discussed. But those are the 3 components we have been focusing on in the last year. I'm sorry I don't have any slides to show you, but I would welcome my team to provide additional inputs if they are willing to.
Thank you, Maui, and I hope I still have my job after putting you on the spot. And I have more people that I'd like to put on the spot here, but I'll leave that for a little bit later. I'd like to invite, before actually your question, if you don't mind, just for continuity of this topic, to have Kevin step up and just provide some additional comments from the EPIC contractor side.
Sure. Yeah, thanks for the question. I'll be pretty brief. I think Maui pretty much hit all the areas. But to answer your question, I think the one thing that we've really worked on is transparency. I think that's really the last item she hit with the community dashboard is how do we really make this easy to see so that as you make changes, as things go through pipelines and all the infrastructure that you can't see behind the scenes, what does it really look like to be transparent to the community? And that's kind of what we spent a lot of time on working on lately is really to hit that home so that question doesn't have to be asked in the future. Everything's right out there in the open. To include the biggest question we get asked, is at a lot of our code fests and hackathons is how do I do this on my own? So some of the team members, have ways that they create, you can create all the infrastructure on any of the 3 cloud service providers in about 7 lines of code. So that's a really transparent way that anybody can take these applications on their own and build them out pretty easily. So thanks.
All right. Thank you very much, Kevin. So we'll go to a question, Phil Pajan, and then we'll check the online.
Thanks. Phil Pajan from NOAA's Physical Science Laboratory. And there's all this talk about the UFS, the Unified Forecast System, and it seems like a lot of times it's just viewed as the model, and a forecast system is more than just the model. There's data simulation, there's product generation, all that. And Luke, you touched on this in your talk about the data simulation. That's not a community-developed model. It's behind a firewall, and that's, I think, a big hindrance on building a unified forecast system. And I want to get your perspective, and then put Tom on the spot on what are the barriers to making that a community system.
Yeah, I can touch on some of that and kind of go back to Danae's comment on the progress of EPIC. I think the progress of EPIC has been very beneficial, not so much to us because we are extremely, and I will speak for the people that work with me, not myself, extremely advanced users of the UFS infrastructure. We don't need a graduate student test. We don't need an example of how to run on AWS. We've been doing it for decades collectively. So we're highly advanced users. We can get around these barriers. It just takes time. So we have to do additional development. We have to build things that don't exist or build things that are behind a firewall that we don't have access to. So we have a lot of really talented people that can just build it. So really the hindrance just adds time. There's nothing that's unknown for us. We just have to build it if it's not available to us, or if we don't have the documentation, we have to just figure it out. But yeah, so I don't know if that kind of answered the question on EPIC progress. And in addition to the EPIC progress, we have a lot of some of our scientists and engineers are actually on the EPIC contract, working under Raytheon, contributing our kind of expertise back to the EPIC program. So I think once EPIC becomes more mature to the point that we can really dynamically use the software, the code, and contribute back, I think that's when somebody like Tomorrow.io can actually really benefit from EPIC, and the overall community can benefit from us. But it's too early, I think, for that level. Did I adequately answer your question? I feel like I kind of answered 2 and gave you only half partial answer.
Not fully, but it was sort of getting your perspective, and even like Shuguang, I'd like to hear your perspective on the DA, because that is, it is behind a firewall, and you don't have full access to it. And is that a hindrance for your work?
Right. So so far, because we have been working as a developer data simulation, so that means we already have who are developing the Malaysia itself. So talking about GSI, we are not having that problem at all. So I guess you're talking about JEDI, Phil. Is that what you're asking for?
Yeah, it's because JEDI, so the UFS is this focus on being a community model, and JEDI doesn't have that charge. And I was saying, is that a problem?
Yeah, we just started use JEDI for our work. I think one thing that related to what you're talking about, there seems to be a public version versus like an internal development version. I think for public version, we can access very well. An internal developer version, we do have to ask people, that's, to the close developer to have access. And yeah, I think having direct access to this system, transparency and direct access will be very helpful for everybody to be able to access the system and put the efforts on the development and translate, get our own development into the system. Yeah.
All right, thank you, Shu Guang. We're going to give the opportunity to Tom Alinier to say a few words.
Thank you. I'd like to correct the idea that the DA system is behind. Our code is open source. It's actually available to the community. We have more than 1 million lines of code available to the community. We did 5 public releases this year with UFS atmosphere, aerosols, land, marine. And that's all available online on our website, jcsda.org. So all the code is available. And on top of these releases that are done quarterly, you have direct access to the latest version of the develop within seconds. So basically, you have access to all the JEDI code for these releases in real time. So the piece that's still behind internal is actually the agile boards, and this is actually a discussion we're having with our board, multi-partner boards, with multi-agency boards. So that's the part that's actually internal.
You said you are having discussions on making that available, not internal. Oh, great. Good.
All right, thank you, Tom. Let's see, is there any question online? No, okay, so Jillian, go ahead.
Hello. I'm short, gotta adjust. So I have a lot of thoughts about all of this, but I think first to address Danae's question about some of the new developments that have been happening with EPIC in the past year, 6 months. I will say I work on the AUS team, which is the Advanced User Support team. And although things were a bit slow to get started, we're really trying to work on transparency in terms of providing user support in a timely fashion. And we're using GitHub discussions primarily for that. So if you or your students or anyone else really is working with UFS repositories that EPIC manages or supports, you can post in the discussions. So I will say, to be clear, that's the SRW, UPP, LandDA, and the UFS weather model. So for those 4, we have more support. For other repositories, you can post on UFS community discussions, and we will try and get you the support. But that, for a while, I think wasn't getting enough attention, and now we're really putting a focus there. So I would highly encourage you to use that functionality. We're also trying to, we've added EPIC support requested labels for issues. If you're not able to add labels yourself on GitHub, you can request that when you create an issue. So you'd create an issue if there's a feature that you want to see or that your students want to see. We can't guarantee it'll happen right away, but we can put it in the queue and we can forward it to the right people. And I think that's been a huge issue with UFS is I'm hearing so many of the same issues from everyone in academia, and it sounds like nobody really knows quite how to get those into the queue so that they can get some attention. So I also highly encourage creating issues. And then I guess because it seems like there are some shared issues, I'm wondering, there's like the system architecture working group. There's a bunch of working groups. Is there a working group for academics who are in climate modeling of any kind? Because I feel like it would be good for us to be in touch with some sort of organized group of academics who are working on UFS-related topics, so that we can figure out what needs prioritizing and how we can help better. There's my question.
Yeah, that was a great comment and question. So thank you, Julian. I think at some point it might be worth it to do a demo during this workshop about how to post on GitHub discussions, because while we may think it's trivial, people just don't know where it is. So,
Yeah.
and I was looking in the SRW app users guide, and I think it's like several pages in when we get to the information of how to get help. So I think we're gonna have to move that
I'm
up.
also reorganizing the user's
But
guide.
I'm gonna pass it to the panelists, but I thought maybe I could start with Shu Guang. So Shu Guang, you are one of the co-leads of the UFS release team. And so you kind of represent the community, you know, the group that Julian's talking about in terms of how releases are used. So can you talk a little bit about how can we collect this input? How can we be more in touch with the academic community? And, you know, Sarah, Luke can also help us with that.
Just have a survey like what I did and you did, and send it out and engage them to provide inputs. I think that will be one of the efficient ways. Yeah, I felt like that's very efficient. So that's what I did with my group. You hear them directly.
I guess one concern is we don't necessarily know who to send the surveys out to. You know, now that I'm seeing you all here, I know that you are professors that we could be in touch with, but we don't necessarily know the full extent. So I'm not sure. It seems like there's sort of a communication gap and knowledge gap there. Because I agree, the surveys would be fantastic.
But I think one approach is I think you want to find a mechanism to keep track who is actually using the UFS, right? And I think there should be a way of doing that, right? I'm not sure GitHub download have a functionality like that to allow you to track the users. Once you have that database for users, I think you should be able to send your survey to those people and ask for inputs or feedbacks.
Okay, let's see if there's anybody else on the panel that wants to comment.
So I guess the verification workshop there's a workshop couple years twice, and then you know you have initially reached a certain group, but for example there's one area is on air quality, so we specifically reach out to end user. So sometimes you have to build stuff on somewhere from wherever you know, but you know there's a gap there, right? So for verification metrics workshop, then I specifically reach out to air quality focused people, ask them to provide feedback. So you need to almost proactive reach out to those potential end user, and also I think UFS a working group, but if the working group is more with people already work on development and already funded by UFS, it's difficult to grow the community. So then you have to open up, so to have new idea. Then working group cannot be only those people already ongoing. Yeah.
Okay. All right. So we move on. Neil, are you online or fine? And you probably have your own questions you want to pose, but if you also want to speak to Danae's question about the progress of EPIC, that would be great.
Well, I was actually going to address what was just being talked about, because I think this is actually really timely. So I did want to point out that Alekia has been working on this as a La Penta intern, but we just, so we being UCAR CPAS, just hired a person a couple days ago. They haven't started yet. She was here yesterday and last night. Her name's Allison Gregory, and she's going to be working with me specifically doing outreach coordination to mostly the academic stakeholders. So what we're going to be doing is trying to get the input from the users of what they want to see in the UFS. So whether it's doing surveys, and her background is a mix of atmospheric science and social science, and I think she's going to be really awesome at this. So this, to me, getting this feedback is essential, because I hear this a lot from people that do the graduate student test. They're like, this is really cool. I could run the entire model, but really for the purposes of a teaching tool, simplified, idealized cases are way more useful. And so for what you can get with CSM, I'd love to see that as part of a way to engage the academic sector. But you know, really when EPIC first was initiated, the point was taking the production code and putting it out into the public. And no one at NCO is using that kind of stuff in their model because they have a total different mission. But it needs to be in there if we're going to engage the full community. So this information is super important. I just wanted to let everyone know that we're aware of it. We've hired a person. Their full-time job is basically going to be reaching out to the universities and getting input and feedback on what you want to see in the next releases as far as how you want to use it both as a research tool and a teaching tool.
All right, well, thank you. Go ahead, Danae.
Yeah, so I just want to piggyback a little bit on Phil's question, and you know, when I listen to some of the speakers and they talk about using JEDI, I really don't know what that really means exactly, you know, because at some level we've been talking about using the use of JEDI as the next generation DA system for several years, but I feel like we're all over the place as it pertains to the use of the actual system, you know. And so I'm just kind of wondering, you know, and Luke, you talked about you have the talented people that can kind of get around some of the barriers with regards to some of the modeling capabilities that are out there, but everybody doesn't have that. And you know, as a community, how can we be more transparent about where we are in our kind of research and development process, the R2O process at the kind of end of the day? Because that to me is where the community can actually benefit.
Okay, Luke?
Right, so what does it mean for us to use JEDI? It's fundamentally the data assimilation system that we use to ingest observations in real time. We're not doing research, we're doing operational forecasting. So it's the observation quality control, data ingest, real-time data ingest, forward operators, you know, that are basically translating the observations into the model state, the entire workflow. There's some workflow elements that come with JEDI that we are using, but it's not robust enough for us to be cloud agnostic and things like that. So we take all of the pieces from JEDI that we need, forward operators, just the fundamental pieces of data assimilation, background error covariance that we're generating, the spectral coefficient generator for our passive sounders. We're using a lot of those components. Some of those aren't fully released. So some of the development that's behind what we've been calling a firewall, we have to get around that, you know, those elements as well. So really it's just making the entire data assimilation system operational. We use what's available, we build what's not available, and we operationalize.
Sarah?
So, Dina, I guess Tom can answer a lot of your question, but at least the JEDI have a lot of different elements. So for us, you know, Siwa and I, we have a project because JEDI is a DA system, really know how to map observation data to model data to observation space. So we actually couple that with Map+, which is for verification purpose. So in addition to be a DA system, there's a lot of very nice science element can be used for different application.
So Luke, you just said you guys are operational with JEDI.
Well, I
think you're the first person I've ever heard say that.
We are building an operational system with JEDI, and we're doing it because we have utmost trust in Tom's team that it's going to become the next generation data assimilation system in the US and UK Met Office. We don't want to invest time in working on a legacy system that's GSI if this is going to become the next generation. So we made the choice, assuming that JEDI will become operational in the community, but we may be the first to truly operationalize it, I guess. But yeah, maybe it's ambitious.
I wonder who else has it operational. Any other organization in here? Other than JCSDA?
So I get your point. There's a need for more communication on the status and the development that's happening, and I'll invite you to my presentation in the system architecture parallel session, where I'll actually show a high-level summary of this. 2 months ago, we also had a joint center workshop. If you want to dive in, if the high-level status is not enough, there's a lot more. So we had, dozens of presentations about JEDI developments, about JEDI status, about the transition plans from all the partner agencies and line offices in NOAA. So there's a lot of material. The recordings are available. The presentations are available. I can point you to that, and I invite everyone who's interested to come to me if you need.
I only asked that question because everybody, it feels like we're waiting. So if we shouldn't be waiting, then why we're doing something wrong.
So we have hundreds of people in NOAA and NASA and Air Force and Navy and Met Office who are not waiting, who are actively working on developing the best system in the world.
All right. So we'll have to come to Tom's talk and learn more about this. Meanwhile, we'll go for a question from online.
Yeah, we're going to sidetrack from JEDI for a second, but this question is from Stuart Young. How significant is runtime prediction and compute environment or optimization for different data sets and algorithms for research and production?
All right. Anybody want to raise their hand? I mean, I think there was some discussion before about the code being, there being some barriers to install outside of the NOAA Tier 1 platform. So any comment on that?
I mentioned that yesterday. She will also mention for us to put on our cluster is some issue. But beyond that, for research application, a lot of times it's platform dependent. And it will be unrealistic for me to expect EPIC tell us how to run our machine. So that means we need to work with our university IT people. But guidance about what is needed and what's the minimum requirement, what's nice to have, that kind of information can help us to get started. So then, but a lot of times, the optimized code, whatever is really local, because each machine is different, and only the user really know. So that's my point. I don't know if Shuai seems to add.
Yeah, I just want to add one thing is Fridays we will have Christian's had his presentation about how he run the UFS code, and he's running on Cheyenne, which is supported by the UFS community. But I think he still need to figure out how to specify the layout for the UFS code and the work collector time to optimize his code running on the Cheyenne. So it will become the same issue with the university cluster, because some like our cluster, we actually have an Intel compiler, but that's the 2015 version, pretty old. So we actually cannot install the updated library for the UFS. So that kind of support we need to work through with our ITs. So I think that basically that's the difficulties we face on our university clusters. Yeah.
All right. I'm going to keep moving. Louisa?
Can I respond to that last question too?
I was going to change the topic slightly. So I hear everything everybody wants and needs in order to engage with UFS. And we're trying to really support a really broad range of community. And so I just wanted to say that community. So while EPIC can provide a lot of capabilities, they've got talented software engineers and all that kind of stuff, I think other community models have relied on community development going back in. And I think about some of the needs for more idealized capabilities, and I think about HWARF when DTC was supporting that. We actually had graduate students who developed some idealized capabilities, and DTC supported those getting back into the repository. So as we advance as a community, if everybody can provide what they're developing for their release, for their research back into the repositories and be able to get those things supported out to the community, then we're all going to be able to grow and advance a lot more quickly instead of maybe totally relying on one group to do everything, because we're going to be waiting a long time if we're relying on one group to do everything. So just a thought to think about from that perspective.
Yeah, thank you, Luisa. I think this is really important. I think there's not going to be like a one system push button GUI that's going to execute all the, all possible idealized cases. So perhaps EPIC can play a role into being, a distributor, documenter, and supporter, but there has to be contributions coming. So, Christiane.
Yeah, good point, Luisa. And I briefly mentioned that we have a couple of examples already in DTC, with the physics, for the single column physics model that's based on the UFS. And then we have these examples from GFDL, the solo model, and we have the CSM examples. So I think we do need a facilitator at this point because we already have pieces, and I think we're all happy to contribute, but we don't quite know how. I think that's really the point that we should tackle.
I could quickly comment on that as well. I think there's a lot of components that you can, I don't understand this thing, lights on, I'll just leave it alone, that you can contribute. Workflow elements, like research packages where it does, some certain set of research on a use case or something like that. You can contribute that to just a general repository. But contributing back to the operational code, or what I imagine is if we try to contribute model physics contributions back, we're going to have branch nightmare. We're going to have all these branches from different organizations, and then NOAA's going to be left with, EMC's going to be left with, well, what's the operational branch, and how do we merge those contributions in? But all the peripheral elements, workflows and validation and stuff like that, I could see just a pool like NCAR does for WRF, like WRF tools, a bunch of shell scripts and examples on how to do workflows and do some simple experiments and validation. I think that could be something we can all contribute to right now, but it has to be like a separate bucket of tools versus like the actual main branch, because we're going to have branch nightmare if we allow the community to start contributing. I just don't know how that, that's maybe for Neil to think about or comment on how to handle branch nightmare once we get community contributions back on the core science.
All right, thank you. Yeah, Sarah Lou?
I guess the intent to contribute back, and I'd like to raise a potential issue could be the code was designed for research and operation, and there's certain operational constraint that could potentially cause a barrier. For example, we had an ongoing project to do land surface evaluation, and then we want to implement some prognostic process level diagnosis in the model. So the key is if we want to put a post-processing, and if that's a new field, it's not defined group 2 table, then there will be practical difficulty there now. And then we have project work on Make Plus, and then students, if they do certain Python, certain module may not be allowed by NCO, then will be also potential issue. So when you want to contribute, and there's some kind of information about, well, there's certain thing you had no chance, let us know so we can avoid. Yeah. So.
Okay, well, thank you. Hendrik, you're next.
Since the original question had embedded in that something about efficiency and runtime and what the difference was for operations and for research. Well, our operations machine at the end of life cycle, and actually pretty quick in there, are used at the 80 or 90% level of capacity. And so if you have something new that you want to put into operation that's 10% more expensive than was planned for, well, tough luck, it's not going to get in. We don't have a big enough machine. On research, of course, there's a lot more play there, but as a researcher, if you have a code that's twice as fast, you can do the research for half the cost of compute, or you can do twice as much runs. What would you like? And so, having said that, if you were lucky enough to be coding on supercomputers in the late 1990s, the Cray C90s, our operational codes could get anywhere between 30 to 60% of the peak performance of the CPUs. Some of our codes were running more than 50% of peak performance. In their new data center in Italy, the European Center is expecting and apparently going to accept 2.5% of the nominal peak performance of the CPUs. So slowly but surely, people who have worked for a long time in this field have gone from really using our CPUs to using only a really small fraction from it. Now, I'm not saying that we can go back to 50, 60%, because there are reasons why our type of problem doesn't scale very well on the new CPUs, but having that small a fraction of a CPU that you use, you actually have runway to perhaps make the code 2 or 3 times as efficient. And from an operational perspective, if we buy, say, this is a fake number, but if you say I spent the 25 million a year on computing, I could spend $5 or $10 million on just code optimization. If I get my code twice as expensive, I get back 25 million a year in terms of not buying compute anymore. And so this is really a unique time that, since we are all working with the same code, more with the same codes and the same infrastructure, that if we can figure out a way of investing in making these codes portable and a little bit more efficient, it's worthwhile to put some real money in there, and the payback for everybody is going to be incredible.
So Hendrik, before you actually leave, I think that Luki touched on a point that I think is very important, like kind of like coming back to the focus of the panel, which is, you know, how to make the UFS more usable for a bunch of people in the community. And he mentioned the idea of branching nightmare. And I know, as myself, I was code manager for the WaveWatch 3 model. We had substantial contribution from the community, and we managed to avoid branching nightmare. Of course, the WaveWatch 3 model is a much simpler model compared to the UFS system as a whole. But I wanted to ask you specifically, because I think it's so fundamental. You know, one of the big payouts for community wanting to contribute to code is to see their contributions making their way to operations. And reversely, having a functional flow of contributions from the community is really an open door to innovations, right? So that's where perhaps the more radical innovations may come from, may not. So I wanted to ask you, going back to this idea of branching nightmare, and since Luke also mentioned Neil in that, what are your thoughts, just briefly? Is that something that concerns you? Do you have in mind a way to avoid that from happening?
No, yes, and what was the other one? So, yeah, wave modeling, the model is not simple, but the community is smaller. And so, smaller community, less branches. And so, but you have to look at it from both sides. Wave model has about 5,000 to 6,000 users, but about 20 or so real contributors. So it's a small group, and so I have experience with that. I use that to sell the UFS over the years, but I'll be first to say that I don't know if I have economy of scale here. I don't know if that still will work if I have a much bigger community. The biggest issue that we found, and that's Arun and that's Enrique and a few others that have worked on the wave model for many years, it is a culture problem. Because it is a problem where you have to get the people to do the right way of working with it. So having branches that are about one topic, not about a person or an organization, keeping these things, well, I'll keep it short. Things like Git flow. What I've seen, this is a culture problem, at least in the wave model, more than anything else, because everybody, including Enrique, including Arun, started off with saying, I don't want to do all the extra work. And everybody in this community, every last person, including the top scientists in Europe, were going, once they were going with Git flow and doing clean working on the branches, keeping them up to date, merging them back when you needed to, everybody said, oh man, I should have done this way earlier. And so I don't know if my experience from the wave model will translate to the bigger scale, but I do know it's a culture issue that gets in the way first. If we can get over the culture issue, we'll see whether it works for the bigger scale.
Thank you so much, Hendrik. You definitely have a lot of experience with their Wave Watch, and that's been very successful. We only have 8 minutes to go, so we're going to go to Natalie and then a question online.
Hi, my question is to the academic community. For now, I know many of the academic community do use like shared systems such as Orion, and spread it to a wider community may be dependent on the installation of software dependencies. That's another hell. So I wonder if wider use of containers might solve this problem, because most of the HPC systems, if not all, they are Unix, Linux based, and this is something we may put more efforts to in order to make it available to
All right, so
users.
is there one of the panelists from the academic community that want to take that on? Christiane?
Yeah, I think that's a good idea. And I think we need a little bit more education in the academic community, how to use containers, how to work with them. I think that's a barrier. It's not the idea. I think the idea of containers is making a lot of progress. Also, I hear that the move to the spec library management will actually do its wonders in the near future. So I think things are improving on that side. But I think you're right. This is one of the biggest barriers, and it was mentioned also by the other panelists that if the model isn't portable, we are kind of lost a little bit because our university servers will not support it. I think I got around that a little bit with Cheyenne. I do see that problem though for the academic community on Cheyenne, which is the NCORE system, that we are not able to apply for computing resources for the UFS unless we are NSF funded, and that's probably not quite the case yet. So that's a barrier. Also, if we want to go to maybe Frontera or Access systems, these are kind of the widely available clusters. We probably need to get more help from the UFS community or EPIC community to get the libraries installed. I hope there's progress, but in the near term, and containers are a good idea forward. Yeah.
And I just want to add one comment. My personal experience with our cluster again. So using container, I can install and compile the UFS, but the requirement for in the slides or the tutorial slides said we need a Locata workflow and then slurry system to do the job management. So for our cluster, we have the slurry system, but we don't have Locata. So I try to install Locata, but then Locata needs the Ruby as a library, but our Ruby is outdated, so I cannot install Locata. So that becomes some other issues exposed. But I mean, I know that on the documentation there's some we can go around the Locata-based workflow, but we need to manually to execute the shell scripts, but that's not recommended by the tutorial slides, so that's another issue I faced during using the container on our cluster.
Thank you so much, Shui. We're going to go to a question online.
Yeah, this question is from John Potterjoy. In response to previous questions, does the committee feel that more support is needed to accelerate the transfer of DA science from academia into JEDI? For example, the DTC used to provide a level of developer support for GSI.
Okay, thank you for that question. So Shuang, maybe you want to start us?
Yeah, having more support is actually one of the wish lists actually supplied by the students and society in our group. So I think it is critical to have sufficient support from wherever EPIC or GCSD or others, as we all trying now migrate to JEDI and to do the actual data submission research development. I think this support will be critical. I think in my talk I also outlined how we're gonna establish an effective mechanism for effective support. You may actually have various questions, some of just from like earlier users, beginners, and some actually may be coming from an experienced data submission developer, but they are, when they do development, they have questions on the source code, for example, for a particular solver, And this is a deeper question. So I think we should think about what we can do to support these different level questions. Who is responsible for supporting what kind of questions? I think, I think this is something we should talk about in this workshop.
Thank you, Shuguang. In the interest of time, so we have three minutes left. I'll give a question to Christina. We'll get some answer. And Neil, if you have some closing words, we'll do that.
A comment that Hendrik made there, he was talking about it being a cultural problem for a branching nightmare to happen. I totally agree with that. And I think that that cultural problem has been born out of a little bit of distrust of code coming into a code base that is meant to be operational at NCO and all of the reliability that that requires and the timing and all of that. And I think one way that we can start to both apply the Git flow pattern that he was talking about and also regain some of that trust is through really robust testing. And that's one space that we're starting to get into now that I think we really can use both on the trust side of this cultural issue to make sure that we're only accepting the best code into our code bases, but also it's a documentation of the code. We don't want to forget that tests give us examples of how to run. So in short-range weather, for example, we have about 80 workflow end-to-end configurations that we test a subset of, but that's 80 different examples of configuration files that you can use for a variety of different purposes that we want to make sure work every time we accept a new code to the base. So those are your examples of how to change different physics, how to change different domains, and how to run an ensemble in a variety of different ways. So I don't want us to forget about the testing frameworks that we're incorporating into these systems as both documentation, examples, and that sort of thing, but as well as building that trust in the community in the code base. Thanks.
I just have a 30-second comment on top of that. That was exactly the mechanism that WaveWatch 3 used to build trust. So one of the first things that Hendrik did way back, maybe 50, 60 years ago, when he was developing WaveWatch 3 with us, was to write a matrix, which we called Hendrik's matrix or something like that maybe I can't repeat here. And it would run all the regression tests available for running WaveWatch 3. And it was made so easy for any user or developer to, just release that thing, leave it running overnight. It built the trust, and it did change culture. So, I think we're on the same page. And I'll pass it on to Neil.
Yeah, thank you, Enrique. That guy says he's going to turn the lights off on us here anytime. So go ahead, Neil.
I'll keep it short. So I just wanted to bring up the fact that while we're talking about these needs and wants, that NOAA or any other government agency is not going to do anything without congressional authorization and appropriated money to pay for it. And so this message is actually mostly for the academic folks, but probably industry too. The time right now is really important because the Weather Act reauthorization, so the original Weather Act of 2017 is going to be, the reauthorization is going to get introduced this year. And it's usually every 5 years. So if you haven't, and I know there's been some drafts floating around, someone posted it on a map listserv at one point. If you haven't gotten your comments, requests, needs, and wants in to your members, you're about to miss the boat. And it won't come up again until probably 2030. And so it's really, really important. If your needs and wants are in there and you like what the language in the draft bill has to say, then have your member publicly support it, because we need to get this passed by both houses and signed by the president, because there's a lot of authorization in there followed by appropriations that's going to fund a lot of this stuff. Otherwise, it's either an unfunded mandate or just a hopeless wish.
All right. Thank you so much, Neil. So on that note, we're going to thank our panelists. Discussion, and we're going to the break now.
Okay. Should I go out there? Hi, everyone. So just start gradually making your way back into the sessions. We'll be beginning in a couple of minutes. All right, so we are now restarting the 3 parallel sessions. The room has been divided into 3 sections once again. The session on system architecture is located in the South Bay. The session on physics, land verification, and validation is located right here in the Center Bay. And the session on dynamics and nesting is located in the North Bay. And I'll now introduce Dr. Mike Barlish to introduce the speakers this afternoon.
Okay, thanks. I guess we need to get started. We've got 7 talks in this session, so it's a very tight schedule. Just a reminder to the speakers, you have 12 minutes, including questions. Jen is in the back of the room. Please keep an eye on her. She's going to hold up some signs for how many minutes you have left. And again, you know, we're very tight here, so I think we should just kick off and get going. So our first speaker is Joe Wong, talking about the evaluation and process-oriented diagnosis of the GEFS version 14 reforecasts.
Thank you for being here. I understand that my study is like maybe one or a few versions behind some of the studies presented at the workshop so far. But I want to assure you that the diagnostics I present here can also be used for more recent, more latest model versions. Most of the work here was done by my former student, Jiacheng Ye, and I also want to acknowledge my co-authors here, and also the funding support by NOAA. The paper has been published at the journal Climate earlier this year. Our diagnostics include 3 levels. Level 1 is focused on model systematic biases, including moisture precipitation relationship, cloud microphysics. At level 2, we focus on sources of predictability for extended range forecasts, including the Maiden-Julian oscillation, NAO, and weather regimes. At level 3, we evaluate high-impact weather and climate phenomena, such as blocking and tropical cyclones. Most of the model diagnostics have been included in the MetPlus package or made available at the Model Diagnostics Task Force GitHub online. The data we used here are GFS V12 reforecasts covering 20 years. We only used one member, the control arm here, because of the data volume. We used the EIE5 reanalysis, GPCP precipitation, OIR from cirrus and also tropical cyclone information from IB track for model evaluation. For convenience, I will simply regard them as, simply denote them as observations. First, let's look at model systematic biases. This slide shows the precipitation-moisture relationship. The top two panels represent the Western North Pacific, or tropical Western Pacific. The one on the left shows histogram of column water vapor. The black one shows observation, and the colored lines represent GEFS reforecasts with different forecast lead times. From blue to red, we have increasing forecast lead time. You can see in observation, we have a primary peak around 57 millimeter, which is corresponding to deep convection. Compared to observation, GFS peak frequency shifts to the left, which indicates dry bias. Now, if you look at the right panel, which is precipitation as a function of column water vapor, you can see compared to the black curve, the colored lines indicate early precipitation onset in terms of column water vapor accumulation. We know precipitation reduces column water vapor. So when we have early precipitation onset, column water vapor cannot keep increasing. That's why we have the dry bias as indicated in the histogram on the left. On the other hand, when the peak frequency shifts from 55 millimeter to 50 millimeter, basically down the curve, that also represents a substantial reduction in precipitation, which means heavy precipitation frequency is significantly underrepresented in the GFS. Now let's look at the Eastern Pacific. The panel on the left in the bottom shows a histogram of precipitation, and here we have a bimodal distribution. The primary peak represents congested convection, and the secondary peak is for deep convection. Compared to observation, we can see the model underrepresents congested convection, or the peak, primary peak, but overestimates deep convection. Again, in the right panel, we can see precipitation onset occurs too early in the GEFS in Eastern Pacific. Now let's look at the two-dimensional distribution of long-term water vapor on the left and the precipitation on the right. From top to bottom, we have observation, EI5, and the GEFS, and the biases. In the bottom, biases are defined as GEFS minus EI5. We can see over the maritime continent, we have strong negative biases in column water vapor, which is consistent with the dry biases we saw in the last slide. Then in the precipitation biases, you can see precipitation is overestimated over Eastern Pacific. In other words, the ITCZ is too strong over the Eastern Pacific. We will come back to these 2 points later. Now let's look at the sources of predictability for extended range forecasts. This slide shows the median Julian oscillation scale in the GFS represented by the bivariate correlation coefficients. What we see here is the correlation coefficient as a function of forecast lead time indicated in the x-axis. The black curve is for all MGO days. Blue and orange represent strong and weak MGO days. You can see for the all MGO days, the correlation coefficient is above 0.6, up to 16 days, which is a substantial improvement compared to an earlier GEFS version. I should also emphasize that here we only used one member. If we increase the ensemble size, the prediction skill would further increase. Also, you can see strong MGO days represented by the blue curve have stronger skill than the weak MGO days represented by the orange curve. This slide shows the harmonic diagrams of bandpass filtered precipitation. From A to D, we have GPCP observation, 2 day, 9 days, and 16 days GFS forecasts. In GPCP, we can clearly see the eastward propagation of enhanced and reduced precipitation signals, the disruption over maritime continent, and the resumed eastward propagation over Western Pacific. In GFS reforecasts, even with the 16-day forecast lead time, we can still see the eastward propagation. But with larger forecast lead time, the propagation signals are less coherent, also much weaker. That can be tied to the dry biases we saw earlier over maritime continent. Earlier studies have suggested the gradient of humidity, the horizontal gradient of the humidity field or maritime continent is important for the eastward propagation of the MGO across the maritime continent. So the biases here can be partly attributed to the moisture biases, which is linked to the precipitation humidity relationship or biases in the cumulus convection scheme. To quantify the biases in MGO, we showed the probability distributions of MGO phase speed on the left and the daily changes of MGO magnitude on the right. Here, the black lines represent EI file reanalysis. On the left, you can see I forgot to mention, the vertical lines represent the mean of the distribution. You can see the black vertical line is around 8 degrees per day, which is corresponding to 45 days period of the MGO. Then with the increase in forecast lead time, you can see the vertical lines shift to the left, indicating slower MGO propagation. We can also see the propagation on the left panel, the propagation distribution becomes flatter, which means MGO propagation becomes less coherent. Now let's move to the right panel. You can see the peak frequency occurs around 0, which means MGO is about a quasi-steady state. But with the increase in forecast lead time, the distribution becomes flatter. Again, that indicates less coherent MGO pattern, or the model has difficulty representing the quasi-steady state of the MGO. Now let's look at weather regimes over North America. We have 4 weather regimes over North America. The figure on the left shows the anomaly correlation coefficients of weekly weather regime frequencies. The different colors represent, the 4 different colored lines represent individual weather regimes. The black line represents the average over the 4 weather regimes. Basically, the ACC values above 0.6 up to 12 days, which is similar to the performance of ECMWF S2S reforecasts. The panel on the right shows the persistence probability, or the probability for weather regime to persist into the next day. This is an important metric because persistent weather regimes are often tied to extreme weather, such as heat waves. We have 4 groups representing 4 weather regimes. The colors from blue, orange, green to red represent EI file, Pentad 1, Pentad 2, and Pentad 3 GFS reforecasts. We can clearly see the strong persistence here across over different weather regimes and at a different forecast lead time. Now let's look at high impact weather. This one shows the tropical cyclones, genesis density function from top to bottom. We have observation, GFS, Pentad 1 reforecasts and biases. Over West North Pacific, we see substantial improvement. Basically, we don't see much biases. That is a substantial improvement compared to an earlier version. Over Eastern Pacific and Atlantic, we see positive biases, which can be linked to the overestimated ITCZ I mentioned we saw earlier. Now this is the last slide of my result. This one shows the blocking frequency as a function of longitude on the top, it will represent the two peaks, one over Europe Atlantic sector, the other over North Pacific. The bottom one shows a two-dimensional distribution of blocking frequency. Basically, we see a good agreement, although we see positive biases over subpolar North Atlantic and the negative biases over Eurasia. Okay, here is my summary slide. I will stop here. Thank you.
Interest of time, I think we should move on. There is a Q&A session after this, I guess, at the end. So, so next up, Sarah Liu, right? Talking about integrating JEDI and MET+ for evaluation of atmospheric composition forecasts.
JEDI is a DS system that multiple agencies are developing, and NOAA included. So, but JEDI including different science elements. So one is really do forward operators, so they really know how to generate the model state on observation space. So this work is really to try to integrate JEDI with MET+, and then use this to evaluate the atmosphere composition forecast. And then a lot of technical work was done by Shi Wei here. So I'd like to acknowledge this project is really joint center, and then your medicine, Wisconsin Medicine's team, and then also we're including scientists from NCAR and NCEBIT, and then Air Resource Lab. And the funding is from the JPS Proving Ground and Risk Reduction. So the background is MET+ is a verification and validation package for the UFS, but right now they still have quite limited capability to verify the chemistry forecast. Right now, MET+ can evaluate AOD and ozone and surface PM. However, really in the satellite era, there's a lot of satellite observation, but the system is not able to really take advantage of the new generation observation in the space. So, and which, that although there are a lot of very nice ground-based measurement, but to really verify the chemistry forecast, you need all the information, including those from space, and those are really still lacking in the MET+. So the project is really, we try to enhance the MET+ constituent verification capability by really try to build an interface and allow us to really using the satellite observation from JPSs and from other observation, other sensors. So the specific application we're talking about is really cross-cutting verification framework for trace gas and aerosol, and of course UFS application, because MET+ designs for cross-cutting for, from S2S to weather to air quality. And then, but why this is important? So really, when we develop model, we tend to compare with observation. So it's very, very important we actually put those model output and satellite in a comparable way. Not just space, not just temporary comparable. It's also, use the operator allow us to consider a lot of sensor properties, so we will not mistakenly, well, I will show later on in the one of CO2 wireless operators to see, when you put in a comparable state, you can do a fair comparison, and that's actually very important when you try to use the results to tune your model. And then obviously, once you advance your MET+ capability by having a better way to compare with satellite observation, through the process you can, the whole idea is to improve the model forecast by learning from the comparison results. So this is an example about in the middle is, in the central panel is a Trap-Omi observation, and this is show the Siberian Wi-Fi event. And then on the right side, it's we use one version UFS, and then they produce a CO. And now when you don't consider every kernel, you don't consider sensor sensitivity to height. So you will see you get a plume much weaker. So just by actually interpreting results in the wrong way, you will tend to say, well, models tend to be too low. Let's tune a model to big up. But then when we're on the left side, when we consider observation operator, which you consider averaging kernel, then you actually see we get higher plume intensity. So that means actually the model is adequate to produce a Siberian Wi-Fi event. But the key is really to really use the observation to tune your model, you need to use observation the right way. And use a satellite operator is really one of the critical way to ensure we can achieve our goal. And then this is, in the Joint Center, we built a Skylab, and this is how we view the data viewers. So on the left side is on the left side is really, after we run a forward operator, we actually simulate observation, use a model state. So this is pretty much what the satellite will see when they sense the atmosphere is actually model atmosphere. And then right side is actually the corresponding observation. So we have this capability right now for multiple sensor, for trace gas and for the aerosol. So the whole idea is we want to really bring this in to couple with Make+ for the model evaluation. So that's the framework we're building on. So on the left side, you'll see, obvious to compare model with observation, you bring both information. And then we build a generic interface to read the model state. The JDA was developed for data simulation, so they actually originally only read model in the natives. So for do every three will be native model grid. However, a lot of time when we do the evaluation, we tend to use a post-processing data, tend to be regularly long or even Gaussian grid. So the Joint Center developed a generic interface to read those model grid, different model grids, so that we use the archive or post-processing results. And then, so once you use this and then observation, we have a YODA data, well, I guess you want to define. So generic interface was developed to ingest model in any grid format. And then both observation and the model goes through the YODA is how we really read in the observation. And through the forward operator, which is we call the UFO here, and then you can pair model observation and the observation space, which on the right side, the model pair. So in this, so the forward operator will produce a pair model and the observation in a specific format we call a YODA, which stands for the interface for observation data access. So once you create to the point and we build an interface, which is based on Python, to really, that's where we couple with Make+. So once you got to this point, you pretty much can use a lot of capability existing in the Make+. So the key is really, you really don't want to reinvent the wheel. Make+ has a lot of very nice capability we want to use. At the same time, we want to verify model use satellite observation, and we know that JDA has a lot of elements, know how to produce the information we need. So this project really try to interface these two elements there, and then for the specific applications, actually for atomic composition. So one example would be here is, so up to this one I mentioned, we kind of cross-cutting from Make+ to the JDA, which is really from the UFS core cutting verification package to the JDA, which is a DS system. And then we also work on other aspects. Really, there's another verification, Melody Monet was developed by NCAR and NOAA. And that was originally designed for atmospheric composition. So this is just demonstrating, there's a lot of frameworks, a lot of very nice software systems already there. Sometimes we really just need to make effort to kind of link everything together, and then instead of reinvent the wheel, we can take advantage of existing capability. So on the left side, we run the Melody Monet to pair the WorldCam results run by my group and with a surface observation. So this existing Monet Melody capability. And then we actually, so this will again create a pair model and observation. And now you send the Python interface, you actually call the Make+ now. So to generate those statistics, the continuous table, those kind of statistics, and this is not available in Monet Melody. So instead for Monet Melody to bring those new statistics through those interface, these two very nice package was able to kind of integrate together and for the user's need there. So, so this is one example I will show is actually recent mid-June, the very large Canadian fire that, cover the whole Northeast, and that's particular event we pick here. So it's really not to show how good, how bad our model is. It's just show, the effort to really combine different software. And because, at the end of the day, you had a lot of effort already built on the Make Plus, a lot of effort already on Monet Melody, and even JDI. So really, you really just need effort to kind of interface all together, and then for the really much broader application. So really, conclusion here is we have this project is funded by JPSS, and then the Joint Center, the Wisconsin group, and Ross team, we work together and to develop atmosphere composition evaluation package, and our specific approach to interface JDI, their observation process element, which including YODA and the UFO with Make Plus. But we also connect Make Plus with Monet Melody, and that's really, the whole idea is really we want to serve the broad composition community. And one advantage could be, there's certain operators already available Monet Melody, like ARMS, Nader, Maple, Ozone, which so we can, just by interface, then we can use what available in Monet Melody. So this I just want to showcase, we really working on the composition verification framework. It's really cross-cutting, really just not within across the UFS. We really go beyond, because that's where we bring the JDI and we bring the Monet Melody. So I guess that's what I have. So.
Thanks, Sarah. Dustin, you might as well come up. Try to keep the transition short here too, but yeah, again, I think we probably need to push the questions to later. Next up is Dustin Swales talking about hierarchical physics development with the Common Community Physics Package single column model.
Thanks for sticking around for this. First, I want to thank my co-authors, Grant Furl at NOAA GSL, Mike Eck at the DTC, Lulin Zhu at RAL, and Ligia Bernadette at NOAA GSL. And I'm going to be talking today about hierarchical physics development within the CCPP physics, and specifically tools within the single column model to enable greater process level studies in hierarchical development. So I'm going to start out with just putting this up here. This is a schematic of the single column model. It's a little bit, there's a lot of little boxes here, but the most important piece is this gray box on, well, this isn't working, but right in here. So this is the physics, and then the infrastructure, to call the physics from the single column model surrounds it. So the single column model has the infrastructure in place to already provide a lot of the hierarchical steps you need to develop new physics within the CCPP, being that we could run it offline very quickly. So it's a great tool for transitioning products from research to operations. And the DTC maintains the single column model physics up to date with the operational UFS. So you could use the CCPP physics with what they're using relatively close to what they're using in the UFS. Right, so I was just saying that again, but there are some limitations to that because the single column model doesn't have the robust data set that the full 3D coupled model has. It has some case studies that can be used to explore physical processes, but it's relatively limited in the amount of coverage you could do. And the single column model does a great job of partitioning off the dynamic impacts away from the physics dynamics coupling impacts, so that you could just study the impacts between the different physics schemes and not have to worry about feedback with the dynamical core. But then there's a gap in the hierarchy there where we don't know how to understand these changes between physics parameterizations. So the single column model is really great for isolating the dynamics away from the physics, but then the individual physics are still all there to interact with one another. So that's still, a problem that I will hopefully have a solution for at the end of this. So one of the new features in the CCPP single column model is this feature called UFS replay. So this allows you to take any UFS output, create forcing data sets from that output, and run the single column model. So this could allow your physics to see the atmosphere that it would eventually see when it was in the fully coupled model, but you could do this offline without the computational burden of running the full 3D model. You don't need access to high-performance computers to do this. You could do this on your laptop. So here are just some profiles of a couple of ensembles I created. So I created 100-point SCM ensembles over just the Atlantic Ocean for a couple different UFS outputs to show the sensitivity of the replay characteristics to the data that you'll be using. So on the left, we have 6-hour UFS output that I'm using to drive forcing for the single column model, and then on the right, we have 1-hour forcing. And I just want to highlight here that when you go from 6-hour to 1, you still kind of have the same mean state that you recover from the UFS, but the variability is much lower when you use the higher resolution temporal output. Same thing here, just 2D outputs. So rather than the full profiles, these are ensemble means going out 10 days. So the single column model does a pretty good job of tracking the state of the UFS in this replay mode. On the left, again, 6-hour output from the single column model, and on the right, 6-hour output from the UFS used to drive forcings for the single column model, and on the right, it's 1 hour. So here's just a quick example of using this. So I took some UFS columns and I created an ensemble of columns and I ran them through the default physics, so with the RRTMG radiation. And one thing we know about the RRTMG radiation is it has a warm bias in up in the stratopause. So the new version of the radiation RRTMGP has better spectroscopy built into the algorithm to avoid this heating rate bias. So I ran this through with both cases and was able to reproduce this signal in the single column model, running it offline as in the UFS. So it can recover the state and be useful to helping tell us, how our physics are going to behave when we finally make the step to the 3D physics. So just to summarize this tool before I move into the other ones, we can explore physics coupling relationships using this replay tool without the computational burden, without worrying about feedbacks to the die core, and really providing that step in the hierarchical process when you're going from understanding basic physics processes to the full dynamical coupled 3D model. But there's still a gap in the hierarchy when we do this because we don't know how the parameterizations themselves are going to interact with one another. So that's another piece in the hierarchy that we want to try to close, and that's what I'm going to show here, which is this new thing called the suite simulator. So the suite simulator, what it does, it's a CCP compliant physics scheme that emulates the internal state evolution in the physics suite. So I'm going to use a lot of CCPP specific lingo maybe here. So if it's not landing, that's okay. We have questions later. But the idea is if you had a bunch of physics parameterizations like we do in the CCPP, for process split physics, which just means the physics are always using the same state as every other scheme, you could evolve your time step along by aggregating all of the different tendencies from the different simulators together and then advancing your state like that. So we could emulate this internal physical state within the CCPP. So it gets more complicated for time split physics processes, which are physics processes that matter in terms of ordering. So that means if we're going to call certain physics schemes in order, it can handle that too. It's just a little bit more complicated. So what we do is we take the active physics schemes and we replace them with data-driven physics tendencies, and then we reconstruct the state, and then we evolve in time. So here, just the top line is just an example of a completely active scheme, which means that it's all active tendencies. And then the second line is we're replacing everything that's active with data-driven tendencies and keeping the PBL scheme. The next line is just an example of the same thing, but we're keeping the PBL scheme active and the radiation. So in that case, we're really testing the coupling and looking at the coupling of those two schemes. So this is accomplished by adding a new scheme to your suite definition file, which is just CCPP lingo for your physics configuration. So you could add this on, change the name list, and play with the internal evolution of your physics state via name list. So this is pretty straightforward for process split physics. Because all of this, the order doesn't matter, we could just kind of implement the scheme at the end of the physics configuration and just kind of re-aggregate the state. With time split processes, it's much more complicated because we have to advance the state according to the evolution outlined in the suite definition file or the physics configuration. So for time split processes, it's more involved. We have to add these calls in multiple times. So that's just what I want to show here. This is kind of just technical CCPP stuff, but these are just kind of how like physics suites are organized, you know, idealistically, where you have different schemes called in order. So on the left, we have, you know, a process split physics configuration where all of the schemes don't depend on the other schemes. So that means you can call them in any order, which is nice for us because we're trying to put the state back together after the fact. So it's very easy to do this with process-based physics because it doesn't matter about the order. So we can just put our thing at the end of the suite, run our model, change our physics as we go. Another example here would be in the middle where we have a time split suite definition file. And the deep convection scheme is time split. So to emulate this, we have to put the simulator in before we call the convective scheme to aggregate the state up to it. Then we would call the convective scheme, and then afterwards we would aggregate all the states back together. And then on the furthest right plot is another example of a time split suite definition file, but this is with two active schemes. So we'd have to put these inserts, these hooks, into different places within the physics evolution so that we can modify the state how we want to. So, okay, so one thing I didn't discuss yet was the data that you need for this CCPP suite simulator. So it's, you know, infinitely possible to create any kind of data that you want, but your data, if it's not physically useful, it's not going to really get you any hierarchy. So, you know, with the single column model, we provide some ways to create these data sets from output from previous runs so that you could essentially, you know, run the single column model, save the diagnostics, and then run it again, but only keep one simulator on, one parameterization on, or two parameterizations on. So this way you could build up to running from, say, one developmental part of one scheme all the way up to the full interactive 3D suite. Right, so this is just, you know, what I just said here. I should have advanced this slide before. But this is just to say that the data is the hardest part in creating this simulator because you want to be able to replace your physics processes with physically relevant data to force it. So you need to be careful with how that is done. And we tried to outline some ways and put some guardrails within the single column model, but there's infinite ways you could do this. So I'll just leave this up here. Just a summary about the two tools that we have for hierarchy with the single column model, the UFS replay and the CCPP suite simulator. Both of these will be, one of these is already available, the UFS replay, and the other one will be available in the coming weeks. So if you're interested, you know, stay tuned or talk to me after this. That's it. Any questions?
Thanks. This is really wonderful tools. Really helped us. And also thank you for the hard work. And one question I have for the UFS replay capability is that you can, if you write out the model output step by step, each time step, were you able to reproduce the forecast model results?
So we originally started by saving instantaneous dynamic tendencies and forcing it with that. But that required us to modify the output. So we created the script to run on the standard outputs, which derives the tendencies from the states. So when you do that, you don't get exactly bitwise, but tendencies you do.
Okay, I think we're good. Wei, you want to come up? All right, so next up is Wei Li from the DTC, talking about their contributions to the UFS physics development and advanced testing and evaluation towards UFS physics unification.
That's a long title. Sorry about that.
half your time.
Yeah. To present some contributions by DTC to the UFS physics development and our advanced test evaluation for the UFS physics unification. So I put all of our team members here, including Manjong, Evelyn Grail, Tracy Hernacki, Brain Nelson, and Catherine Newman. All of them are from DTC and across NOAA Labs and NCAR. I also want to acknowledge our internal collaborators, Jimmy Dadia, Lu Linxue, and all of the, our team members across CCPP and MapPlus team at DTC. And lastly, our external collaborators, the UFS physics leads, Lisa and Fanling, and all the physics developers across the UFS working groups for the physics. Okay, lots of acknowledgements. Okay. So just a brief introduction about our activities and its connection to the UFS stages and gates. So we basically have two objectives. The first one is to facilitate the transition of some near-term and pre-operational physics improvements to operations. And the second one is, the first one has relatively higher readiness level, and the second one is to support the longer-term and high-priority UFS objectives to really help facilitate the unification physics parameterizations across different applications and skills. So this one has relatively lower readiness level. Okay, so in our activity, we use real case studies for both land and oceans because these case studies can capture the processes of moist physics, boundary layer, and surface conditions and their coupling or interplays because we want to focus on physics. And we choose these case studies to represent phenomena under a variety of cloud, or weather, or climate regions. So I list some of the case studies that we used in our activity. So these have some reliable benchmark to compare with. Some of them are from very famous like field campaigns. And we simulate and evaluate our case study against a reliable benchmark. As I said, observations or analysis or reanalysis. And the tool we use is something that Dustin just talked about, CCPP single com model, because it really can help us to decompose the physics contributions. And we also ran some limited area model simulations to try to connect what we see in single com model and to help, for the physics unification, like application into the regional domain. So we ran our cases for both 13 kilometer and 3 kilometer. 13 is because this is something that currently used in the global configuration, and 3 kilometer is because this is convection allowing scale. Okay, so for the targeted physics that we have been focused on in the past year, we become more actively close working with all of the physics developers in the UFS to determine what kind of physics we can help with. The code base that we focused on so far is the prototype 8, that is a candidate physics for GFS version 17, and it's from CCPP version 6 or SRW version 2.1. Both of them are public released version, but they are experimental P8, but not the final version of P8, just so we can inform the development. And second one is the physics suite for the regional configuration, including Rufus version 1 beta and HER. And we also, touch base with some latest code base just so we can inform the physics development. So we use the top branch of the repository. And we also become as a PR watcher to identify those physics enhancement or innovations or updates to help with. The first one we work on is the so-called proc sigma, and I will talk about this later. And then the next one is updated Thomson microphysics, and then refactored RTMGP radiation scheme, updated unified gravity wave physics, and lately the updated MYN, EDM, PBL, and shallow cumulus. So, so we help with these physics innovations or updates, and we also involved our DTC visitor project conducted by Andy Hazelton, who is also here today, to help him, implement these physics updates into or in the context of hurricane and using the hurricane application, just so to really fulfill the purpose of being like physics unification across different UFS applications. Okay, so I'm just going to show some examples that we did for each physics update or innovation. So the first one is prognostic scale adaptive cumulus convection closure, dubbed the proc sigma. So here I'm just going to show an example using the UFS limited area model simulation for Hurricane Florence. So in this case study, we identified that if we just use the control run, which is P8 based, we see at 3 kilometer, the simulation produces more grid scale precipitation, more low clouds, and more microphysics result hydrometers. But if we add the proc sigma feature in it, which leads to less scale sensitivity and tends to prevent the microphysics from dominating the rainfall production as the grid spacing decreases. So which is really positive because this is what we are expecting proc sigma can do for the model physics to behave at this grid scale. This case study stressed the importance of the interplays between the moisture physics component when we consider the scale awareness. So next, I'm going to show our case studies for the updated Thomson microphysics. Here shows the time height profiles of cloud fraction for 2 cases. One is our MAGIC, which is the marine stratocumulus of the west coast, and the next one is the famous TWP ice case featuring the monsoon transition between deep convection to stratocumulus. So this case study shows that even though we do see some negative happening like low cloud base and also more like stratocumulus happening, but with the updated Thomson, we do see there's some improvements. For example, the low cloud fraction representation in the stratocumulus regimes. I go too fast. Okay, the third case, the third one I want to show is our contribution to the refactored RTMGP radiation scheme. So here we use the Dynamo case study, which is basically to represent some processes associated with MJO initiation. So in this case study, we try to compare RTMGP with RTMG, like the older version of radiation scheme, just to see if RTMGP bring any negative impacts where it's neutral. So basically, by comparing with G or observation, we see GP does not bring any negative impact. In fact, so we find that at the upper level, the code bias is actually improved for GP because we see those like radiated cooling related negative biases sort of decreased in GP. However, we do notice GP has some like a deficit in shallow cumulus cloud that we see in all of the cases, not just this Dynamo case. So we report this back to the developer to see, okay, maybe this is something that we need to pay attention for the GP to represent in shallow cumulus. Okay. So next one, I want to show about our contribution to the updated unified gravity wave physics. So here we apply the MetPlus standard verification to several cases over the CONUS. We conducted limited area model runs just to see if including the GSL gravity wave drag can bring any negative or positive impacts. So basically, we ran the case at different horizontal resolutions, and what we find is the GSL gravity wave drag do bring, overall higher scale with respect to the standard verification for upper air variables. However, we do notice including this feature leads to some lower scales of surface temperature and the winds for both like 13 and 3 kilometers. So we reported this back to the developer just to see anything can be done for the surface, conditions. Okay, lately we helped the MYN EDM FPBL in the shallow cumulus scheme to conduct several single count model runs. So here just show an example of the arm lasso cases, and we also tested the sensitivity to different vertical coordination. The upper panel shows the 65 vertical levels for Rufus, and bottom panel shows the 127 vertical levels for GFS. So just to see how this is sensitive to, how this physics is sensitive to different coordination of the vertical coordinate, different configuration of vertical coordinate. Anyway, so in this case study, we see these updates for the PBL scheme really improves the cloud fraction with respect to the cloud amount and cloud continuity using both the vertical configuration that we used here, particularly in the afternoon, which is really challenging for representing the cloud. And we also noticed that MYN, this updates, has clouds better represented especially at finer or higher vertical resolution, if you look at the details of these plots. So this is really important to inform the PBL development to focus on not just the horizontal grid spacing, but also the vertical resolution. So it's really important for PBL representations. Okay, so I go it very quickly, but basically DTC has been working really tightly with developers to test, evaluate the physics updates and innovations for the operation. And we focus on, across the full spectrum of model physics. And the results inform both improvements or areas of attention in this physics, and stress the importance of the interplays between physics component when we consider skill awareness, and appropriate vertical coordinate to work with particular physics, and lastly, how physics can be applicable to cases across different cloud weather regimes. So it is hopeful our evaluation against a relatively reliable benchmark can help constrain the parameterized processes and inform future physics development. So I just want to highlight our visitor program. If you want to work with us, you're going to be paid. Okay.
Now you're up next. All right, next up is Jinwen Bao on developing next generation physics for UFS applications, the microphysics parameterization challenges.
Thanks, Mike. Greetings. For those who do not know me, I'm a research meteorologist at NOAA's Physical Science Laboratory, and I'm also co-chair of the UFS Physics Working Group. In this talk, I will provide a summary of the major outcome of the first annual UFS Physics Workshop held on 16th through 18th May this year. This year's workshop focuses on microphysics development, particularly challenges in microphysics development in the UFS. I'd like to first express my gratitude to all of my colleagues serving with me on the workshop organization committee. I'd also thank for the help, support from NOAA front offices, plural, and UFS leadership, and ONR, and NCAR role, particularly our colleagues at NCAR, Paul and Jenny. The focus of this year's workshop on microphysics was motivated by our long-term desire to address the needs for NOAA's operational forecast. It has a very long historical background, and it has its own predecessors. I'd like to mention a few major ones. Back about a decade ago, we actually held an HFIP workshop. In that meeting, we particularly want to find out what's the best strategy for the development of microphysics for the HFIP system. And as a thorough discussion, the conclusion, interestingly, from that workshop is that very scheme that then operational in the HFIP system was the best suitable for the tropical cyclone prediction, okay? Although there are a lot of development that needs to be still carried out. About a year later, the ECMWF community who are working with the ECMWF urged them to have similar workshop to decide that if there is a need to update the microphysics scheme in the IFS, their system. And they held a very successful workshop and invited experts from all around the world. Basically, after thorough discussion, they have the conclusion that IFS scheme worked well for medium range forecast. For us in the United States, we are mindful of these previous developments around the world, and in 2015, we had our own workshop, okay, to give us chance to look into the possibilities and challenges for us to develop our own physics, particular microphysics. So that workshop led to a white paper on very specific high-level directions for moisture process parameterization development for multi-scale prediction system. And because that is high level, so in the second year, we had another meeting to respond for the call from NGGPS, if you all recall. If not, you can ask me later. In that workshop, that workshop actually was the prelude to the development of the UFS Physics Working Group, which I'm a co-chair, and the UFS-R2 Physics Development Project, as well as the so-called Strategic Implementation Plan for evolution of NGGPS to a national unified modeling system. In that particular workshop, a group of us brought up a few important questions listed here for discussions. The process of these discussions led to the decision to use and further develop and test the Thomson scheme, a version of Thomson scheme we got from the WRF system in our UFS and then now the GFS V17 prototype. Okay, with a lot of ensuing work, much of work, we have the now almost unified Thomson scheme in halves, gaffs, and roofs, and the future GFS V17. So, to help the discussions at the workshop, we formed these topics for our discussion and presentations. First, the question is, what is the minimal complexity of the microphysics scheme for operations, particularly for UFS applications? And what is the research needed to actually optimize the various schemes with this minimal complexity? It is possible to unify for the unified operational microphysics scheme for the UFS applications. How actually we do aerosol chemistry cloud interaction better accurately? What is the way to make the resolved and the subgrid-most physics consistent in our representation of cloud formation and production? What is a better way or accurate way to handle the mixed phase clouds, especially in the middle and high latitudes? And importantly, how we actually engage the entire community of UFS to use observations and LES for evaluation and constraining the future schemes. So we structured our presentation and our breakout discussions with these objectives. Basically, we want to identify the current challenges and opportunities. We want to foster collaborations and knowledge sharing among all of the participants and the community. We wanted to find the best way, best actionable strategies and recommendations to address what we can identify in our discussions, the challenges and opportunities. Further, how we actually work together to explore innovative ideas to improve substantially, tangibly, our microphysics representation. We indeed identified a few major challenges and opportunities. In the interest of time, I'm going to provide a summary of the recommendations for future research development and the transition to operation to address the needs, the challenges we identified, and embrace the opportunities. Most of us agreed. When I say we now, basically it's most of us. Some people may still have a different opinion. Most of us agreed that our operational schemes in the for UFS operations should have the predictive capability of cloud water, rainwater, cloud ice, snow, and rammed ice, either in separate categories of hydromedias or in discrete spectral bin. This is something we needed to discuss further and have a best strategy. We all agreed that a double moment representation should be used for the separate hydromedia category schemes, at least for some of the hydromedias. Given the fact that we now have a scheme that actually fits this desire to have different categories of hydromedia and a double moment, to me, it appears our top priority, one of our top priorities, is to develop a consistent, in terms of energy and mass conservation, a consistent prognostic scheme for clouds. And this is not just a convection scheme. This is a scheme that includes all the components of fractional clouds in a grid box, and including the description of variability on a subgrid scale, such as shown in this photo, taken on polystyrene and provided by one of our colleagues on those high clouds at high latitudes. Not so high, actually, it's low clouds at high latitude, but it's fractional if you wanted to describe it in a microphysics scheme or in the, I call it general cloud scheme. We all agreed that our future development should incorporate state-of-the-art and efficiency and the effectiveness balanced of aerosol and microphysics interaction. Particularly, we needed to use aerosol information consistently between convection scheme and microphysics scheme and other subgrid cloud formation and production evolution. The future development should include gas, phase, and aerosol chemistry processes, such as wet scavenging processes of all chemical species, aqueous phase chemistry processes. We also should include a configurable and flexible microphysics scheme with optional components for future research, for process evaluation, and to look into what's the best way to treat close interactions with chemistry. We also agreed that in order to improve microphysics, one focus should be on the improvement of supercooled water representations to use LES to fill gaps associated with sparse observations and refining scheme configuration, careful consideration of dynamical microphysics process coupling, and importantly, collaboration with experts across the entire community. We also recommend developers be open-minded about ownership transfer, knowledge transfer, so to avoid single point failure. And last, not least, we need to incorporate observations in our future development. Such observations should provide us a good comparison of statistical relationships between microphysics, representation of cloud properties, and observations. We also need to add more cases with the comprehensive observation data to the CCPP single column model, as mentioned by Justin. And these are the two examples of observations can provide and what we can use in the single column model to use the observation to evaluate microphysics. To wrap up, we have had a successful workshop that actually helped us to create a vision for future development of microphysics in the UFS. A white paper is under development to inform community and funding agencies for our future study. I'd like to thank Ligia and Lisa to contribute to the beautification of the presentation here, particularly Ligia for those pictures.
I think we're out of time. Song Yu, you're up. So yeah, I think we hold questions again until the later session, but thank you, Bao. Next up, Song Yu Hong with a new double moment cloud microphysics parameterization scheme for UFS.
Okay, thank you. This is the development a new double moment scheme. This is a team efforts led by PSL with Bao, and also collaborates with GSL from Hai-Chin Lee, also Jimmy Dudia from Anchor. Also Sarah Mickelson and Evelyn Grell from the PSL. This is a history, long history of about 30-year history of MPS scheme development. When I worked at NSEM 1993, exactly 30 years ago, I implemented a simple ice microphysics scheme into the NSEP global and regional spectral models that is so-called the NSEP Cloud 235. And then in 2000, early 2000, we revised ice microphysics, which is normal concentration is not function of temperature. It's so-called Wolf's single moment microphysics scheme. And then when you implement the scheme into the global model with a larger time step, is sedimentation is very costly. So we developed the several sedimentation. And then we realized this single moment scheme has a limit in producing light precipitation and fog. So that we set a strategy developing double momentum scheme by pronouncing CCN, NC, and NR. And then we added a hail species for sub-kilometer resolution. And then we introduced a partial cloudiness microphysics, so-called in-cloud microphysics. And then GFTL microphysics version 16 adopts summarized microphysics from the warp single momentum scheme. And then WS scheme was written about 20 years ago, and the WDM about 10 years ago. I think I have some accumulated experience, also feedback from the community. Then it's time to update or develop the new scheme. So take all advantage of previous development and some bug fix, and the code was entirely rewritten for readability and company efficiency. Two major ingredients is in-cloud and the semi-Lagrangian. Name of the scheme is not determined yet. So tentatively, we call new or UFS microphysics scheme. This is a cloudiness. In reality, if you see the left, and then suppose over 33%, in reality, right column over 98%. But when you're computing microphysics term, all the conventional scheme assume that it is covered by 100%. It's not true. So this is a major ingredient of in-cloud microphysics, so that we compute that in-cloud in computing microphysics production terms, and then grid state QC tilde and the QI, QR, QS is a PBL or advection or sedimentation. So that we got the cloudiness from the observation, from satellite and the aircraft observation. We get the monotonic relationship on the right, like this panel. Oops, not working. Okay, so that is a very simple idea. And from the analytic solution, suppose you have this is auto conversion, for example. So that is auto conversion rate about the double in the cloudiness 0.5 as compared to cloudiness 100%. Our method very simpler than the method in the European Center. Also, they apply only few terms, but we applied all the microphysics terms. And another one is sedimentation. This is we developed a monotonic mass conserving scheme. This is unlike the conventional semi-Lagrangian, we find the arrival point by the with the velocity at the top and the bottom of the cloud cell. Then we don't need iteration to estimate the departure point. So with this, some treatment is that scheme is numerically absolutely stable, also mass conserving. But when you apply to the double moment scheme in the WDM6, we realize that it has some problem in number concentration of rain. So that in the WDM scheme, WDM microphysics, QR and R are developed by Eulerian scheme until now. And then two major issues in the double momentum scheme in sedimentation. There's a size sorting because of the slower sedimentation of a number concentration than mass. Also, vertical layer depths decrease downward. And then we set up the 1D test, sedimentation only. Beam is a beam microphysics. Eulerian 1 is Eulerian scheme as in WDM6. Eulerian 2 is the increased iteration, Eulerian scheme, and then maximum number of iteration in the also rainfall. SEM2 is a newest one. You can see that Eulerian 1 as in WDM6 or all the micro scheme in the warp model is suffer from the serious mass deficit, as seen in the top right panel. It was good enough for the single momentum scheme, but it's not in the double moment. So that we have two treatment. Eulerian 2 is the maximum iteration with the delta Z computed the lowest model level, which is a 241 iteration. SAM2 is the constraint of radius and velocity. It's very realistic. We removed some undesirable wiggling features, but it's a single loop, so that's much faster, obviously. Then we tested it into the 2D idealized core line test in the WAP model. You can see WM6 on the left. New one is the all revisions other than in cloud microphysics. New two is the plus in cloud microphysics. You can see that difference between U2 and U1 is greater than between the U1 and WM6. And this reflectivity, you can see that top is the new scheme, bottom is WM6, the left is a 4-hour, right is 6-hour. You can see that new MPS produce stronger convective activities with a small horizontal widths. Also, in terms of a storm structure, UMPS produced realistic front to rear inflow jet along with the cold pool near surface and outflow. So that if you just compare to the top and upper and lower panel in the 4-hour, the arrow, there is a very organized rising slantwise convection by the new scheme, but it's a WM6. It's a very less organized, wide, also up and down, instead of a slantwise convection. Then we tested it for the aerosol sensitivity by changing the 100 to 5,000 per cc, so that left figure number concentration is the decrease. Is with the oops. I think it's somehow figure is sorry about this. So the laser effect is actually reasonably reproduced, and then cloud drop size is decreased and the raindrop size increased as seen in the airborne observation from the WAP community. And then we implemented in the CCPP single column model, so that in general, new scheme has a smaller amount of cloud ice, but still is smaller than JFTR and actually smaller than Thomson. And then implemented the 3D C76A 13 kilometer. Also coupled with the co-cut aerosol, and then tested one case. Oh, sorry, it's not one case. It's 1 month of July 2021. In terms of skill score, anomaly correlation coefficient at 500 hectopascal. Red line is P8, and the black is a new scheme. You see, very similar, but in the northern hemisphere is better. And tropics, you can see the difference. Is black is upper. This ongoing is grid scale precip. We figure out that when you look at the surface precipitation, enhanced light precipitation of a tropical ocean and unrealistic distribution rainfall of a tropical land, this found to be apparent deficiency of in-cloud scheme when they have larger time step. All products term need to be re-examined. But there's a positive point. In terms of work clock time, as compared to JFTL microphysics, it's 11 point for Thomson scheme, and new scheme has 4.8% increase. So that it has, new scheme has one additional 3D variable, but its work clock time is about half of the PA scheme. So this is a new scheme is under development with some preliminary evaluation result, and then will be shared to the public domain early next year. Thank you.
Have you looked at the simulation of mixed phase cloud, like severe cold or cloud water?
Yeah. I think it has a less amount of cloud, I remember. Actually, we haven't looked at, but after finding this kind of apparent issue in the presentation, we are working on it.
I ask because currently the like FS model or Thomson microphysics or GFD microphysics, none of them can capture the mixed phase cloud in the Arctic region. We are looking for a solution for this.
Actually, I put that one of the to-do list here. Yeah.
Okay.
Yeah.
I'll ask a quick question. So have you ever done longer into comparison just simply to isolate this impact of in-cloud microphysics? Like you were saying, you had a fractional component. Have you done an isolated test to see with and without, like a clean test?
Yeah, it was done in the 2D square line test.
Yeah.
As seen, it's
but not like in a 3D.
U1 is yeah. We did it for one case. That's the way we continue to debug,
okay.
Also find a way to further improvement. Yeah.
Okay.
All right, thanks, Thank you. All right, and in spite of someone's best effort of removing land from the title of this session in the online program, Sen-Lin He's going to talk about improving snow cover modeling in UFS NOMP land component.
So the land component. So I would like to first acknowledge all my courses here, including Ronnie and Faye from NCAR and Mike from EMC. So this project is funded by the NOAA WPO program and also the USGS NCAR collaborative program. So first, a few words about why we care about snow. So as we know, the snowpack, especially over the mountain regions, significantly modulates the land surface energy and water balance, and also the water resources provided to the downstream regions. However, the current UFS NOMP land components still have a large uncertainties in the snow cover and also other snow processes. So in this talk, I'm gonna talk about our ongoing work to diagnose and also to try to improve the snow cover parameterizations in NOMP. So here, as a motivation, this is done by our previous studies to compare or evaluate the NOMP snow cover versus the snow depths. This is so-called a snow depletion curve. If you just look at the points where the red ones are model and the black ones are observations. So as you can see, the red ones are almost like a binary type of relationship, especially when you look at the if you look at this low snow density or accumulation period, especially compared to the observations, the model highly overestimates the snow cover in NOMP. And if we look at this from a more spatial perspective, this is 10-year simulations over the Western US mountain regions for different sub-mountain regions. And you can see here, this is the model bias by subtracting the model from the observations, MODIS observations. And we also use different types of observations to do this. It's generally, the pattern is similar. As you can see here, the model overestimates the snow cover almost everywhere, particularly over this outer boundary of these Western US mountain regions. This directly contributes to a very large surface albedo bias in NOMP over the mountain regions, as you can see here, where the red colors are showing the overestimated snow albedo. So why is this snow albedo bias and snow cover bias so important? So if we look at this so-called snow albedo feedback, which connects various model uncertainties here. So if we have this overestimated snow cover fraction, we would have the overestimated pixel-wise surface albedo in the model, and then we underestimate the absorbed solar energy, which triggers the underestimated heat flux from ground to atmosphere, and then we have the cold bias in the model. and this further promotes the underestimated snow ablation and also the overestimated snow depths. And then this is a positive loop here, as you can see. So this is why the bias in snowpack and also surface area is so important, and that's why we try to look at this and fix this in the model. So what do we do to fix this? So we try to use observations to constrain the model parameters here. So these equations here basically is used in the UFS non-peak land component to calculate the snow cover fraction from the snow depths here. And two important factors here, or parameters here. The first one is this snow cover pre-factor, and the next one is this M factor, which is the snow melting factor. So what we do is that we use the 1 kilometer snow depth and density data, and also the 500 meter Mozgag snow cover data to constrain these model parameters. And what we do is that we also try to look at how these parameters vary across scales. Here the native resolution we are looking at is 1 kilometer, but we also try to transfer this to the UFS resolution in the future. So that's why we also consider 3 different UFS relevant spatial scales, including the 3 kilometer, 13 kilometer, and 25 kilometer. And some of the preliminary results, because this is just still ongoing work. So we can see here the red part is the model, the optimized or enhanced snow cover fraction parameterization results for the bias, and the gray part is the default model bias for the snow cover fraction. So as you can see, basically, after we use the observation constrained parameters, the model significantly reduces the snow cover bias, and you can see a general trend to have a much larger reduction in the bias as we go to the causal resolution. And this is just 2 examples for the different vegetation types, and we actually do this for all the MODIS-based vegetation categories in the model. Here I'm showing the scale dependence of these snow cover parameterization curves. As you can see here, this is still showing the snow cover fraction as a function of snow depths. So this is the so-called snow depletion curve. So this is evergreen needleaf forest as an example, and this is bare soil or bare ground cases. And the left column showing the low density snow, which represents the accumulation period, and then this red column showing the high density snow, which shows the represents the ablation period. So as we can see, in general, so compared to this gray line, which is a default curve, the optimized curve show a substantial difference here. And also as we go to the causal resolution from red line to the blue line, in general, the curves going towards this lower snow cover fraction at the same value of the snow depths. So this is just to show the tendency of the different parameters over the different resolutions. However, we do have some we do face some challenges here. So here, what I'm showing is that the x-axis is different vegetation types. The y-axis is the optimized parameter values. So and also different colors showing different resolutions. So ideally, we try to have a pattern or a relationship that we can use to say, okay, we have these optimized parameters under different resolutions uniformly that we can apply to the UFS system. However, as you can see here, the pattern is not clear where we can discern a very systematic relationship from this optimized parameter as a function of resolution or as a function of vegetation types. So we are still trying to figure out how we could leverage this information and to apply that to the UFS system across different scales. But if you have any suggestions or ideas, please talk to me. So we are still thinking about how to solve this problem. So lastly, some of our ongoing work. So first, we try to, as I mentioned, we try to find a solution to allow the optimized snow cover parameterizations to be applied across scales, particularly in the UFS system. Second one, we are still evaluate the suitability of this current snow cover fraction scheme for high resolution modeling, because the default parameterization is the developed 20 years ago based on 1 degree satellite observations. But now you see, like even for UFS global applications, we are going towards a higher and higher resolution. So this scheme may not be applicable anymore. So we are also trying to include more unaccounted for parameters in the current scheme, such as the land surface and meteorological conditions, as the topography, radiation, etc. The third one is that we are trying to assessing the regional offline non-MP simulation with the enhanced parameters, so that we can see the effects on the land surface and water energy budget balances. And the last one, we will test this coupled UFS non-MP performance with the enhanced parameterizations shown here. But all these will be dependent on this, the first one. So we try to have a cross-scale uniformed snow cover fraction parameterizations in the model. With that, I would like to stop here and take your questions. Thank you.
We've got time for a question. You? Over here.
Great talk, very interesting. So I have a question. We also run the offline OMP for recent 3-4 years, I think between 2017 and 2020. We found exactly the opposite tendency. The depletion of snowpack over places like the Upper Colorado River Basin have been just too fast in comparison to observation. So we actually had a paper that was just submitted about 2 months ago. So one thing we found out is that much of the sort of faster than observed depletion has to do with inadequate precip. So I just wonder, have you actually attempted to isolate the impact of precip in the biases you have seen? Whether you have any kind of ability to sort of distinguish the contribution from a precip bias versus the issue with the albedo?
Yes. So in the motivation slides, I was showing is actually the different colored lines showing using the cases using the different precipitation forcings, including WRF, NLDAS, and all those ensemble precipitation data sets like created by Ben Livni group. And also in my results part, the preliminary results part, the biases we see for the gray part for the default one and versus the red part for the optimized versions, all those are constrained by using the relationship, but also using the observed or snow dust constrained snow depths to drive the equations and to calculate the snow cover fraction. So that's essentially the results can remove all those uncertainties from the forcing. So it's exactly the snow depths from observations and put that into the equations, and we calculate the snow cover fraction compared with the MODIS, the MODSCAC 500-meter data.
All right, I think that's it. Thank you, everyone, and I'd like to thank all the speakers. We're only 1 minute off of schedule, amazingly, so thank you, everybody, for keeping on time, and let's another round of congratulations. I think we're coming, I don't know what's happening actually with the rooms, but I think Lisa is moderating a session on Q&A for all of these coming up in 15 minutes, right? Okay. All right, great, thanks.
Yeah, I think this like projects out there, so I'll like make it, yeah. I know. Right, yeah. Hi, everyone. Please start making your way back to the session. We'll be starting in a few minutes. Yes. Yeah. It's 5:02. I don't know if I should make an. It starts at 5. Should I just begin? Hello, everyone. We'll be starting our next session. We have allotted some time for a joint Q&A for the parallel sessions with cross-cutting concepts, and I would like to instant from NOAA, ESRL, and PSO. Thank you. All right, welcome back, everyone. So this Q&A session is for us to have some question and answering session and discussion about the cross-cutting concepts that we had just previously. So they were on physics, verification, and validation, and it was system architecture and dynamics and nesting. And I think this time slot is to allow you to ask questions from any of those sessions that you heard, any presentations that you heard. And one of the goals is to sort of clarify and understand the crossover between groups, identify areas that these groups can work together and so on. So if you have questions to any of the talks that you heard from the previous sessions, please step up to the microphones and ask them. I was thinking in terms of the idea of crossover and within the unified forecast system, one thing that all the applications share among the different model components within the UFS is the dynamical core. And perhaps one topic of discussion is what does that mean for the UFS if one of the applications were to switch to dynamical core? Does that mean that we're no longer unified as ununified forecast systems, or
could there be an opportunity to fit several die cores within one system? So I think that's one topic that perhaps could be worth discussing now when we're in the larger group. But please, I welcome anyone to share their view, ask questions. Who's brave? Who's still awake? Yes, thank you, Kevin.
Okay, so do we have the speakers on here, or?
Yeah,
Yeah,
that sounds
okay, I have
like
a question, I have a handful of questions for Paul Ulrich. I don't know if you could answer configuration questions about Scream. I was wondering about whether or not you're using a static or a floating Lagrangian vertical coordinate. And if you are using the floating Lagrangian, what type of remapping method are you using, and how often do you do it?
So, do we know if the virtual attendees can hear this conversation? Yeah. So I wonder if Paul Ulrich is still online.
Oh, we just have one of the virtual presenters in Zoom at the moment.
Oh, okay.
Yeah.
So I think he said it's just one person virtually right now, so perhaps he's not around to.
Okay.
It was a good question. Is there anyone else who could answer it?
Yeah, we can, or at least I can hear and see, so I think it's okay. I don't know if you can hear me.
Yes.
Okay, cool. Hello.
So yeah, unfortunately, the recipient of the question wasn't still online. So I wonder if there's anyone else who would like to take the opportunity to ask questions on any of the presentations you heard previously. Yes. Mm-hmm.
Hi, I have a question to Christina, actually. How can we unify the workflow, complex workflow that intends to serve the needs, larger needs of operational forecasts and ensembles, with the simpler workflow that is needed for like community, academia, and teaching purposes?
Well, that wasn't a softball. Okay. So I think that one of the keys to being able to span the variety of use cases that we have here, whether it be operations or research, is to define a lot of these different pieces in a way that they're all fully configurable for what you would like to do. Not making so many presets that you can't get in there without going in and manually editing those presets, but giving you enough that if you say, I want to run something like GFS, that you could make that high-level switch and then say, let's change a couple of little things. Giving folks entry points to what that might be, I've learned recently, might be one way to help out on the research side. So if I want to run something like GFS, but I'd only like to start with the initial conditions from GFS and then run a different forecast from that, then you know, tweaking the physics or whatever that might be. Or I'd like to run something like Rufus, but I want to do a data assimilation experiment. Like, how can I start from that point where I have the background and the observations that I'd like to incorporate, but then I have an entry point to this tool that allows me to do that. So we're taking in all of these requirements as we're listening to all of these use cases across a variety of different organizations at this point to try to figure out how we can make these individual pieces as succinct as possible to do one thing, and then allow you the building blocks to build those up in the way that meets your needs. And I think that that is one way that we can start to move forward in a building block kind of way. In taking that service-oriented architecture approach that I outlined there, we start to see something like a lot of us are starting to get a little familiar with like how to build AWS cloud services. You know, you have a YAML file in a lot of cases where you're gonna define like a piece of that thing and it can hook up to another kind of totally different piece, but they work together nicely, and then you have this whole system working together where data can transfer between each of those. If we have something like that where I want to just configure the model to run in a way that I want, and then I want to configure the UPP to run after that, then we can start to see like, oh, I can just do these two pieces. I don't have to do all of the other pieces with that. This is kind of a long-winded answer, but I think building single-use components of a broader system gives us that ability to start to approach what we need as a broader community.
I had a question also in particular to the workflow, the actual workflow as Rocoto that gets complicated. Will use the EC flow or eventual transition to EC flow be easier to manage? Do you have an experience with that?
So we do have a couple of different workflow managers that we have been historically using, and we are seeing some of the limitations of those. I think that we'll see some other workflow manager options start to come on as we start to get out of our original assumptions about what these systems should do. Everything runs on one particular platform. Maybe we want to run some parts on one platform, some on another. That's way outside the space of what we want to do with Rocoto or EasyFlow. If we can somehow provide a way just for users to specify, I need these resources on this platform, it has these characteristics, and then some tools are kind of the intermediate steps there to get us to whatever it is definition file that sets that up. It's like, I don't know how that's gonna look over time. It may transition, but I think getting away from static XMLs might be one way to go, and just a thought. But you know, having the ability to flexibly define those workflows is going to be an important key, and then having a language to do that that users are comfortable with is going to be another important step. But know that that will be an iterative approach to like trying to figure out where those flexibilities and usability lie.
Thank you. I think we have to move on from the discussion on workflow because we only have half an hour in total. I saw that Paul Ulrich is back online, and you had a question originally from Kevin Weiner from EMC. So would you mind repeating your question?
Yeah, sure. So Paul, I have a few questions about, I guess, home non-hydrostatic vertical coordinate. I was wondering if you all are using that, and if so, what type of remapping method are you using in the vertical, and how often do you remap?
Can you hear me?
Yeah.
Thumbs up. All right, cool. Yeah, it was a struggle before, actually. I had realized that I'm in like the read-only stream and not the write stream as well. But now I'm in the right stream. So yes, it uses a floating Lagrangian vertical coordinate, and that's the default, actually. There is an option for an Eulerian vertical coordinate in the model, but at this point, I'm not entirely clear if it actually will work with the current infrastructure because it's almost never used. And with regards to the remap method, previously we used PPM, but I think there's a new spline-based method that has been adopted for the vertical remap. But I would refer to Mark Taylor and Oksana Guba for specifics on how that works.
Okay, and then one more question. Have you thought at all about adaptive mesh refinement versus the static that you showed in your talk? Or I know there are a lot of different ways to trigger that, so it's a bit nebulous.
Yeah, I mean, I spent a couple of years working on that back in 2009. It, I was never able to satisfactorily get the computational performance out of it that really justified its use. The problem was that figuring out where to refine usually took a ridiculous amount of time, and almost eliminated the benefit for at least climate length simulations. I think probably if you're doing like hurricane tracking, like we saw in some of the wonderful talks earlier today, then maybe it's more justifiable. But yeah, we haven't seen enough incentive really in order to pursue it as a model modification.
Thanks, Paul.
Thank you. Danae, did you have a question?
So just a quick question, Jedi question again. Y'all see want to learn more about what's going on with Jedi, but I'm wondering, like, I know we do in-kind. I know GSL does in-kind towards JCSDA. I think PSL does some in-kind. I'm wondering, what are you doing?
Go ahead, Jeff.
So for PSL, what we're working on is developing the ENKF solver so that we can transition from the GSI ENKF to JEDI. We have a JTTI funded proposal that allows us to do that and contribute that in-kind work to JEDI.
If you want a pretty detailed level of information about what all the components, the core and in-kind staff are doing with the JCSDA, we have a document that we call our annual operating plan that is actually gathering all these information into one coherent plan. It's a long plan with a lot of details in it, but if you're interested, you can actually see each partner, in-kind, core, how it's actually put together into a coherent plan. And that's something that is actually, heavily coordinated among the joint startup partners and signed by all the partner agencies.
Does that actually change every year? Do you measure your success against the AOP? Are those activities completed 100% every year?
I wish it was. So the answer is it's not 100% completed every year, but we do actually look back and report. So what we do is actually break down the annual operating plan into quarters. Each quarter has deliverables. Each deliverable is actually associated with a roll-up release. So the release of the software is actually supposed to deliver the pieces that we've put in the plan. And most of them get delivered, not 100%. And then we actually report on things that get delivered and then get pushed right.
Can you make a quick comment on, you said on FY24 delivery for JEDI, right? What is it? I guess, what does that look like? Can you give us a little bit more detail about what that delivery looks like in 2024? What does that mean exactly?
So I think the AOP is like a 70-page document, so it's going to be with a lot of detail. So I don't know exactly what you're looking for in the AOP, or maybe I misunderstood your question.
So when you say delivery in 2024, does that mean that we'll have a code that the community can start, that basically replaces the GSI, that is more advanced than the GSI, because you talked about all of the different functions that the JEDI system will have. And my assumption in 2024 is, based on what you presented, is that, GSI is gone. We're all using JEDI. We can pretty much do everything that we do with our GSI or DART system, whatever DA system that we use. Is that what that means?
So I think rather than thinking, hey, we're waiting for something to arrive and right now there's nothing, the better way of thinking of it is it's actually a continuous process. So we have actually a series of improving systems. So there's a system right now. Next quarter, that system will have new features, additional features, and it will perform better, and then next quarter, and so on like this. So it's basically a continuously improving approach. So the planning that we have in EOP is basically these new features that get added to the existing capabilities. So there's already a publicly available JEDI system that you can run today, but it doesn't have yet all the features that are needed by the partners. So the plan has actually, a timeline of the delivery for these additional features. Does that help with understanding how we function as a group? All right, yeah, you can.
All right, do you have a question online?
Lisa, yeah, we actually have a question online, but Paul Ulrich asked it. If you want to ask your question.
Yeah, I was just wondering, so Joseph gave a presentation on using an extended grid in order to reduce grid imprinting. And I was just curious how that affected the parallel scalability of the FE cubed model.
Oh, hey, Joseph, are you able to unmute or?
Sorry, I didn't hear the question. It was like, can you please repeat it?
Yeah, so you gave the talk, of course, of the extended grid and interpolation to the extended grid in order to reduce grid imprinting. I'm just curious, because that's only applied in a limited area of the grid, I would expect that would affect the parallel scalability of the model. Do you observe any artifacts of that procedure?
So yeah, we are still working on the computational performance of the GeoGrid code, especially because we have also to apply some to conserve properties such as mass. We have to do extra communication between the different processors that are in the ties, because when we remap the data from different phases, we will have different fluxes. So we are trying to improve that as much as possible. So we haven't really got to the phase where doing like final performance test to give an idea, but that is like really something that we are trying to improve, and that's maybe like one of the things that making that code a little bit slow now, but like we expect to move forward on that. So
thank you.
Thank you. So I have a question for perhaps Neil and Henrik about the concept of having multiple die cores. Something that we would still strive to have a unified die core, or if that's something that could be supported within, I guess, the UFS as a concept. Maybe Henrik.
Why do we need that?
So we have a, it's the unified system. It's not the unitary system. It's not the uncoordinated system. It's the unified system. It's a business model where you look at how can you focus your resources to work together on a small amount of things, while at the same time you have the diversity you need for your mission, for your research, and everything else. So the goal is never been to get rid of as much models as possible and just leave one behind to work with. So the discussion about which atmospheric die core we have may be a little loaded in general, but let's give you the example of other pieces of the UFS. On the ocean side, there is no single model that can do barotropic and baroclinic at the same time, and that can do it at all the different scales at the same time. So when we did unification on the ocean side, the coastal ocean modeling testbed that Tracy is running these days, first did a cook-off of 7 or 8 storm surge models and went down to 1 storm surge model. Then we looked at what do we need for coastal navigation and coastal water quality. That's a 3-dimensional model that we need. And what do we need for the global for the moment still? Well, we need a good model like either MOM6 or HICOM. So on unification on the ocean side meant that we need at least 3 or 4 models. And that's a heck of a lot better than all the models we had before. Unification on the atmospheric side. In my time working at EMC, I have seen 7 different mesoscale models in operations. So going back from 7 to 2 or 1, that's the unification. It's not the goal to get just one. So going back to the atmosphere, in operations, we're trying to go to see if we can go to 1 or not. That's important for EMC because EMC does not want to maintain 4 or 5 die cores with a team that's big enough for 1. So on the research side, I see this very clearly as if there are people in the research community that want to benefit from all the other things in the UFS and want to show that they have a good die core that they could work for the atmosphere with, by all means, bring it in. Don't expect the Weather Service to pay for it until there may be a time that we see that we may either need 2 die cores or we need to change to another die core. At that time, operations will start looking at it. But from a science perspective, the whole idea of a UFS and UFS approach is that if you have something you want to add to a UFS, you think it's going to add eventually to operations, you don't have to wait until operations. You can use that infrastructure. Okay, I'll have to say 2 things about wave models then. So everybody says that we have 1 wave model. That's actually not true. The wave model that's run at NCEP or at UK Met Office or at BOM or at the Navy or at the Corps of Engineers, or it's not true. They're all running the WaveWatch common infrastructure that the whole community uses. There are 4 different die cores or propagation schemes and grids in WaveWatch. There are 6 or 7 physics packages in WaveWatch. All these different groups have different combinations of die cores and physics that they use. And so effectively, the community has an enormous amount of diversity in approaches, but they do it with a single framework. And so that's sort of the picture that I at least personally see as being a really good way of having this broader diversity in research that operations can push from, but nobody is going to be forced in operations to take every option that there is in the research community, and both benefit. Operations can really quickly transition new stuff if it's in there. Research can benefit from the fact that is a joint infrastructure that is being maintained, but also the fact that an operational model is very well fettered compared to a lot of other models, so you can do very interesting research to it. Anyhow, I could talk about this for another 3 hours, but anyway.
We don't have a whole lot of time left. Did you want to make a comment, or you don't have to?
Yeah, there's.
I think Hendrik pretty much summed it up, but from my view of having a community modeling system where we're interested in innovative ideas, it's got to be architected in a way that those ideas can find their way into a system. At some point in the future, we're not going to be using the same die cores we're using now. I don't know what the future looks like, but it's not going to look the same. Well, because I'm assuming someone's going to come up with one that works better than what we have now. Otherwise, what's the point? We'll just flatline our AC scores from now to the future. The point is, it's got to be architected in a way that can accept these innovative ideas. Otherwise, what's the point? Why do we need the community? We'll just have a handful of developers, give them a budget, and what? Tell the community to go pound sand? I mean, that's the whole point of the community model.
The European Center has been using the same spectral dynamical core for 40 years now.
So, Lucas, you had a question. When I raised the point, you had a question, why do we need a new dynamical core?
Yeah, exactly, yes.
So I'm a little bit curious to hear about your impressions of some of the results that's been shown with the Rufus model. That's I guess both NOAA, OAR Labs, and EMC and community has shown that there's some challenges in near grid scale precipitation. Do you have some comments on that or some insights?
Well, I mean, this is an eminently solvable problem. I mean, you know, we showed in our presentation that, yeah, by improving the microphysics, you can solve the problems with too heavy precipitation. And CAPS has shown, as I mentioned earlier, that yes, you can improve the radar data assimilation by making it overall improvements to the model. And I mean, I can't say exactly what the RFS folks are doing, and I know they're working very hard on operational implementation, but I mean, this is an eminently solvable problem. And in my talk, I showed very clearly results from here at GFDL and here and there at University of Oklahoma that this can be fixed.
Okay, thank you. I guess we're coming to the end here, but I'll let Neil respond to that.
So if there's no reason to change the die core, why did we switch to the FE3? Why aren't we still running the AVN and the GFS?
But you know, there is a competition, we entered it, and we were selected. That's the end of the story. You'd have to ask Fred Teffer about that.
And so we're never going to have another competition in the future when something better comes along?
Well, you know, we could just stop all development all the time and just say, hey, we're going to have a new competition this year. And the next year we'll have another new competition. And we could just keep doing this over and over again when some very senior person is upset that what he likes wasn't selected. And we just keep doing it over and over again. Nothing gets into operations. Nothing actually gets better. Everybody just starts hating one another, which is basically the fallout from the whole NGGPS thing. And we just keep going over and over again. You know, I mean, you know, we're very proud of what we did during NGPS, but you know what? It was a miserable experience for us. You know, many of us on our team started having health problems as a result of the vile attacks we were getting from NCAR's team and their allies. We would be insane to do that over again. I know maybe some people are amused by this idea of constantly having new competitions, but think about the people who are actually working to try to improve numerical modeling in America. And I mean, you know, we have a new competition, development stopped during NGGPS for 2 years on basically entirety of NOAA's modeling apparatus, while people waited for what the new die core is going to be or what the new framework is going to be. And we can't simply just keep doing that. The endless competitions don't benefit anybody, it seems.
Thank you, Lucas. So I see some red signs in the back of the room, and we have to wrap up, unfortunately. I think it's a discussion to be continued, definitely, throughout the week. It's a rather important discussion abruptly. But yeah, let's continue throughout the week and some sort of consensus on moving forward. So I don't know if the organizers would like to say some last words or... Okay. Yeah, so thank you everyone for participating in this discussion.
All right, this concludes our second day of the UIF-CW. I would like to thank the chairs, speakers, presenters, and panelists who shared their innovative ideas with us today. And don't forget, tomorrow there will be an 8:30 a.m. Azure training running the short-range weather application version 2.1.0 containers in Azure. And the UIF-CW Day 3 kickoff will begin at 9 a.m. tomorrow morning. And with that, the UIF-CW Day 2 is adjourned.
Oh.
I feel like we probably owe you guys information.